This multiple choice final exam review is for those of you who are taking the first semester of organic chemistry. So let's go ahead and begin. Number one, which of the following functional groups is not found in the molecule shown below? For each of these questions, pause the video and work on the problem first. See if you can get the right answer. And then once you have selected your answer, unpause the video to see the solution. So let's go ahead and begin. Our goal is to find out which functional group is not found in a molecule. So let's identify all the functional groups that are in the molecule. So what is this? What functional group do we have here? CHO. This is equivalent to this expression here. That is an aldehyde. So therefore, we can eliminate answer choice E. Now what about this functional group in the middle with two oxygens? What is that called? That functional group is known as an ester. An ester has this general shape. It has a carbon with two oxygens, and it has an R group, one attached to the carbon and the other attached to the single bonded oxygen atom. So that's an ester. After that, we have an NH2 group. This is known as an amine. You can also write it as RNH2. So D is out of the question. What about this group, this OCH3 group? What functional group is that? So notice that we have an oxygen attached to two carbons, which is basically equivalent to an oxygen attached to two R groups. This is known as an ether. So A is eliminated. Next, we have a COOH group. That is known as a carboxylic acid, which if you write it out, it will look like this. You have an R group, and then you have a carbon, which is double bonded to an oxygen, and it has an OH. So that's a carboxylic acid, and this is an ether. Now, the carboxylic acid is not listed as an answer, so we don't have to worry about that. Next, we have this OH, which is an alcohol. So C is eliminated, which means that B is the right answer. And what about this group? What is this group called? So as you can see, if you see a carbon attached to an NH2 group, that's an amine. If you have an NH2 group attached to a carbonyl group, that is known as an amide or amide, which is not listed. So therefore, answer choice B is the right answer for this problem. Number two, what is the IUPAC name for this compound? Is it A, is it B, or is it C or D? Well, let's find out. The first thing that we need to do is we need to identify the longest chain. So let's begin counting from left to right. This is 1, 2, 3, 4, 5, 6. If we go to the right, it's 7. But if we go up, it's 8. So that is the longest chain. 8 carbons is associated with octane. So we can eliminate answer choice D and C because the parent name is heptane. Now here's a question for you. Should we count it from left to right or right to left? If we count it the way we have it, notice the substituents. We'll have a methyl on 3, a methyl on 6, and an ethyl on 4, which correlates to answer choice B. B has an ethyl on 4 and 2 methyls on 3 and 6. Now, if we count it the other way, notice that we still have a methyl on 3 and 6, but we have an ethyl on 5, which correlates to answer choice A. So do we want the ethyl to be on 4 or on 5? You want to count it in such a way that the substituents have lower numbers. So therefore B is the right answer. So you want to count it in this direction. So when you name it, you want to start with ethyl, since E comes before M. And then we have a 3,6 dimethyl. And then because we have an 8 carbon chain, it's octane. If you recall, methane is associated with 1 carbon, ethane 2, propane 3, butane is 4, pentane is 5, hexane is 6, heptane is 7, octane is 8, nonane is 9, and decane is 10. So B is the right answer for this problem. Number 3, which of the following carbocations shown below is most stable? So what do you think the answer is going to be? So go ahead and take a minute and work on this example. Now, what we need to keep in mind is that tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. And the reason for this is due to the inductive effect and hyperconjugation. In the inductive effect, the carbon atoms, which are electron donating groups relative to the positive charge, they can donate electron density to the positive charge by means of the inductive effect, that is through the sigma bond. So that's one way they can donate electron density to a starving carbocation which really wants electrons. The other way is by means of the overlap of atomic orbitals, which is known as hyperconjugation. So let's say if you have a carbon atom with a plus charge, and let's say there's another CH3 group, and so here's a CH bond that's next to it. So there are electrons in this orbital, and that orbital can overlap with the empty p orbital below it. And so that's how electron density can be donated to the carbocation by means of hyperconjugation, which is through the overlap of atomic orbitals. So when these two orbitals overlap, electron density can be shared. So those are the main reasons why tertiary carbocations are more stable than primary ones. A tertiary carbocation is basically a carbon that has 3 other carbons attached to it. And the carbon in the middle has a plus charge, so it's a carbocation. So that's why it's called tertiary, because there's 3 carbons attached to the carbon with the plus charge. And so the more methyl groups that you have next to the carbocation, the more electron density that can be donated, which means you have a more stable carbocation. Now, what about allylic carbocations? A secondary allylic carbocation is more stable than a regular secondary carbocation. An allylic carbocation is one that has a plus charge 1 carbon away from the double bond. And the reason why allylic carbocations are relatively stable is due to the resonance stabilization of the carbocation. This double bond can move here, creating a resonance form that looks like this. So as you can see, the plus charge is shared between 2 carbon atoms as opposed to 1. And as a result, it's more stable. So those are the main things you need to look for. So keep in mind that tertiary carbocations are more stable than secondary and primary ones, and that allylic carbocations are more stable than those that are not allylic. Now, let's identify the type of carbocation that we have in every choice. So let's start with part A. What type of carbocation do we have? So let's focus on the carbon with the plus charge. How many other carbons are attached to it? So we have 1, 2, 3. Because there are 3 carbons attached to it, it is a tertiary carbon. And notice that it's 1 carbon away from a double bond, which means it's tertiary and it's allylic. Now what about B? What type of carbocation do we have? So focusing on the carbon with the plus charge, that carbon is attached to 2 other carbon atoms and it's adjacent to a double bond, which means that it's secondary and it's allylic. So moving on to part C, the carbon with the plus charge, is adjacent to two other carbons, but it's too far away from the double bond, so it's simply a secondary carbocation. And now this carbon with the plus charge is only attached to one carbon atom, which means it's a primary carbon, and it's too far away from the double bond, so it's not allylic. So therefore, D is the least stable. Primary carbocations are not stable at all. The most stable is answer choice A. It's tertiary and it's allylic. So if we had to rank it, compound A is the most stable. After that, the next most stable is B. A secondary allylic carbocation is more stable than a regular secondary carbocation due to resonance. And then B is more stable than C, and D is the least stable. But answer choice A is the answer. That's the most stable carbocation that we have in this selection. Number 4. Identify the hybridization of the indicated atoms shown below from left to right. So is it A, B, C, or D? How can we determine the hybridization? So feel free to try this one. Now, before we work on the solution, let's review how to find the hybridization of an atom. So let's start with methane, CH4. So what you want to do is count the number of groups and lone pairs attached to the carbon. Single bonds, double bonds, triple bonds, count them as one group. So 1, 2, 3, 4. The carbon atom has 4 groups. 4 groups correlates to sp3. S1p3. 1 plus 3 adds up to 4. So that's the hybridization on the center carbon atom. So let's do some more examples so you can get familiar with this. Next, let's try formaldehyde, since it has a double bond. Now, how many groups are attached to the carbon atom? 1, 2, 3. Treat the double bond as one group, don't count it as 2. So we have 3 groups, which corresponds to sp2. 1 plus 2 adds up to 3. 3 groups will always correspond to sp2. 4 groups will always correspond to sp3. That's a quick and simple way to find the right answer. Now let's try acetylene. What is the hybridization at the carbon and at the hydrogen? So if we focus on the carbon atom, that carbon atom is attached to a hydrogen and a CH group. So it has 2 groups, which means that it's sp hybridized. 2 is basically 1 plus 1. If you don't see an exponent, it's 1. Now what about the hybridization on hydrogen? Hydrogen is only attached to one atom, so it only has one group. One group correlates to S. Now what if there are lone pairs? Let's use ammonia as an example. NH3. What's the hybridization on the nitrogen atom? So what we need to do is count the number of groups and lone pairs. So nitrogen has 3 atoms and a lone pair, so it has 4 groups. And 4 correlates to sp3. 1 plus 3 adds up to 4. Next, let's use sulfur dioxide as an example. So here's the Lewis structure of SO2. What's the hybridization on the sulfur atom? So sulfur has 2 groups and a lone pair. So it has a total of 3 groups, which is sp2. So it's sp2 hybridized. Now what if we have more than 4 groups? Let's use phosphorus pentachloride, for example. What's the hybridization on a central phosphorus atom? So here we have a total of 5 groups. So it's going to be S1, P3, D1. S only has 1 orbital, so there's no S2. P only has 3 orbitals, so you shouldn't have P4. D has 5 orbitals, so we don't have to use all 5. The exponents have to add up to 5. 1 plus 3 plus 1 is 5. So therefore, what do you think the hybridization will be for sulfur hexafluoride? SF6. So sulfur has 6 groups in this case. So 6 corresponds to S1P3D2. 1 plus 3 plus 2 is 6. So now that you know how to find the hybridization of an atom, go ahead and finish this problem. So let's start with CH3. So we have a carbon attached to 3 hydrogens, and it's attached to the carbon at the right. So let's put C here. So this carbon has 4 groups attached to it, which means that it's sp3 hybridized. So let's put sp3 here. Now we need to go in order from left to right. So in each answer choice, the first answer should be sp3. We can eliminate A, which is sp2. So we're between B, C, and D. Now let's move on to carbon number 2. So that carbon, we can see, has 3 groups. It's attached to the CH3 on the left, the CH2 on the right, and the oxygen. 3 groups correlates to sp2. 1 plus 2 is 3. So that's the second answer. It's sp2. So we can keep B, C, and D the same. As you can see, the second answer, they're all sp2, so we can't eliminate anything at this point. Now let's move on to carbon number 3. So we have a carbon that has 2 hydrogens, so we can draw it like this. And then to the right we have another carbon, and to the left we have another carbon. So the carbon, the CH2 carbon, has 4 different groups, and as we know, 4 correlates to sp3. We can eliminate answer choice B because the third option is not sp3. We need to keep C, and we need to keep D. So looking at C and D, we can see that the next option is sp. What we need to focus on is the last one. But if you look at this carbon, you can see why it's sp hybridized. It's attached to a carbon and another carbon. So it has 2 groups, which correlates to sp. 1 plus 1 is 2. Now if we focus on the hydrogen, that hydrogen is only attached to 1 group. It's attached to 1 carbon atom, and 1 group correlates to S. So the hybridization for any hydrogen atoms is always S, because hydrogen cannot form 2 bonds. It can only form 1 bond, which means that C is the right answer. D doesn't have S as the last option, so this is it. Number 5. Which of the following Lewis structures contain a sulfur atom with a formal charge of +1? So go ahead and try this problem. The formula that I like to use is this one. The formal charge is equal to the number of valence electrons minus the number of bonds plus the number of dots in the structure. So let's start with answer choice A. Sulfur has 6 valence electrons. If you go to the periodic table, you'll find that sulfur is in group 6A of the periodic table, and typically elements in that group have 6 valence electrons. So all of the sulfur atoms in each of these molecules have 6 valence electrons as a free atom. Now in structure A, or in compound A, sulfur has 4 bonds. 1, 2, 3, 4. And it doesn't have any visible lone pairs, so it has 0 dots. 6 minus 4 is 2. So the formal charge on this sulfur atom is +2. So we can eliminate answer choice A. Now let's move on to B. Sulfur has 6 valence electrons. In B, it has 6 bonds. 2, 3, 4, 6. It doesn't have any lone pairs, so the number of dots is 0. 6 minus 6 is 0. So we can eliminate answer choice B. It's neutral in that molecule. Now let's move on to C. Sulfur has 6 valence electrons, and in this structure, sulfur has only 1 bond, but notice that it has 6 dots. 2, 4, 6. 1 plus 6 is 7, and 6 minus 7 is -1. Therefore, we can eliminate answer choice C. So D has to be the answer, but let's go ahead and use the formula to get the answer. Sulfur has 6 valence electrons, and this structure has 1 bond plus 2, so that's 3 bonds in total. And we can see that it has 2 dots, or 1 lone pair. 3 plus 2 is 5. 6 minus 5 is 1. And so that's the formal charge of sulfur in answer choice D. So D is the answer. That's what we're looking for. Number 6. Which of the following represents the best Lewis structure for the cyanide ion? Is it A, B, C, or D? So which answers can we eliminate? We're looking at answer choice D. Notice that nitrogen, which is a second row element, has more than 8 electrons. Every bond represents 2 electrons. So it has a triple bond, which equates to 6 electrons, and 2 lone pairs. So nitrogen has 10 electrons around it, which violates the octet rule. Elements in the second row like carbon, nitrogen, oxygen, fluorine, they cannot have more than 8 electrons. In the second row you have 2s2, 2p6. There is no 2d10. So second row elements can have at most 8 electrons. 2 plus 6 is 8. So we can eliminate D. Nitrogen violates the octet rule. Now in answer choice C, what's the issue here? Carbon has an incomplete octet. Notice that it doesn't have 8 electrons, it has 6. Now it's possible for an element to have 6. However, it's not stable, it's not the best Lewis structure. It has 2, 4, 6 electrons, so we can eliminate answer choice C. Answer choice A and B. Carbon and nitrogen both have 8 electrons, which means that their octet requirements are satisfied. Now what we need to look at is the formal charge. We need to find out which one is more stable. The compound that is most stable is the one with the minimum formal charge, where the formal charge is closest to 0. So let's start with B. Let's calculate the formal charge. We know it's equal to the number of valence electrons minus the bonds plus the dots. So starting with carbon, carbon has 4 valence electrons naturally. It's in group 4A of the periodic table. And in this structure, it has 2 bonds and it has 4 dots. 2 lone pairs corresponds to 4 dots. Every lone pair has 2 dots. So 2 plus 4 is 6, and 4 minus 6 is negative 2. So that is the formal charge of carbon in this structure. So let's go ahead and write that. Now what about the formal charge of nitrogen? Nitrogen naturally has 5 valence electrons. It's in group 5A of the periodic table. And in this structure it has 2 bonds, and it also has 4 dots. So 2 plus 4 is 6, 5 minus 6 is negative 1. Now let's go ahead and calculate the formal charge of carbon and nitrogen in the other compound. So starting with carbon, we can see that it has 3 bonds, 1 lone pair. So it has 3 bonds and 2 dots. 3 plus 2 is 5, 4 minus 5 is negative 1. Now what about nitrogen? Nitrogen has 5 valence electrons. It too has 3 bonds. It has a triple bond. And it has a lone pair, so 2 dots. 5 minus 5 is 0. So is it better to have a formal charge of negative 1 and 0, or negative 2 and negative 1? Negative 1 is closer to 0 than negative 2 is, so we can eliminate B. If you have a formal charge of negative 2, it's not good. It's not stable. Also, the total charge for cyanide has to add up to negative 1. If we add these charges, they add up to negative 1. If we add these 2 charges, they don't add to negative 1. So this is not the correct Lewis structure for cyanide. This is it. Number 7. Which of the following represents a pair of resonance structures? Do you think the answer might be A, B, C, or D? So what can we do in order to identify a pair of resonance structures. Is there a better way of figuring this out instead of drawing everything? It turns out that there is. A quick way to identify a pair of resonance structures is to identify the ones that are not resonance structures. If any atoms are moving from one spot to another spot, it's not a resonance structure. If you want to draw a resonance structure, only the electrons are free to move and not the atoms. So if we look at answer choice A, this represents a hydride shift. The hydrogen moved from the tertiary carbon to the secondary carbon. And when that happens, the plus charge is going to move from the secondary carbon to the tertiary carbon. So basically, they trade places. So because the hydrogen was moved, this is not a pair of resonance structures. Now looking at D, we could see that the location of the bromine atom and the hydrogen atom were reversed. So anytime you're moving around atoms, it will not be a resonance structure. So D can be eliminated. In fact, these are basically cis and trans isomers. This is the cis isomer, and this is the trans isomer. In the cis isomer, you have two groups facing one side, and in the trans isomer, the two groups are on the opposite sides. Now let's move on to part C. Notice that we have a keto-enol tautomerization going on here. A hydrogen was moved from this carbon onto the oxygen. Before there were 3 hydrogens, and now we only have 2. So a hydrogen was transferred from one part of the molecule to the other part of the molecule, which means that these two do not represent a pair of resonance structures. The only answer is answer choice B. If you draw all the hydrogen atoms, notice that none of them were moved. We still have 6 hydrogen atoms, 3 on each carbon, and so no hydrogens were transferred. The only thing that moved were the electrons. 2 pi electrons in the double bond was transferred to the oxygen, as we can see here. And anytime you move electrons without moving atoms, you're going to generate a resonance structure. So answer choice B is the right answer. Number 8. Which of the following would best act as the Lewis base? So in this problem, we need to identify which ones are the Lewis acids and eliminate them. And then we can easily see which one's going to be the Lewis base. A Lewis base is a nucleophile. It's electron rich. It's full of electrons, which means that it has a lot of lone pairs and it may have a negative charge. A Lewis base can donate a pair of electrons. Lewis acids, on the other hand, are electrophiles. They're electron poor. They're deficient in electrons, and typically they may have a positive charge. But the most important thing you need to know is that they have the ability to accept a pair of electrons. So let's look at answer choice A. Is it a Lewis base or is it a Lewis acid? Can it accept a pair of electrons or will it donate a pair of electrons? If we draw the resonance structure, notice that the carbon atom will have a positive charge. The oxygen now has a negative charge. So therefore, the carbonyl group, which correlates to aldehydes and ketones, they're typically electrophilic. They tend to act as Lewis acids. Let's say if we take a Lewis base like hydroxide. Hydroxide can donate a pair of electrons to the carbon, which means that acetone and ketones and aldehydes are all electrophiles, which means they're Lewis acids. So we can eliminate answer choice A. Now what about answer choice B? Is it a Lewis acid or is it a Lewis base? Or is it neither? Let's find out. So the methyl radical has an unpaired electron. Since it doesn't have a pair of electrons, it cannot act as Lewis base. For anything to act as a Lewis base, it has to donate a pair of electrons, which means 2 electrons. The radical only has 1 unpaired electron, so it can't donate 2 electrons. It doesn't have it. Now, can the methyl radical accept a pair of electrons? So let's say if we react it with hydroxide. Can hydroxide donate a pair of electrons to it, forming a bond? Let's say if it did. This bond will be created, and the oxygen, which had 3 lone pairs, now has 2. The carbon still have the 3 hydrogens, and it should still contain the radical, or this unpaired electron. Notice that this structure is not possible. Carbon cannot have 4 bonds and at the same time have an unpaired electron. That would violate the octet rule, and it's not possible. Carbon cannot have 9 electrons, which means that a radical cannot behave as a Lewis acid, nor can it behave as a Lewis base. Particularly this particular radical. Now what about BH3? Is that a Lewis acid or is it a Lewis base? So we can see that boron doesn't have a lone pair. So it can't act as a Lewis base. It can't donate a pair of electrons. However, it can act as a Lewis acid. It can accept a pair of electrons from hydroxide. And then what's going to happen is we're going to get this product. So in this example, hydroxide, which donated the pair of electrons, is the Lewis base, or the nucleophile. BH3, which accepted the pair of electrons, is the Lewis acid, also known as the electrophile. So by default, the answer has to be water. And if we draw water, water has a lone pair. We can draw it like this. It has 2 lone pairs actually. And let's react it with BH3. So like hydroxide, water can use one of its lone pairs and donate it towards the boron atom. And so we're going to get a product that looks like this. Boron is going to have a negative formal charge. Oxygen is going to have a positive formal charge. And so we can clearly see that water is behaving as the Lewis base, which is the nucleophile. So D is the right answer. Number 9. Which compound is the strongest acid? So let's look at each answer choice. So for answer choice A, we have a carboxylic acid. You can see the functional group COOH. And what you want to do is you want to be able to determine the pKa of each of these molecules. If you know the pKa, you can tell which one's the strongest acid. As the pKa decreases, the strength of the acid increases. So the one with the lowest pKa is going to be the strongest acid. Carboxylic acids have a pKa of about 4 to 5. Now, answer choice B, we have an alcohol, which most alcohols have a pKa roughly between 16 and 18. In the case of ethanol, ethanol has a pKa of 15.9. Answer choice C represents phenol. It has 6 carbons, 5 hydrogens, and an OH group. Whenever you see C6H5, it's a benzene ring attached to something else. Every carbon atom in a benzene ring has 5 hydrogen atoms. So C6H5 represents phenol. And phenol has a pKa of about 10. Next we have methylamine. Most amines have a pKa roughly of about 35 to 40. And E is a sulfonic acid. Whenever you see an SO3H group, these acids are very strong. This particular acid has a pKa of about -2. So the right answer is answer choice E. But now let's talk about it. Let's go over a few things. So how can we find out the answer if we don't know the pKa values? The first thing you want to compare is the element attached to the hydrogen atom. In our examples, it's either an OH group or an NH2 group. The carboxylic acid has an OH group. The ethanol molecule and phenol has an OH group. Even the sulfonic acid has an OH group. The only one that's different is the NH2. So whenever you have a different element attached to a hydrogen, you can use the trend found in a periodic table. Acid strength increases as you go to the right due to increase in electronegativity, and as you go down due to increase in size. So what this means is that HI is more acidic than HBr, which is more acidic than HCl, and that's more acidic than HF. HF is more acidic than water, and water is more acidic than NH3, which is more acidic than CH4. But let's focus on this. Water contains an OH bond. NH3 has an NH bond. So the OH bond is more acidic than the NH bond if everything else is equal, assuming that they have the same charge. If one is positive and one is neutral, you can't use this comparison. Either they both have to be neutral, or they both have to have a negative charge, or both be positively charged. So the OH group is more acidic than the NH group, which means that D cannot be the strongest acid. So that's how you can eliminate D without knowing the pK values. Now let's look at B and C, because both of them contain an OH group. So ethanol has a pKa of 15.9, and phenol has a pKa of 10. And they both have an OH group attached to a carbon. So why is phenol much more acidic than ethanol? The answer has to do with the stabilization of the conjugate base. The more stable the conjugate base is, the more acidic the conjugate acid will be. So that's the conjugate base of phenol, also known as ethoxide. And this is going to be the conjugate base of phenol, which is phenoxide. So the conjugate base of ethanol is ethoxide, in case I said that incorrectly. And the conjugate base of phenol is phenoxide. So notice that the negative charge on phenoxide is not localized, it's delocalized. It can move around. We can draw a resonance structure, take a lone pair, form a double bond, and push the negative charge here. Because the negative charge can move about the ring, the conjugate base is more stable. And when you have a more stable conjugate base, you're going to have a stronger conjugate acid. So the negative charge is shared between the oxygen atom and 3 other carbon atoms. The negative charge can jump every 2 carbon atoms, so it can move to these other positions indicated in red. So that's why phenol is more acidic than ethanol. It's due to the resonance stabilization of the conjugate base. So we can eliminate answer choice B, since C is more acidic than B. Now let's compare A with C. So let's start with the conjugate base of phenol. Let's redraw it. And if we draw the resonance structure, we know that this electron, or those pair of electrons, can move here, pushing a negative charge on the carbon atom. And that will give us this particular resonance form. And we can draw 2 other resonance forms. So this lone pair can move here and push the other 2 electrons on the next adjacent carbon. So now the negative charge is in that position. So the negative charge is going to keep jumping 2 carbons away. So now we can draw another resonance form. So as you can see, the phenoxide ion has a total of 4 resonance forms. The negative charge can be placed on 1 oxygen atom or 3 carbon atoms. Now let's draw the conjugate base of acetic acid, which is known as acetate. And let's draw the resonance form. To draw the conjugate base, all you need to do is take off the hydrogen. Now this negative charge can move to the other oxygen atom, giving us these 2 resonance forms. So here's a question for you. Why is it that phenol is more acidic than acetic acid? I take that back. Why is it that acetic acid is more acidic than phenol when the phenoxide ion has more resonance structures? Because typically, the more resonance forms that you have would indicate a more stable conjugate base, which means a stronger acid. But we don't see that. Acetic acid is stronger. And it only has 2 resonance forms when we draw the conjugate base of acetic acid. So why is it that acetic acid is a stronger acid when it should be phenol, if we look at the number of resonance structures? So, not only should you look at the number of resonance structures, but you should look at where the negative charge is being placed on what type of atom. Is it better to put a negative charge on an oxygen atom or on a carbon atom? Oxygen is more electronegative than carbon. Electronegativity increases towards the right. So it's a lot more stable to put a negative charge on an oxygen atom than a carbon atom. So if we look at the first resonance structure, the negative charge is placed on the oxygen atom. So let's assume that those 2 are equivalent. Now, in the second resonance form of the acetate ion, the negative charge is also on an oxygen atom. But in the remaining 3 forms of the phenoxide ion, the negative charge is on a carbon atom. It turns out that putting a negative charge on a single oxygen atom is more stable than putting a negative charge on 3 carbon atoms, because carbon really doesn't want to have a negative charge. Oxygen can stabilize it better. And so that's why acetic acid is more stable or more acidic than phenol, is because you have a negative charge on 2 oxygen atoms as opposed to 1 oxygen atom in the case of phenol. So putting a negative charge on a second oxygen atom increases the stability by a huge amount, as you can see based on the number. Acetic acid is much more acidic than phenol. Now this case is apparent if you compare answer choice A and answer choice E. So let me get rid of this stuff. So let's draw the conjugate base of methane sulfonic acid. Instead of drawing a methyl group, I'm just going to represent it with an R group. So we need to take off the hydrogen. Now, if we draw the resonance form, we can take a lone pair and form a double bond, causing the negative charge to move on the other oxygen atom. So we can get this resonance form. And to get the next one, we can use a lone pair, form a double bond, breaking the other pi bond. So as you can see, because there's 3 oxygens, there's 3 different resonance forms that we can draw for the sulfonic acid. So the negative charge is shared between 3 oxygen atoms as opposed to 2 in the case of acetic acid. And we can see the pKa difference is significant. So that's why methane sulfonic acid is the most acidic one, is because first you're placing a negative charge on an atom that can stabilize it or that can take the negative charge, like oxygen. and the quantity of oxygen atoms. There's 3 resonance forms. That negative charge can be shared between 3 oxygen atoms as opposed to 2 in the case of acetic acid, or as opposed to 1 in the case of phenol. So the more resonance structures that you have, and if you can place it on an atom that can stabilize the negative charge, that will increase the stability of the conjugate base, making the conjugate acid more acidic. Number 10. What is the IUPAC name for the compound shown below? So take a minute and work on this problem. So what do you think we should do first? The first thing that I would recommend doing is converting the condensed structure into a line structure. So we have a CH3 and a CH2. That's 2 carbons right there once you draw a single line. And then we have a carbon double bonded to another carbon. And then we have a CH3 on the bottom, a CH2 on the top, and then a carbon which is attached to 3 methyl groups. And then let's draw the hydrogen as well. So that's the line structure. Now the next thing we need to do is identify the longest chain. So if we start from this end, this is going to be carbon 1, 2, 3, 4, 5, 6, 7. So it's going to be a heptane derivative as opposed to a hexane derivative, which means we can eliminate D. Hexene indicates that there's 6 carbon atoms in the longest chain, but we can see that there's 7. Now we need to know the right direction in which to count it. Should we count it from left to right or right to left? As we count it from right to left, notice that the double bond is between carbons 4 and 5. We need to give the double bond priority. Let's count it in the other direction. So let's say this is carbon 1, 2, 3, 4, 5, 6, and 7. Notice that if we count it from left to right, the double bond is now between 3 and 4 instead of 4 and 5, which is better. So now let's go ahead and name it. Notice that we have a methyl group on carbon 4, and we have 2 methyl groups attached to carbon 6. So it's 4, 6, 6 as opposed to 2, 2, 4. Now we're between A and B. Everything looks the same except one is E and the other is Z. So we need to know which isomer do we have. Is it E or is it Z? So we need to determine which group has more priority. So on the left side, is it the hydrogen or the ethyl group? The ethyl group has more priority than the hydrogen. Carbon has a higher atomic number than hydrogen. Now what about on the right side? Is it the methyl or is it these groups of carbons that we see here? If you have a chain of carbons, that's going to have more priority than a single carbon atom. If you analyze this is a methyl carbon compared to a secondary carbon. A secondary carbon has more priority than the methyl carbon. So the highest priority groups are on opposite sides. When they are on opposite sides, you have the E isomer. If they're on the same side, you have the Z isomer. So answer choice A is the right answer. Number 11. Which of the following molecules has the S configuration? A, B, C, or D? Well, let's find out. Let's start with A. So first, we need to rank each group based on their atomic numbers. Bromine has the highest atomic number, so we're going to give it a score value of 1. It has the highest priority. Next, fluorine has the second highest atomic number, and then it's carbon. So fluorine is going to be group number 2, carbon is 3, and H is number 4. So what you do is you count it from 1, 2, and 3. Ignore 4. So going in the direction starting from 1 to 2 to 3, notice that it's rotating in the clockwise direction, which is R. Now before you count it, you need to make sure that group number 4 is in the back, which it is. So A is not the answer we're looking for because it has the R configuration. So we can eliminate answer choice A. Now let's move on to B. So we can see that it's relatively easy to assign the configuration whenever H is in the back. You just simply have to count it in a direction starting from 1 to 2 to 3. Now what about when H is in the front? Well, let's do everything that we did. We know H is going to be number 4. Now, between these three groups, they all start with a carbon. But the CH3 doesn't have an oxygen, so this is going to be group number 3. Between these two, which one will have a higher priority? Well, the carboxylic acid has more oxygens than the alcohol. So therefore, that's going to be group number 1, and this is going to be group number 2. So what you need to do is count it in a direction from 1 to 2 to 3. But because H is in the front, you need to reverse it. As we go from 1 to 2 to 3, this is clockwise. That's R. But because H is in the front, and we want it to be in the back, we need to reverse it. So we get S, which means that C is the correct answer. So you always want group number 4 to be in the back. Now we know that B and D has to be R, but for the sake of practice, let's go ahead and work through those examples. Let's prove that it's R. Now in B, notice that group number 4 is not in the back. So what do you do in a situation like that? Well, let's find out. So we know hydrogen is going to be group number 4. But which one is group number 1? So notice that we have a carbon atom, and a sulfur. You need to compare the first atom that's attached to the center carbon atom before you look at the second atom. So you can't look at bromine yet. You have to focus on the CH2. Sulfur has a higher atomic number than both of these carbon atoms. So therefore, sulfur, or the SH group, is group number 1. It has the highest priority. Now, these two carbon atoms are similar, so let's move on to the second atom relative to the chiral carbon, and let's see if there's a difference. Bromine has a higher atomic number than oxygen. So therefore, this is going to be group number 2, and this will be group number 3. Now, there's a method that you can use if you don't have, let's say, like one of those ball and stick models. This is a method that I use to quickly determine if it's going to be R or S. If you have a group that's in the front or in the back, put it in a circle. So group number 2 is in the front, which means that we're going to have to reverse our answer to get the right answer when we assign R or S configuration. Now, at the top we have number 1. To the right of number 1 we have a 4. And to the left of number 1 we have the 3. So you want to put the 3 numbers similar in the form of a triangle around the number that's in a circle. Now, currently group number 1 is on top. We want to rotate the molecule such that group number 4 is on top. So let's rotate it counterclockwise. So now 4 is going to be on the top, 2 is still in a circle, and keep in mind, the stuff that's in a circle represents what's in front. Now 1 is going to be to the left, and 3 has moved to the right. Now what we're going to do is we're going to flip the molecule. We're going to flip it in such a way that number 4 is going to kick out number 2. So 4 is going to be in the front. 1 and 3 are going to flip in the upward direction. So 4 is in a circle, 2 has been kicked out, and 1 and 3 are at the top now. Now we can count it from 1 to 2 to 3. So right now, this appears to be S, counterclockwise. But because number 4 is in the front, we need to reverse it. So the answer is R, which means B is not an answer. Now what about the last one, D? The answer that we're looking for is S, and we know that C is the right answer. So let's prove that answer choice D has the R configuration. Feel free to try this method yourself. Go ahead and pause the video and try it. So first, let's identify the 4 groups that we have. We know the hydrogen is number 4. Now if we compare the carbon atoms with the oxygen, oxygen has a higher atomic number, so the OH group is number 1. Now comparing the methyl group and the aldehyde group has an oxygen, so it's going to beat the methyl group. So this is going to be number 2. The methyl group is number 3. So group number 3 is in the back. Let's put that in a circle. So for this one, we don't have to reverse it because what's inside the circle is already in the back. We want group number 4 to be in the back of the molecule. Right now, group number 1 is on top, so let's put that here. 4 is to the right of number 2, and 2 is to the left. So let's rotate the molecule counterclockwise. We want 4 to be on top, so we can kick out 3. So now we're going to flip the molecule such that 4 kicks out 3, and 1 and 2 are going to flip to the top. So it's going to be 1, 2, 4 in the center, 3 below. So keep in mind, what's in a circle represents what's in the back. So we just got to count it from 1, 2 to 3. So this is the R configuration. So therefore, only answer choice C has the S configuration. So answer choice C is the right answer. Number 12. Which reaction will generate a pair of enantiomers? What do you think the answer is going to be? Well, let's start with D. If we combine an alkene with osmium tetroxide and H2O2 or hydrogen peroxide, we're going to get 2 alcohol functional groups on the same side, basically with syn addition. Now we can get 2 in the front and we can get 2 in the back. So these 2 molecules, are they a pair of enantiomers or is it a single meso product? It turns out that these are the same. Notice the symmetry. Even if the chiral centers change configuration, if there's a line of symmetry, it will not be a pair of enantiomers. Instead, we have a meso product, which means these 2 compounds are identical. So therefore, D is eliminated. That's a meso product. Now what about answer choice C? Deuterium works the same way as hydrogen. Deuterium will add across the double bond, turning it into a single bond. And the reaction proceeds via syn addition, which means the 2 deuterium atoms will be on the same side. So therefore, this will generate a meso product as well. So you get a single product. So answer choice C is eliminated. Now let's move on to B. If we combine an alkene with a peroxy acid, it could be RCO3H. Another peroxy acid you might see is MCPBA. Basically, they do the same thing. If we put these 2 together, we're going to get an epoxide. Now the epoxide reaction works with syn addition, which means that it's on the same side. So we can write it like this. This is one way we can draw the product. We can also draw it like this as well. So as you can see, there is a line of symmetry. And so it can't be a pair of enantiomers if there's a line of symmetry. So this too generates a meso product. So B is eliminated, which means A has to be the answer. Bromine adds across the double bond via anti-addition. And so the products will look like this. Notice that all chiral centers have been reversed in the 2 products, and also that we do not have a line of symmetry. So if you look at it carefully, this side is the same as that side. And these 2 BRs are not the same. One is in the front and the other is in the back. Now you might be thinking, well, there's 2 carbons here, only 1 carbon here. But if you draw it like carefully, let's say if we draw it this way, the line of symmetry really exists here. So as you can see, these 2 carbons, they're symmetrical about each other. This is on the line of symmetry. And these 2 bromine atoms because one is in the front and the other is in the back, they're not symmetrical. So that's why we don't have a line of symmetry in this case. And so A would represent a pair of enantiomers. Number 13. Which of the following Newman projections represents the most stable conformation of this molecule here? So go ahead and try this problem. The first thing we should do is we should draw a better structure. Let's expand the condensed structure. So let's start with the CH. So that carbon has a hydrogen and it has two CH3 groups attached to it. So it looks like this. Next, it's attached to another CH group. So basically that's a carbon with a hydrogen. And this CH is attached to a CH3 and it's attached to a CH2 CH3 group. So that's the structure that we have. And looking at the answers, we can see that these two methyl groups corresponds to these two methyl groups. And this hydrogen also corresponds to it. So therefore, we're viewing it along the C2-C3 bond. So the C2 carbon is the one in the front. The C3 carbon is behind it. We can't see it. Now attached to the C3 carbon, we have, I'm going to highlight it in yellow, we have a CH3 group, we have a hydrogen, and we have an ethyl group. So now you know how to turn a condensed structure into a Newman projection. So looking at A, B, and C. A, B, and C have the right number of carbons. However, D does not. A, B, and C all have 3 methyl groups. Answer choice D only has 2 methyl groups. So therefore, D doesn't have the right number of carbons. We can eliminate answer choice D. Now let's just get rid of a few things. So we need to identify the most stable conformation of the Newman projection that represents this molecule along the C2-C3 bond. So how can we do this? We need to count the number of gauge interactions. This is a gauge interaction. The CH3 groups are 60 degrees apart. So we'll call this a methyl-methyl gauge interaction. This is another methyl-methyl gauge interaction. And that's a methyl-ethyl gauge interaction. So A has 3 gauge interactions. B also has 3 gauge interactions. Here we have a methyl-ethyl gauge interaction, another methyl-ethyl, and a methyl-methyl gauge interaction. Now looking at answer choice C, there's only 2 gauge interactions. A methyl-methyl gauge interaction and a gauge interaction between a methyl and an ethyl group. So because answer choice C has the least number of gauge interactions, and all of these are staggered conformations, answer choice C represents the most stable conformation. Now between A and B, which one is more stable? So the methyl-methyl gauge interactions are the same, so we can cancel one of them. And the methyl-ethyl gauge interactions are the same. Now B has an additional methyl-ethyl gauge interaction. A has an additional methyl-methyl gauge interaction. So which requires more energy? To put a methyl group next to an ethyl group or 2 methyl groups next to each other? Now the ethyl group is bulkier or bigger than the methyl group, so there's going to be more steric strain when a methyl interacts with an ethyl. So therefore, because it's more steric strain in answer choice B, it's going to be less stable than A. So if we had to rank it, C would be number 1. It's the most stable. Then A would be number 2. It's the second most stable. And B would be number 3. It's the least stable out of what's listed here due to the extra methyl-ethyl interaction. And we can't compare D because that represents a completely different compound. But C is the right answer for this problem. Number 14. Which is the most stable conformation of trans 1-fluoro 4-methylcyclohexane? So first, let's identify which of these represents trans and which ones are cis isomers. So A, is it a trans isomer or a cis isomer? The fluorine is in the equatorial position, which is towards the side. But notice that it's going down slightly, so it's equatorial down. And the methyl group is in the equatorial position, but it's slanted slightly up. So if one position is up and the other is down, that is going to be the trans isomer. Now looking at answer choice B, the fluorine is in the axial up position. So I'm going to put U for up. The methyl group is in the axial down position. So that also represents a trans isomer. In answer choice C, the fluorine atom is in the equatorial down position, and the methyl is in the axial down position. So because they're both in the same direction, that is in the downward direction, this represents the cis isomer. Now for answer choice D, fluorine is in the up position, and methyl is in the equatorial up position. So they're in the same direction, so this also represents a cis isomer. So we can eliminate answer choice C and D. We're looking for the trans isomer. Now in answer choice A, both groups are in the equatorial position. In answer choice B, they're both in the axial position. Which one is more stable, axial or equatorial? Well, there's something called 1,3-diaxial strain. So let's say if we start from the fluorine. On the third carbon, you have a hydrogen. And if you count in the other direction, there's another one. Fluorine interacts with these hydrogen atoms, making the axial position less stable. So therefore, the most stable conformation is the one that has all the groups in the equatorial position. So answer choice A is the answer. Number 15. Which reaction will produce a racemic mixture of chiral products? So what do you think the answer is going to be? Well, let's go through each one. Once we add HBr to a double bond, or to an alkene, the double bond is going to turn into a single bond, and we just got to add the bromine atom. Now, this reaction typically occurs with more carbon-to-carbon chemistry. However, because the two carbon atoms across the double bond have the same substitution, they're both secondary carbons, this reaction is not regioselective. So you can put the bromine atom on any one of those two carbon atoms. So let's put it there. This particular product, is it chiral or achiral? The carbon that bears the bromine, does it have 4 different groups? It has a bromine atom, it has a hydrogen atom, but notice that the left side is equivalent to the right side, so it's not chiral. So that's an achiral product, which means we can eliminate answer choice A. Now what about B? Will B generate an achiral product? Well, this carbon is secondary, this one is tertiary. The bromine is going to go on the tertiary carbon. The reason for that is because tertiary carbocations are more stable. And we can go over the mechanism later. But for now, this is going to be the product. Now, this particular product, is it chiral or achiral? So analyzing the carbon that has the bromine atom, that carbon has a bromine atom, an ethyl group, but notice that it has 2 equivalent methyl groups. So it doesn't have 4 different groups, which means that it's achiral. So we can eliminate answer choice B. Now what about C? In this reaction, there's going to be a carbocation rearrangement. You're going to get the same product as answer choice B. So C is eliminated. The correct answer is D. But let's talk about why. We have one butene, and we're going to react it with hydrobromic acid. So in the mechanism, the first thing that's going to happen is the nucleophilic double bond is going to grab a hydrogen in HBr, expelling the bromine atom. Now initially, bromine has 3 lone pairs, but once the HBr bond breaks, bromine is going to pull the electrons toward itself. Bromine is more electronegative than hydrogen, and so when that bond breaks, that's why it pulls the electrons toward itself. Now, where is the hydrogen going to go? Should we add the hydrogen to, let's say, the primary carbon or the secondary carbon? The hydrogen is going to go on a primary carbon. If we put it there, we're going to get a more stable secondary carbocation. If we put the hydrogen on a secondary carbon, we're going to get a less stable primary carbocation, which we don't want that. So now, the bromide ion, which now has 4 lone pairs instead of 3, and it has a negative charge, it's attracted to the carbocation. And so it could approach it from the front or the back. And that's why we can get a racemic mixture of products. So if it approaches it from the front, we can get this product. Or if it approaches it from the back, we can get this product. And both of these compounds are chiral. So if we analyze this carbon, it has a CH3 group, it has a bromine, it has a hydrogen, and it has an ethyl group. So we have a racemic mixture of chiral products. Now granted, this may not be a 50-50 equal racemic mixture. It could be 40-60, 55-45, but we do have both enantiomers though. Now what about the other reaction in part C? We mentioned that we're going to go over it. Let's talk about the mechanism. So just like in the previous reaction, the double bond is going to react with HBr. It's going to acquire the hydrogen. And just like before, we're going to put the hydrogen on the less substituted carbon, that is the primary carbon, so we can get a more stable secondary carbocation. Now the secondary carbocation is adjacent to a tertiary carbon. Whenever you see that, there's going to be a hydride shift. And so this hydrogen is going to glide towards that carbocation. And so the hydrogen and the carbocation, they're going to trade places. So now the plus charge is on the tertiary carbon. And the bromide ion can attack from the front or the back, but it doesn't matter because that carbon is not chiral due to the methyl groups. So because that carbon has 2 methyl groups, it doesn't have 4 different groups. So therefore this product is achiral. And based on this mechanism, you can write out the mechanisms for answer choice A and B. There's no carbocation rearrangement for those. So the first step is going to be the same. You just add HBr, and then the bromide attacks the carbocation, and you'll get the product. So that's it for this problem. 16. Which radical is most stable? Is it going to be A, B, C, or D? Well, let's identify each radical. So let's start with A. This carbon is secondary because it's attached to 2 other carbons, and it's adjacent to a double bond. So this is a secondary allylic radical. Now looking at answer choice B, this carbon is also secondary, and it's it's 1 carbon away from a benzene ring. So this is a secondary benzylic radical. Here we have an arrow radical. The unpaired electron is directly attached to a double bond. And for answer choice C, we have a tertiary benzylic radical. And the reason why it's tertiary is because the carbon that bears the radical is attached to 3 other carbons. and it's one carbon away from the benzene ring. So which of these is most stable? Well, it turns out that the tertiary benzylic radical is the most stable. One, tertiary radicals are more stable than secondary radicals. By the way, this is a secondary aryl radical. The radical is attached to two other carbon atoms. So we have the most substituted radical in answer choice C, but also notice that it's attached to 3 benzene rings. So there's a total of 10 resonance structures that you can draw. There's 9 additional structures, including, well, if you add this one, then it's a total of 10. But not including this one, there's 9 other resonance structures that you can draw. This compound only has a total of 4 resonance structures. A only has a total of 2 resonance structures. D doesn't have any. D is the least stable. It's not good to put a radical directly attached to a double bond or directly on a benzene ring. So if we had to rank it, C is number 1. It's the most stable. The second most stable, would you think it's A or B? The second most stable is going to be B. The secondary benzylic radical, as we mentioned before, it can form 4 resonance structures, including the one that you see here. Whereas in A, we can only get 2 resonance structures. So therefore, B is going to be the second most stable, A is the third most stable, and D is the least. Now let's talk about the resonance structures that we can draw. Let's start with the secondary allylic radical. Now when dealing with radical compounds, you need to use half arrows. Half arrows represent the flow of 1 electron, and a full arrow represents the flow of 2 electrons. So the double bond basically has 2 electrons on it. So we can represent it like this. One of the electrons will move to form a double bond, and the other unpaired electron will move in this direction. The other one will stay where it is. So we're going to get this particular resonance form. And there's going to be a radical left on the primary carbon. Which of these 2 resonance contributors is more stable? Which one contributes more to the resonance hybrid? The one that's more stable is the secondary radical. Secondary radicals are more stable than primary radicals. So if you ever get a question to ask you which one is the major resonance contributor, it's simply the resonance form that's more stable. Now let's say if you're going to draw the resonance structure from this form instead of using 2 dots here. Here's what you need to do. There's going to be 3 arrows that you need to show instead of 2. So the first arrow and the second arrow is going to be the same. However, you need to show this third arrow where the radical is going to be placed on the primary carbon. And this would lead us to get this product. Now going back to this compound, let's show all 4 resonance structures. Feel free to pause the video and try it yourself. So first, we can break this double bond and put a radical 2 carbons away from the first one. So the radical is over here. Next is going to jump 2 carbons away to the next position. So 1 electron will move over here, and this radical, or that unpaired electron, will combine with it to form a double bond, and the other unpaired electron will form a radical 2 carbons away. So now we have a double bond here, and this is a tertiary radical. Now for the last one, we can follow the same process. So this is the 4th resonance structure that we can draw. And so that's it. So now you know how to draw the different resonance forms when dealing with radicals and double bonds. Number 17, which proton is most acidic? Well, let's find the pKa values. And whichever hydrogen has the lowest pKa value, that's going to be the one that's most acidic. So what is the pKa of a hydrogen that's attached to, let's say, an alkyne? The pK is about 25. For a hydrogen that is basically part of an alkane carbon, the pK is very high. It's about 50 to 60. A hydrogen that's attached to an alkene, the pK is around 44, if I remember correctly. It's somewhere in the 40s. And for an alcohol, the pKa is about 16 to 18. So clearly we can see that the OH group is going to be the most acidic. It has the lowest pKa value. So D is the answer. So if we had to rank it, this is the most acidic. The second most acidic is the hydrogen that's attached to the alkyne. This is the third most acidic, and this is the least. And so that's it for this problem. Number 18. Which halide will react most rapidly with a hydroxide ion in an SN2 reaction? Is it A, B, C, or D? Well, the first thing that we should do is we need to convert the condensed structure into a line structure. So let's start with A. We have a carbon that's attached to 3 methyl groups, and we have a bromine atom on it. So basically, this is a tertiary alkyl halides. It turns out that tertiary alkyl halides do not work very well in an SN2 reaction. And the reason for that is due to steric hindrance. The hydroxide, which is the nucleophile, is going to have a difficult time approaching the carbon that it needs to attack. And the reason for that is because these bulky methyl groups, they block approach to the carbon that it has to attack. So those methyl groups block that carbon, they protect them from nucleophilic attack. And so that's why tertiary alkyl halides do not work very well for SN2 reactions. So A is eliminated. Now looking at answer choice B, this is 1-bromobutane. So we have 4 carbons and a bromine atom. That's a primary alkyl halide. Primary alkyl halides work pretty well for SN2 reactions. Methyl halides work better than primary halides because the methyl carbon is very accessible to the nucleophile. Primary halides work better than secondary ones, and secondary halides are more accessible than tertiary ones. Answer choice C has 3 carbons and a bromine atom. But answer choice C represents a primary allylic halide. And answer choice D represents a vinylic halide. The bromine is attached to a carbon that is part of the double bond system. Now, something else that you need to know is that vinylic halides do not work at all for SN2 reactions and for SN1 reactions. So therefore, we could eliminate answer choice D. So we're between B and C. So which is better, a primary alkyl halide or a primary allylic halide? It turns out that allylic halides are more reactive toward SN1 and SN2 reactions than their alkyl halide counterparts. So a primary allylic halide works better than a primary alkyl halide. So C is a better substrate than B. It's going to react more rapidly in the SN2 reaction. So this is the answer. 19. What is the major product that results when R2-bromobutane reacts with sodium iodide and acetone? So first, let's draw R2-bromobutane. We need to put the bromine atom in the front, and we need to put the hydrogen in the back. So let's make sure it's R. The bromine atom has the highest priority. Next is the ethyl group, then the methyl group. So if we count it from 1, 2 to 3, H is in the back, which is group number 4. We can see that we have the R isomer. Now we're going to react this with sodium iodide and acetone. So what kind of reaction will we have? Is this an SN2 reaction? Is it an SN1? Typically, when you have an alkyl halide reacting with some sort of nucleophile, you have to think about nucleophilic reactions and elimination reactions. This particular reaction is an SN2 reaction. We have the secondary alkyl halide, and sodium iodide, the iodide part, is a good nucleophile, and acetone is a polar aprotic solvent. Aprotic solvents do not have any OH or NH groups, and they work well for SN2 reactions. So what kind of product will we get? In the SN2 reaction, the iodide is going to attack the substrate. It's going to act as a nucleophile. It's going to attack the carbon from the back, expelling the bromine atom. Because it approaches it from the backside, we're going to have inversion of configuration. So the iodide is going to be in the back, and now H is in the front. So before we had the R isomer, now we have the S isomer. So the product is 2-iodobutane, but the S isomer. So B is the answer. The only way we can get a mixture is if it was an SN1 reaction. Then D would be correct. But this is an SN2 reaction, which doesn't yield a racemic mixture. It only gives you the inverted product. So SN2 reactions always occur with inversion of configuration. So B is the answer. Number 20. Which reagent will produce the product shown below? So how can we convert 3-methyl-1-butene into 3-methyl-2-butanol? Well, let's start with answer choice A. Water with H plus is equivalent to H3O plus. This reaction will give us an alcohol, but rearrangements will occur. It turns out that the OH group will be on the tertiary carbon, which is not what we want. So answer choice A is not the right answer. Now let's focus on answer choice B. Hydroboration followed by oxidation. This reaction occurs with Markovnikov anti-regiochemistry, or just anti-Markovnikov regiochemistry. You know what I mean. In this case, the OH group will be on the less substituted carbon atom of the double bond. So it's going to go on a primary carbon as opposed to the secondary one. So B won't give us the answer that we want. Now, answer choice C. We have MCPBA, metachloroperoxybenzoic acid. Once we add that, we're going to get an epoxide, which will look like this. And then once we add H3O plus, the ring will open, giving us 2 alcohols, which we don't want 2 alcohols, we want 1. We don't want a diol. So C is eliminated. The only one that will give us the Markovnikov product without rearrangement is mercury acetate with water followed by sodium borohydride. So D is the right answer. Now let's go over a few things, particularly the mechanism of some of these reactions. So let's react this alkene with H3O plus. So the first thing that's going to happen, the double bond is going to grab a hydrogen, expelling water. Now we're going to add the hydrogen on the less substituted carbon of the double bond. That is on a primary carbon. If we do that, we're going to get a secondary carbocation. Now the secondary carbocation is adjacent to a tertiary carbon, which means that a hydride shift will occur. And so now what we have is a tertiary carbocation, and at this point, water is going to react with it. So now oxygen now has the positive charge. Anytime oxygen has 3 bonds, it's going to have a plus charge. Now what we need to do is use another water molecule to get rid of one of these hydrogen atoms. So the final answer is this particular alcohol, 2-methyl-2-butanol. So as we can see, A is not the right answer. It's not the product that we want. So now let's move on to B. So once we add boron, I'm going to write it like this. Once we add BH3, it's going to react with the alkene, forming this product. The hydrogen is going to go on the more substituted carbon, since hydrogen is more electronegative than boron, and the BH2 group will go on the less substituted carbon. Now, once we add sodium hydroxide with hydrogen peroxide, the net result is that the BH2 group will be replaced with an OH group. And so, this is the product for that reaction. Now let's talk about the reaction in part C, or answer choice C. So first, we're going to react it with a peroxy acid, RCO3H or MCPBA. This will give us an epoxide. Now once we add H3O plus to it, which I'm going to write it out, the oxygen is going to receive a hydrogen from H3O plus. So it's going to be activated. And once H3O plus loses a hydrogen, it converts into water. Now water is going to attack the secondary carbon as opposed to the primary carbon. It turns out that the secondary carbon has more partial charge than the primary carbon, and so that's why water is attracted to it. If you draw the resonance structure of this molecule, which bond should we break? This one or this one? If we break this bond, this will give us a primary carbocation, which is not stable. However, let's say if we break the other bond, this will lead to a more stable resonance structure, which is a secondary carbocation. Now the resonance hybrid is somewhere in between these two structures. So because this carbon has a positive charge in one of the resonance forms, then this one has to have significant partial positive charge, which means water is attracted to that carbon. So it's going to attack the secondary carbon and not the primary one. So we're going to have an OH group on this carbon and a water on the other one. So now all we need to do is use another water molecule to get rid of one of the hydrogens. And so now we have a diol, which occurs with anti-addition. But that's not the product that we're looking for. Now let's focus on the oxymercuration-demercuration reaction. So the alkene will react with mercury acetate. The mercury atom has a lone pair. So the double bond is going to attack the mercury atom, causing one of the acetate groups to be expelled, and the lone pair on the mercury atom will simultaneously react with the double bond. So we're going to get this cyclic mercurinium ion, which looks like this. At this point, mercury has a positive charge. The acetate that was kicked out has a negative charge. Now this carbon, just like before in the other example, has a significant amount of partial positive charge. So the water that's in the reaction will be attracted to it. So it's going to attack from this side, causing this bond to break. And so the mercury atom is going to be on the primary carbon. On the secondary carbon, we have an oxygen. Now we need to remove the hydrogen. We can use water, or better yet, we can use acetate, which is a weak base. So now we have this intermediate. And in the last step, we need to add sodium borohydride. Now the mechanism for this step is not precisely known, but we do know the end result. The end result is that the mercury group will be replaced with a hydrogen. Now, since we don't have to show the hydrogen, we could simply write the final product like this. It's 2-methyl, or rather 3-methyl 2-butanol. And so that's it. Number 21. What is the major product of the reaction shown below? So we have a cycloalkene and a hydroboration oxidation reaction. What do you think the major product is going to be? Well, first, let's look at the regiochemistry. We have a secondary carbon and a tertiary carbon that are part of the double bond system. Now, the hydroboration oxidation reaction is an anti-Markovnikov reaction, which means that the alcohol, the OH group, should be on the less substituted carbon, that is the secondary carbon, since it's an anti-Markovnikov addition reaction. So therefore, C and D will not be the answer. We can eliminate those two. So now let's move on from the regiochemistry and let's analyze the stereochemistry of the reaction. In answer choice A, the methyl group and the alcohol group, they're cis with respect to each other. Here, it's trans. Which one will be the right answer? So what we need to know is that the hydroboration oxidation reaction occurs with syn addition. Now the syn addition, it doesn't have to do with the methyl group because the methyl group was already present in the reaction. The syn addition is between the hydrogen and the OH. So in both cases, the methyl group is in the front. So let's rewrite that. Now we need to put the OH group on the secondary carbon and the hydrogen on the tertiary carbon. So the hydrogen has to be on the back. I'm going to put it in red. We're adding the hydrogen to it. And because the OH group and the hydrogen has to be syn with respect to each other, meaning they have to be on the same side, the OH group has to be in the back. So this reaction is syn addition with respect to the hydrogen and the OH group that are added across the double bond. But it's trans if you compare the OH group and the methyl group. So therefore, the correct answer is answer choice B. So the reaction is syn addition, but it's syn with respect to the H and the OH. It appears to be trans because you don't look at, the hydrogen's not visible here. If you're just looking at the CH3 and the OH, it will be trans, but with respect to the hydrogen and the OH, those two groups should be on the same side. So B is the right answer for this problem. Number 22. What is the major product from the reaction of propene with bromine and water? So propene has 3 carbons and a double bond. And so we're going to react it with Br2 and H2O. Whenever you react an alkene with bromine and water, you're going to get 2 functional groups. You're going to get a bromine atom and you're going to get an OH group. So we can eliminate answer choice D. We're not going to get 2 alcohol groups and we're not going to get 2 bromine atoms. So we're either between A or C. Now it turns out that the more electronegative atom goes in the more substituted carbon, which is the OH group. So the OH group is going to go on the secondary carbon and the bromine is going to go on the primary carbon. So the correct answer is answer choice C. But let's write up a mechanism for this reaction. So the first thing that happens is that the alkene reacts with bromine. So the double bond is going to attack one of the bromine atoms, expelling the other, and at the same time bromine attacks the double bond. So initially bromine has 3 lone pairs, and the bromine that gets attacked is going to use up one of its lone pairs. It's going to form a cyclic intermediate, so it's going to have 2 lone pairs left over, and it's going to have a positive charge. The other bromine atom leaves as bromide, and it's going to have 4 lone pairs and a negative charge. Now we have water in the solution, and because the reaction is dissolved in water, there's a lot more water molecules than bromide ions. So water is going to attack the carbon. Now keep in mind, there's considerable partial positive charge on the secondary carbon, and water, it has an oxygen with a partial negative charge. That oxygen is attracted to this partially positive carbon atom. It's going to attack it from the back, expelling the bromine atom to the other side. And so that's why the oxygen is on the secondary carbon and the bromine is on the primary carbon. It's because of the backside attack. Now the oxygen has a positive charge. There's one more step in this reaction. We need to use another water molecule to get rid of this hydrogen. And so this is going to be the product. It's 1-bromo, 2-propanol. Number 23. Which of the following represents a free radical termination step? Is it going to be A, B, C, or D? So here are some things that you need to know. Let's say if you have a reaction, A plus B turns into C plus D. Anytime you have 2 radicals, one on each side, this is going to be a propagation step if you have a radical on the left and on the right side. Now let's say if you have 2 radicals on the left side, this is going to be a termination step. And if you have 2 radicals on the right side as opposed to the left side, this is an initiation step. And that's a quick and simple technique to distinguish initiation from propagation and from termination. So we're looking for a termination step. So we're looking for the reaction that has 2 radicals on the left side. So answer choice B fits that description. So B is the answer. B is a termination step. Now looking at answer choice A, is it initiation or propagation? Because there's a radical on the left and on the right side, it's a propagation step. The same is true for C. Looking at answer choice D, we have 2 radicals on the right side. So that's an initiation step. And so that's it for this problem. Number 24. What is the major product of the reaction shown below? Is it A, B, C, or D? Now, what you need to know for this type of problem is that when you mix bromine with HV, either UV light or even heat, it's going to be a radical reaction. And whenever you have a halogen reacting with an alkane, this is an alkane, under radical conditions, the bromine is going to replace the most substituted hydrogen. So if you have a primary hydrogen, a secondary hydrogen, and a tertiary hydrogen, it's going to replace the tertiary hydrogen. Now we do have a tertiary carbon. This carbon is tertiary, which means the hydrogen attached to it is tertiary. So bromine is very selective. It's going to go for the tertiary hydrogen. Now if we had chlorine, chlorine is non-selective. It's going to go for any hydrogen that it can get its hand on. It's very reactive. Bromine is less reactive, more selective. So it's going to replace the tertiary hydrogen, which means that C is the right answer. Now let's go over the mechanism of that reaction. So the first thing that happens once we add UV light, the bromine molecule is going to split into 2 parts. Once it gains enough energy, Each bromine atom is going to take one electron and the two electrons in that bond. So we're going to get two bromine radicals. Once we generate the bromine radical in that initiation step, the next step is going to be a propagation step. The bromine radical is going to react with the tertiary hydrogen. So there's two electrons in this bond. One of those electrons will be used to form the bond between H and Br. So that's going to be a side product. The other electron, it's going to stay on the tertiary carbon. So we're going to get a tertiary radical. Now this radical, we can react it with another bromine molecule, since we have plenty of them in the reaction. So one of the electrons in the bond between the two bromine atoms will react with the radical, giving us the product. The other bromine atom is going to take the other electron with it, regenerating the bromine radical. So that is a propagation step, since we have one radical on the left and one on the right. Alternatively, we can get the same product using a termination step. So we could start with the tertiary radical and react it with a bromine radical. So these two would simply combine. And keep in mind, when dealing with radical reactions, typically you're going to be using half arrows, which represents the flow of one electron. A full arrow represents the flow of two electrons. And so those are the different ways that you can get the product. You can get it through a propagation step or even a termination step. The propagation step is more likely because there's a lot more bromine molecules than bromine radicals. The amount of bromine radicals in a solution is very small. So this step will occur more frequently. 25. What is the major product of the reaction shown below? NBS with heat or light works the same way as Br2 with HV. NBS produces radical bromine very slowly when activated with heat or light. So we know that the radical bromine is going to replace a hydrogen that will lead to the most stable radical. In the last example, the reason why it went for the tertiary hydrogen is because of the stability of a tertiary radical. A tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. So what we need to do is figure out which radical is more stable. Looking at answer choice A, the bromine is on this carbon. So let's say if we take away the bromine atom and just simply put a radical there. Will that radical be the most stable radical? If we take away bromine, that's going to be a primary radical. Here, if we take away the bromine, it's a vinylic radical. Vinylic radicals are not stable, so we can eliminate answer choice B. Now, if we put it here, this is going to be a primary radical, but because it's one carbon away from the benzene ring, it's a benzylic radical, which means that it's stabilized by resonance. So C is a good answer, but if you look at D, it's a secondary radical, and because it's one carbon away from the benzene ring, it's also benzylic. It turns out that you can get a mixture of C and D. However, the question wants the major product of the reaction. Because the secondary benzylic radical is more stable than a primary benzylic radical, D is going to be the answer. The major product is D. The minor product is C. You won't get A or B, and if you do get it, it's going to be very, 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 very low. But D is the answer. Number 26. Which acid has the lowest pKa? Is it going to be A, B, C, or D? So how can we find the answer? Well, we can use the trend on a periodic table. As you travel from left to right, acidity increases due to increase in electronegativity. So an OH group is always more acidic than an NH2 group. Keep in mind the typical pKa of an alcohol is 16 to 18, and for an amine, it can be anywhere from 35 to 40. So we're looking for the one with the lowest pKa. We're looking for the strongest acid. Now, which one is more acidic? An amine or a protonated amine? Anytime you add a hydrogen to something, the one with the positive charge is going to be more acidic than a neutral one. A protonated amine has a pKa of about 9 to 10. As you can see, this is much lower than this one. So we can eliminate answer choice B. And the protonated amine is more acidic than the alcohol, so we can get rid of A. Now the protonated alcohol is even more acidic. If OH is more acidic than NH2, then OH plus 2 must be more acidic than NH3 plus. So clearly, the correct answer is C. A protonated alcohol has a pKa somewhere in the negative range. It could be like -2 or -3, but it's very acidic. So this is the answer. Number 27. What is the IUPAC name of the molecule shown below? So first, let's identify the longest chain. So this is going to be carbon 1, 2, 3, 4, 5. We want to count it in that direction so we can get a 2-bromo and the alcohol on 3. If we count it the other direction, we're still going to get the OH on 3, but the bromine will be on 4. And you want to count it in such a way to get the lowest numbers. So we want to count it from the top to the bottom. So there's 5 carbons, and the functional group is an alcohol, so it's pentanol, which means that we can eliminate answer choice D. So everything else is the same, 2-bromo, 3-pentanol. The only thing that's different is the configuration. So we need to determine if we have an R or an S isomer. So let's start with this chiral center, carbon number 2. Now we know that the hydrogen is group number 4. It has the lowest priority. Bromine has the highest. This entire group here is going to be group number 2. And then number 3 is the methyl group. Now what you need to know when dealing with a Fischer projection is that the groups on the sides, in this case the H and the Br, they're in the front. So we need to reverse it. The group above and below, they're in the back. So keep that in mind. Now let's go ahead and count it. So starting from 1, going towards 2, and skipping 4, go from 1 to 2 to 3. If we travel from 1 to 2 to 3, notice that we're rotating in the clockwise direction, which would indicate R. But because H, number 4, is in the front, we need to reverse it. So therefore, this is going counterclockwise, or opposite to the direction of a clock. Therefore, this is the S isomer. So on carbon 2, keep in mind this is carbon 2, this is carbon 3. On carbon 2, we have an S configuration. So therefore, it's not going to be 2R. It has to be 2S. So now the last thing we need to do is find out the other chiral center, if it's R or S. So OH has the highest priority. If you compare this group with this carbon, oxygen has a higher atomic number. Next, if we compare this carbon and this one, there's no difference, so we got to move on to the next group. Bromine has a higher atomic number than the second carbon. So this entire group above, that's going to be, let's call it group number 2. H is number 4, and the ethyl group is number 3. So counting it from 1 to 2 to 3, ignoring 4, this appears to be the R isomer. But we need to reverse it since group number 4, in this case the hydrogen, is in the front. So because it's in the front, we're going to reverse it, and now it's going to be S. So it's 2S and 3S. Therefore, answer choice A is the right answer. Number 28. which reaction will produce a meso product? Go ahead and pause the video, work on this problem. It turns out that the answer is B. Now let's talk about why. Let's go through each one. So here are a few things that you need to know. Let's say if you have a cis alkene plus a syn addition reaction, this will lead to a meso product if the product has a line of symmetry. So that's important. If it doesn't have a line of symmetry, then this will lead to a pair of enantiomers, or potentially even diastereomers, depending on the structure. But let's assume that we do have a line of symmetry for all of these examples. It's going to be a meso product. Now, if we have a cis alkene and let's say an anti-addition reaction, this will lead to a pair of enantiomers. So I'm going to write En for enantiomers. Now, let's say if we have a trans alkene plus, let's say, a syn addition reaction. This will also lead to a pair of enantiomers. And if we have a trans alkene plus an anti-addition reaction, this will lead to a meso product if there's a line of symmetry. So let's consider the first reaction. So here we have a trans alkene, and we're going to react it with potassium permanganate under basic conditions as indicated by the base hydroxide. The temperature is going to be low and the concentration is also low. So this reaction under cold dilute conditions will produce a diol, and this is a syn addition reaction. So the two alcohol groups will be on the same side. So this is going to be the product. But notice that we don't have a line of symmetry. And a trans alkene plus a syn addition reaction would lead to a pair of enantiomers. So the other product that you can draw will look like this. So we get a mixture of two products for this reaction. So that's what we can eliminate answer choice A. Now let's focus on answer choice C. We'll get back to B later. So we have cyclohexene, which you can view it as a cis alkene. And we're going to react it with bromine in carbon tetrachloride. The solvent carbon tetrachloride is inert, so you don't have to worry about it. So we have a cis alkene and an anti-addition reaction. This will lead to a pair of enantiomers. Because it's anti, we're going to put one bromine atom in the front and the other in the back. And as you can see, we do not have a line of symmetry. To draw the enantiomer, simply reverse the chiral centers. And so this is going to be the product of this reaction. Now let's move on to part C. So this time, we're going to react cyclohexene with water under acidic conditions, which is equivalent to H3O+. So the only thing that's going to happen is the alkene will be replaced with an alcohol. And we're going to add one OH group. And as we can see, the carbon that has the OH group is not chiral. The left side is equivalent to the right side. So therefore, we get a single product. And it's not a meso product. We only have one chiral center. We don't have two chiral centers. Now let's talk about answer choice B, which is the answer. So we have a trans alkene and an anti-addition reaction. This will lead to a meso product if there's a line of symmetry. So one chlorine atom, we're going to put it in the front, and the other one, we're going to put it in the back, facing the same direction initially. Now single bonds have free rotation, so we can draw a different conformer. So if we change the conformation by rotating this molecule, the Cl that was in the back is now in the front. And so notice that we do have a line of symmetry, which means that this is a meso product. Number 29, predict the major product of the reaction shown below. So we're reacting 1-butanol with pyridinium chlorochromate. So we have a primary alcohol, and which of these products will be the product of the reaction? Are we going to get a carboxylic acid, an aldehyde, an alkene, or an alkane? Chromium trioxide is an oxidizing agent, so it won't be reduced into an alkane, and we're not going to get an alkene. It turns out that this entire reagent is equivalent to PCC. PCC converts primary alcohols into aldehydes. Now, you don't need to know the mechanism of this reaction, but you simply need to know what this reagent will do. If you have a secondary alcohol, it can oxidize it into a ketone, but know that it will convert a primary alcohol into an aldehyde. So C is the answer. PCC is a mild oxidizing agent. Now, if you have a strong oxidizing agent, it can oxidize the primary alcohol to a carboxylic acid, but PCC won't take it that far. Number 30, which reagent will produce the product shown below? Is it going to be A, hydrogen gas with a platinum catalyst, B, deuterium gas with a palladium catalyst, C, hydrogen gas with palladium mixed with calcium carbonate, or D, sodium metal mixed with liquid ammonia? Which one will convert the alkyne into a transalkene? So we can draw the alkyne like this. So the alkyne has 5 carbon atoms. Let's call this carbon 1, 2, 3, 4, and 5. Now, what's going to happen if we add hydrogen gas with a platinum catalyst? This will simply convert it to a 5-carbon alkane. So we could eliminate answer choice A. Now, what about answer choice B? What if we add deuterium, and what's going to happen if we use a palladium catalyst? Well, this will be reduced to an alkane, but by means of the addition of deuterium atoms instead of hydrogen atoms. To convert the alkyne to an alkene, first we need to add 2 deuterium atoms. Now, it won't stop here. This will continue. To go from the alkene to an alkane, we need to add 2 additional deuterium atoms. So this is going to be the product of answer choice B, which is not the answer that we're looking for. Now, what about mixing hydrogen gas with palladium over calcium carbonate? What's going to happen? This is basically the Lindlar's catalyst. The Lindlar's catalyst is basically hydrogen gas using a palladium catalyst, but it's a deactivated palladium catalyst. It's deactivated once you add an ionic compound to it. Instead of calcium carbonate, you can add barium sulfate. So if you see palladium over barium sulfate, this still represents the Lindlar's catalyst. And what it's going to do is it's going to convert it into a cis alkene as opposed to a transalkene. So this is the product of the Lindlar's catalyst, using this as the reactant. So we can eliminate answer choice C, which means that we know the answer has to be D. If you add sodium metal with liquid ammonia, it's going to give us the trans product. Now, you can use another alkaline metal. It doesn't have to be sodium metal. You could use lithium metal with liquid ammonia. It will lead to the same product. So D is the right answer. Number 31. Which of the following reagents can produce the product shown below? So we have an alkyl halide on the left, and we need to convert it into an alkene. What do we need to do? Feel free to pause the video and work out this problem. So what kind of reaction is this? Whenever you need to go from an alkyl halide into an alkene, you need to know that you're dealing with an elimination reaction. there's two types of elimination reactions that you need to be familiar with. The E1 reaction, not sure what happened there, and the E2 reaction. Now, looking at the product, the E2 reaction can only produce a double bond that's next to where the bromine atom is located. The E2 reaction does not occur with rearrangements, so it can only put the double bond to the left of the carbon-bromine bond or to the right. So therefore, we know it has to be an E1 reaction, because the only way the double bond can form over here is by means of a carbocation rearrangement, and an E2 reaction does not form carbocation intermediates. So which of these reagents will favor an E1 reaction? It helps to know that strong bases favor E2 reactions. Sodium methoxide is a strong base, and potassium terbutoxide is also a strong base. Both of these reagents favor an E2 reaction. Now, B, NaSCH3 with DMF, that favors an SN2 reaction. Whenever you see a sulfur with a negative charge, you need to know that this sulfur is a very, very good nucleophile. So typically it favors SN2 reactions. Plus, DMF is a polar aprotic solvent, which also favors SN2 reactions. So we eliminate B. Now, C, methanol. Methanol is a polar protic solvent, which means that it favors an SN1 and an E1 reaction. However, when you add heat to the mix, heat favors E1 over SN1, even though they both can occur. So these two occur together, but if we want to get the E1 product, C is our best answer. Now let's go over the mechanism for these reactions, because if you understand the mechanism, then you will understand how the product will form. And this will help you for other questions that you may have in the future. So let's start with part A. So let's mix the alkyl halide with sodium methoxide. We don't really need to worry about the sodium part. It's a spectator ion. It's not going to do anything in the reaction. The methoxide ion is what we need to focus on. So the methoxide ion is going to go for the tertiary hydrogen as opposed to the primary hydrogen. It can go for both of these hydrogens, but it prefers to go for the tertiary hydrogen. And the reason why it does so is it forms a more stable alkene. This hydroxide will attack the hydrogen, the carbon-hydrogen bond will break, and the carbon-bromine bond will break as well. Now this all happens in one step, so it's a concerted reaction mechanism. So by abstracting the tertiary hydrogen, we get a more stable alkene. This alkene is trisubstituted. It has 3 R groups that are connected to the 2 carbons of the double bond. Now let's say if we form the other alkene, if we take away the primary hydrogen, this will give us a less stable alkene. So even though it can form, it's the minor product. This is the major product of the reaction. Now let's move on to our next example. Let's react 2-bromo 3,4-dimethyl pentane with NaSCH3. So let's focus on a nucleophile. So we know this is going to be an SN2 reaction. Whenever you have a secondary alkyl halide, a good nucleophile, and a polar aprotic solvent, this is going to favor an SN2 reaction. The nucleophile is going to attack the carbon from the back. Because bromine has a partial negative charge, the carbon that has the bromine has a partial positive charge, which means the sulfur with the negative charge is attracted to it. So once sulfur attacks the carbon, it's going to expel the bromine atom. And SN2 reactions occur with inversion of configuration, so the sulfur is going to be in the back. And so that's going to be the product for this reaction. The side product, the sodium ion, is going to pair up with the bromide ion. These two will form sodium bromide. Next up, we have potassium terbutoxide. Now, in the previous slide, it was written like this. K is expected ion, so let's not worry about that. So let's expand the structure. So we have an oxygen with a negative charge, since K has a plus charge. That oxygen is attached to a carbon with 3 methyl groups. So this is a bulky base. Now, when we use a base that wasn't bulky, like sodium methoxide, the methoxide was a small, non-bulky base. And the non-bulky base, the small one, it went for the tertiary hydrogen. The reason why I went for the tertiary hydrogen is because it leads to the more stable alkene, also known as the Zaitsev product. However, because potassium terbutoxide is so bulky, it's going to have difficulty trying to access the tertiary hydrogen. That tertiary hydrogen is surrounded by a lot of carbon atoms, and so it's hard for the bulky base to grab that hydrogen. Instead, it's going to go for the more accessible primary hydrogen. So what you need to know is that the use of a bulky base will favor the Hofmann product, which is the one that's associated with the less stable alkene, typically the alkene at the end of a chain. So the bulky base is going to grab the primary hydrogen as opposed to the tertiary one. The carbon-hydrogen bond will break, and those electrons will be used to form the double bond, kicking out the leaving group. And so this will give us the Hofmann product. Typically, more than 90% of the product will be in this form. Granted, terbutoxide can form a double bond in that region. It does occur, but the yield is very low. So this is going to be the major product. So now let's work on our last example, the use of methanol with heat. So we're going to focus on the E1 reaction, even though the SN1 reaction can occur. So once we add heat, the first thing that's going to happen is this reaction is going to speed up, and it's going to ionize. The leaving group is going to leave, creating a secondary carbocation. Now, a carbocation rearrangement will occur, and the reason why it's going to occur is because there's a tertiary carbon next to it. So whenever you have a carbocation that's next to a higher substituted carbon, like in this case, we have a secondary carbocation next to a tertiary carbon, there's going to be some sort of rearrangement that's going to occur. The hydride is going to move towards the carbocation. So those two will trade places, and the plus charge will now be on the tertiary carbon. At this point, the E1 elimination can occur, and it's important to understand that methanol is going to act as a base, and it can grab any one of these 3 hydrogen atoms. It can grab the white hydrogen, the green hydrogen, or the blue hydrogen. But it's going to grab the one that will lead to the most stable product, in this case, the Zaitsev product. So it's going to go for the blue hydrogen. We're going to draw all the products, but let's get the main product first. So the methanol molecule is going to act as a base. Bases, they abstract hydrogen atoms. That's what they do. And then double bond is going to form here. So this is going to be the major product. Now the other products that can form, if we take away the green hydrogen, we're going to get this alkene highlighted in green. And if we take away the white hydrogen, we're going to get a double bond here. Now go ahead and determine what type of alkenes we have. Is it monosubstituted, disubstituted, trisubstituted, or tetrasubstituted? Count how many R groups there are on each of these alkenes. So let's start with the white one. Identify the 2 carbon atoms that are part of the double bond, indicated in red. Next, count the number of carbon atoms attached to those red carbon atoms. Here we have 1, 2, and 3. So this is a trisubstituted alkene. It has 3 R groups. The more R groups a double bond has, the more stable it will be. Now, what about the blue double bond? How many R groups does it have? So let's identify the 2 carbon atoms that are part of the double bond. And so this one has 1, 2, 3, 4. There's 4 carbon atoms in total attached to those 2 red carbon atoms. So therefore it's tetrasubstituted. And that's why this is the major product, because it's the most stable alkene. It's the Zaitsev product. It has the most number of R groups. Now let's figure out the last one. So those are the 2 carbon atoms that are double bonded, and there are only 2 carbon atoms attached to those 2 red carbon atoms. So therefore this alkene is disubstituted. So this one is the least stable out of the 3 listed here, and this is the most stable alkene. Number 32. Which reactant will not produce the product shown below? Is it going to be A, B, C, or D? So go ahead, pause the video, and work on this example. It turns out that the correct answer to this problem is answer choice D. This will not produce the product shown below. But we need to go over each one to understand why that's the case. So let's go ahead and do that now. Let's start with answer choice A. Whenever you have an alcohol, and if you react it with an acid, this is going to be an E1 dehydration reaction. Now typically, even though it's sulfuric acid, there's going to be water in the solution. It might be concentrated sulfuric acid, but there's going to be H2O with the sulfuric acid. The first thing that's going to happen, you can represent H2SO4 with H+, if you want to. The oxygen is going to be protonated by the acid. It's going to grab a hydrogen. And the reason why that happens is so that we can turn the OH group into a good leaving group. Right now it's a bad leaving group, but now it's going to leave as water. And so we're going to get a carbocation intermediate, typical of an E1 reaction. Now once we have this plus charge, a rearrangement will occur. There's 2 possible rearrangements. We could have a hydride shift, which will lead to a tertiary carbocation, or we can have a ring expansion, which will lead to a more stable 6-carbon ring. Keep in mind, 6 carbon rings have almost no ring strain. So 6 carbon rings are more stable than 5 carbon rings. So what's going to happen is this bond is going to break, and this carbon atom will be connected to that carbon. So let's call this carbon 1, 2, 3, 4, 5, 6. So now we're going to have a 6-membered ring. So this is going to be carbon 1, 2, 3, 4, 5, and 6. Now carbon 1 has a methyl group attached to it, so let's put that back. Carbon 6 also has a methyl group. Now, which carbon has the positive charge? Carbon 1, it lost a bond, but it gained it back when it connected with 6. Carbon 6 gained a bond, so it lost the positive charge. Carbon 5 lost a bond, but it didn't gain it back. So carbon 5 has the positive charge. Now what I'm going to do is I'm going to turn the molecule. I'm going to rotate it 60 degrees clockwise. So this is the equivalent structure that we have. So keep in mind, the ring expands due to an increase in stability. Anytime a molecule or carbocation, if it could find a way to increase its stability or lower its energy, it's going to do it. It's going to rearrange. Right now we have a secondary carbocation, and it's adjacent to a tertiary carbon. So a hydride shift is going to occur. So now we have a tertiary carbocation. So now at this point, the base is going to come in and remove hydrogen. We can use water, or we can use HSO4 minus. But I'm going to use water. So water is going to act as a weak base, grab a hydrogen, and form the double bond. So as you can see, A is not the answer because it leads to the product that was shown below. Now let's move on to the next example. So let's react it with H2SO4. This time I'm going to draw out sulfuric acid. And it looks like this. So the alcohol is going to grab a hydrogen. As mentioned before, when dealing with an alcohol under acidic conditions, the first thing you need to do is protonate the alcohol. You need to turn it into a good leaving group. Without that, it's not going to be very reactive towards an E1 reaction. So it's going to leave as water, and we're going to get a carbocation intermediate. Now this time, notice that the carbocation is next to a quaternary carbon. When it's next to a tertiary carbon, that is if we have a secondary carbocation or even a primary one, a hydride shift will occur if it's next to a tertiary carbon. But since we're next to a quaternary carbon, a methyl shift will occur. There are no hydrogens on a quaternary carbon. So the methyl is going to migrate towards the plus charge. And so those two, they're going to trade places. So we have a methyl and another methyl on this carbon. And so the plus charge is now on top. Now this carbon has a hydrogen. So now we're going to use a base. Let's use HSO4 minus this time. We can use this to grab the hydrogen and then regenerate the double bond. Or not regenerate, but generate the double bond. So this too will lead to the same product, as we can see here. So that's why we can eliminate answer choice B. Now let's move on to part C. So this is going to be very similar to the last example. Perhaps you should try it. Pause the video and propose a mechanism for the formation of the product that was shown below. So first, we're going to react it with the acid. You can use H plus or H2SO4, as the last two examples illustrated. So the first step under acidic conditions is protonation. The next step, water leaves, and we're going to get a tertiary carbocation. When you have a tertiary carbocation, there's no need for a carbocation rearrangement, unless of course you can expand the ring. But we already have a 6-carbon ring, so this is as stable as we can get, at least for the examples that we've dealt with so far. So now the last thing that we need to do is use either water or HSO4 minus to act as a base and remove the hydrogen. And as you can see, it's going to lead us to the same product. Which is 1,2-dimethyl cyclohexene. Now let's try part D. Let's see why this is the answer, why it will not give us the product that we want. So let's begin by reacting it with the acid. So following protonation, we will have loss of H2O. So we're going to lose an H2O molecule, and this will lead us to a secondary carbocation, which is 1 carbon away from a 5-carbon ring. So a ring expansion will occur. This bond will break, and let's call this carbon 1, 2, 3, 4, 5, 6. So carbon 1 will connect to carbon 6, making a 6-carbon ring. And because carbon 5 lost a bond, it's going to have the positive charge. So this is 1, 2, 3, 4, 5, 6. Carbon 1 doesn't have any methyl groups attached to it. Carbon 6 has an ethyl group, and carbon 5 now has the positive charge. Now we have a secondary carbocation next to a tertiary carbon, so a hydride shift will occur. So now we have a tertiary carbocation. Now there's two products that we can get. If we remove the red hydrogen, we can form a double bond here. If we remove the blue hydrogen, we can get the same answer due to symmetry. And let's say if we remove the green hydrogen, we can get a double bond in that location. So let's take away the blue hydrogen, which is equivalent from removing the red hydrogen. This will give us this product. And if we take away the green hydrogen, we're going to get a different alkene. So those are the two different types of alkenes that we can get in this particular reaction. As you can see, it's not the same as 1,2-dimethyl cyclohexene. So that's why D is the answer. Number 33. Which molecule will undergo solvolysis by an SN1 reaction mechanism the fastest? What you need to know is that a tertiary alkyl halide will react faster than a secondary alkyl halide in an SN1 reaction. And the reason why that happens is because tertiary alkyl halides can form a more stable tertiary carbocation. Tertiary carbocations are more stable than secondary ones. So whichever alkyl halide forms the most stable carbocation intermediate, that's going to be the one that reacts fastest in an SN1 reaction. So let's look at answer choice A. Once the iodide ion leaves, we're going to get a tertiary carbocation. B will produce a secondary carbocation. D will produce a primary one, so we can eliminate these two. And C will also produce a tertiary carbocation. However, notice that it's one carbon away from the double bond. So if the iodide leaves, let's see what's going to happen. We're not just going to get a tertiary carbocation intermediate, but it's going to be allylic as well. And as you recall, whenever you have an allylic carbocation, it's stabilized by resonance. So these two pi electrons can move here. And so the plus charge is shared between two carbon atoms as opposed to one, making this ion more stable than the other ones. So a tertiary allylic carbocation is more stable than a tertiary alkyl, a regular tertiary carbocation. You know what I meant to say. So C is going to be the answer. Number 34. Which reagent will produce the product shown below? Is it going to be A, sodium borohydride, B, dibol, C, lithium aluminum hydride, or D, methyl magnesium bromide? Now, if you haven't seen these reagents in your Orgo 1 class, feel free to skip this problem. It doesn't apply to you. But let's go ahead and work on it. Sodium borohydride is very useful for reducing ketones and aldehydes into alcohols. Sodium borohydride is not strong enough to reduce a carboxylic acid into an alcohol. The way the mechanism works is that the BH4 ion, the hydrogen attached to it has a partial negative charge, and so it's attracted to the carbonyl group. Hydrogen is more electronegative than boron. So what's going to happen is you're going to get an alkoxide, and then following protonation, if you add water or even H3O plus to it, this will grab a hydrogen from the solution, turning it into an alcohol. This is known as a nucleophilic addition reaction. So we can eliminate answer choice A. Diol is very useful for reducing esters and acid chlorides into aldehydes. The mechanism for diol is very similar to that of NABH4. It's not completely the same, but it's similar to it. So that's going to be the end result. So here's what happens. Diol contains an aluminum atom with 2 R groups and a hydrogen. This hydrogen is used to attack the carbonyl-carbon. And you're going to get an intermediate that looks like this. This oxygen reforms the double bond and expels the OCH3 group, producing an aldehyde. And so that's how that mechanism works. Let's eliminate answer choice B. Now, lithium aluminum hydride can reduce the carboxylic acid into the alcohol. In fact, it's a very powerful reducing agent. It can reduce ketones, aldehydes, carboxylic acids, esters, and acid chlorides all to alcohols. So this is the answer. D is not going to work. If you put methyl magnesium bromide, if you react it with a presence with an acid, it's going to act as a strong base. So before it attacks the carbonyl-carbon, it's going to grab a hydrogen. And so this is going to turn into methane. Now let's say if you had excess magnesium bromide. Once all of the hydrogens has been deprotonated, at this point it can attack the carbonyl-carbon. However, it's not going to lead us to the right product because it's going to add a carbon in the process. And we want 7 carbons, not 8 carbons. So either case, D cannot work. So the only answer that will work is lithium aluminum hydride. Number 35. Identify all possible products of the reaction shown below. So go ahead, take a minute and work on this example. So what do you think the answer is going to be? Is it going to be A, B, C, or D? It turns out that the correct answer is answer choice C. And we'll have to go through the mechanism to talk about why. So keep this answer in mind, where the double bond is away from the CH3. It's not next to it. So let's start with our original reaction. So the CH3 was in the front, and the bromine was in the back. So we have a secondary alkyl halide. The carbon that has the bromine is attached to 2 other carbons, so it's secondary. And we're using a strong base. These conditions favor an E2 reaction. Now we could ignore the potassium part, so let's focus on hydroxide. Something you need to know about an E2 reaction is that it doesn't rearrange. The only place that we could form the double bond is here or here. It has to be next to the carbon that has the bromine. We can remove a hydrogen on this carbon or on this carbon. So it's not possible for us to get a double bond in this region because that would involve a rearrangement, and that's only possible for E1 reactions. So therefore, we can eliminate answer choice, I believe it's D or B, one of those, where we had a double bond on next to the CH2 group. Whichever answer that was, we can eliminate it. Now what you need to do is you need to draw the hydrogens that are adjacent to the carbon-bromine bond. So here we have a hydrogen. There's two of them, one in the front and one in the back. Now on this carbon, this methyl group is in the front, which means that the H must be in the back. Now the hydroxide ion is going to act as a strong base. It's going to abstract a proton. Now, the E2 reaction is an anticoplanar reaction, which means that if the bromine is in the back, the hydroxide is going to attack a hydrogen that is opposite to the bromine, meaning it's going to go for the one that's in the front. So therefore, it won't go for this hydrogen because it doesn't have the right configuration. It's not in the right position. It's not anti with respect to the bromine atom, and it won't go for this one. So the only hydrogen that the hydroxide ion will go for is the one that's in front or opposite to the Br. And so that's why we only get one product as opposed to two. And so this is the only product that we're going to get in this reaction. So that's why C is the answer. Number 36. Identify all the products that can be formed in the reaction shown below. So basically this is a continuation of the last problem. So let's draw the hydrogens that are adjacent to the carbon that has the bromine. So we know on this carbon, there's two hydrogens, one in the front and one in the back. And on this methyl group, since it's in the front, that means that the hydrogen is in the back. Now, since this is still an E2 reaction, we know that the base is going to grab a hydrogen that has the opposite configuration to the bromine atom. So since bromine's in the front, the base is going to take away any hydrogen that's in the back. So if it goes for this hydrogen, we're going to get a double bond in this vicinity. So basically, we're going to get this particular product. But it can also go for the other hydrogen that's in the back, which means that we can get this product as well. So we can get both product A and C, which means that D is the right answer. So keep that in mind. For an E2 reaction, the base has to take a hydrogen that's opposite to the leaving group. So if the leaving group is in the front, the H that's in the back will be the one that's subtracted by the strong base. If the leaving group is in the back, then the strong base will remove a hydrogen that's in the front. Number 37. What is the effect on the rate of the reaction shown below if the volume of the solution is tripled? Will the rate increase by a factor of 3 or 9, or will the rate decrease? Well, first, we need to determine what kind of reaction that we have. We don't have an elimination reaction because no double bonds or alkenes were formed. So it has to be a substitution reaction. As we can see, the bromine atom was replaced or substituted with the iodide ion. Now, is this an SN1 or an SN2 reaction? If we look at the substrate, it's a primary alkyl halide, which favors an SN2 reaction. A tertiary alkyl halide favors an SN1 reaction. So we know it's an SN2 reaction, which is a second order nucleophilic substitution reaction. The rate of a second order SN2 reaction depends on the concentration of the nucleophile, which is the iodide ion, and the concentration of the substrate, which is ethyl bromide, or this thing right here. Now, it's first order with respect to each reactant, but it's second order overall if you add the exponents. Now, what effect will increase in the volume have on the concentration? Concentration is moles divided by volume. And so if you increase the volume, the concentration will decrease. Anytime you increase the denominator of a fraction, the value of the whole fraction will go down. And in this case, it's an inverse proportional relationship. If you double the volume, the concentration will be half of its value. If you triple the volume, the concentration will be 1/3 of its value. So how can we use that information to see what effects will be on the rate of the reaction? So if we triple the volume of the solution, the concentration of the iodide ion will decrease by a factor of 3. It's going to be 1/3 of its original value. However, or in addition to that, the concentration of the substrate will also be reduced to 1/3 of its value. So 1/3 times 1/3 equals 1/9. So therefore, the correct answer is answer choice D. The rate will decrease by a factor of 9, which means that it's 1/9 of its original value. So increase in the volume of the solution will decrease the concentration, which will decrease the rate of the reaction. Now, if you can decrease the volume of the solution, you can increase the concentration, which will increase the rate of the reaction. By the way, keep this in mind. For an SN2 reaction, the rate depends both on the concentration of the nucleophile and on the substrate. It's second order overall. For an SN1 reaction, it's first order overall. The rate does not depend on the concentration of the nucleophile. It only depends on the concentration of the substrate, which is the alkyl halide. Number 38. What is the product of the following reaction? So what's going to happen here? So the first thing we need to do is draw the resonance structure of the reactant. The oxygen can use one of its lone pairs to form a double bond, causing the 2 pi bonds in this double bond to move to this carbon. So what that tells us is that that particular carbon is nucleophilic. It's going to have a negative charge. And so this is the resonance structure that we have at this point. So the oxygen bears a positive formal charge. The carbon that has a negative charge is going to grab a hydrogen. So that's where the hydrogen is going to go. Now we still have a double bond here and a plus charge. Now methanol is going to behave as a nucleophile. It's going to attack this carbon. What you need to understand is that this carbon has a partial positive charge and this one has a partial negative charge due to the negative formal charge that we see in the resonance structure. This one is positively charged because it's next to an electronegative atom. When methanol attacks that carbon, the pi bond will break, and then this will give us the product, which looks like this. So we have this intermediate and a hydrogen. All we need to do is remove the hydrogen. We can use another methanol molecule to get the job done. So this will give us the answer B. Number 39. What is the product of the reaction shown below? So based on the previous question, go ahead and pause the video and work on this example. It turns out that the answer is going to be A. Now let's talk about why. So the first thing we're going to do is we're going to draw the resonance structure of this molecule. So as we mentioned before, the oxygen can use one of its lone pairs to form a double bond, causing the carbon to bear a negative charge. So let's use this resonance form and react it. Now we know that methanol is the nucleophile, which means that bromine is the electrophile. So the carbon with the negative charge is going to react with elemental bromine. Bromine wants electrons, so it makes it electrophilic. So the carbon will attack the bromine, expelling a bromide ion. So this is what we currently have at this point. Now keep in mind the oxygen still bears a positive formal charge. And this carbon atom is partially positive. So it's attracted to the oxygen of the methanol molecule. So methanol is going to behave as a nucleophile. It's going to attack this carbon and break the pi bond. So oxygen once again now has 2 lone pairs. Now whenever oxygen has 3 bonds, it's going to have a positive charge. So in the next step, all we need is another methanol molecule to remove the hydrogen, and this will give us the answer. So therefore, we can see that answer choice A is indeed the answer. The OCH3 group is on the carbon that is closest to the oxygen. The electrophile, which was bromine, it went on the carbon that's further away from the oxygen, but the nucleophile went on the carbon that's closest to the oxygen. So A is the right answer. Number 40. Which of the following reagents will produce the product shown below? So how can we convert an alkene into a transdiol? So first, let's start with answer choice A. What's going to happen if we use osmium tetroxide? If we use it followed by sodium bisulfite, or even if we use H2O2 in the second step, this reaction is a Synedish reaction. We're going to get a cis diol with the OH groups on the same side. So keep this in mind, this is a meso product due to the symmetry. So we get only one product. So we can eliminate answer choice A. Now what about using potassium permanganate under cold dilute basic conditions? It turns out that it's going to do the same thing as answer choice A. We're going to get the cis diol. So let's eliminate this one. Now what about C? Using diiodomethane with zinc and copper. So that reaction is known as the Simmons-Smith reaction, and it produces a cyclopropane ring, which will be added right across the double bond. So basically all we're doing is we're adding a CH2 group across the double bond. The zinc will pair up with the iodine, so you're going to get zinc iodide as a side product. Now what about D? By elimination, D has to be the answer. Once you add a peroxy acid, which is basically MCPBA, MCPBA is a type of peroxy acid. This will create an epoxide. Once you add H3O+, the epoxide opens into two alcohols. So let's go over the reaction. So in the first step, protonation occurs. So now we're going to have a positive charge on the oxygen. So once H3O+ loses a hydrogen, it turns into a base, or nucleophile, which is water. But in this part, water is going to act as a nucleophile, since it's going to attack a carbon atom. And it attacks from the back, which means it pushes the other OH group from the front, or to the front. And so that's why we get a transdiol. The reaction is anti-addition because the water attacks from the back, pushing the oxygen on the other side in the front. But we're not finished though. So right now we have OH2, and we have the other OH here. So we need another water molecule to take off this excess hydrogen atom that we have. So then this is going to be the product. So we get the trans isomer, which is not a single product, but it's a pair of enantiomers. So there's two products. We get this one, and we get the enantiomer as well. As you can see, we do not have a line of symmetry, so it's not a meso product. This side is different from the other side. Number 41. Which of the following reagents will convert one butene into one bromobutane? Well, let's go through each one. So let's react the alkene with elemental bromine. The double bond is going to attack one of the bromine atoms, expelling the other, and bromine will simultaneously react with the double bond, creating this cyclic intermediate. In the next step, the other bromide ion is going to attack from the back. And so we're going to get 2 bromine atoms across the double bond. So this is 1,2-dibromobutane. It's not 1-bromobutane. So therefore, we can eliminate answer choice A. So this is not going to work. Now what about answer choice B? If we mix an alkene with NBS, what's going to happen? Now this is going to be a radical reaction, but this particular reaction, it doesn't react with the double bond. Instead, it replaces a hydrogen that's 1 carbon away from the double bond. Initially, the hydrogen gets replaced with a radical. And this radical can move by means of resonance. So here's the other resonance structure that we can draw. So there are 2 possible products that we can get. The bromine atom, or the bromine radical, can react with this radical or this one, leading to these 2 products. None of these products represent 1-bromobutane, so B is not the answer either. Now let's try part D before we try part C. What's going to happen if we react 1-butene with HBr? The double bond, being a nucleophile, is going to go for the electrophilic hydrogen, expelling the bromide ion. And we're going to put the hydrogen atom on the less substituted carbon of the double bond so that we can get a more stable secondary carbocation. And then in the next step, the bromide ion is going to combine with the carbocation. So this reaction will generate 2-bromobutane as opposed to 1-bromobutane. So this is a Markovnikov addition reaction because the bromine atom went on the more substituted carbon. Now, when you use HBr with peroxides, this is going to be an anti-Markovnikov reaction. The peroxide can be in the form of an organic peroxide, ROOR, or hydrogen peroxide, which is H2O2. Hydrogen peroxide looks like this. This is how you draw it. So in this case, the bromine atom is going to go on the primary carbon as opposed to the secondary carbon. And so this reaction will produce 1-bromobutane. So C is the answer. Number 42. What is the product formed in a reaction shown below? So we have an alkyne, particularly a terminal alkyne, and we're going to mix it with water, sulfuric acid, and mercury sulfate. What you need to know is that this reaction occurs with Markovnikov regiochemistry, which means that the group that's going to be added is going to go on the more substituted carbon of the triple bond. So it's not going to go on the primary carbon, it's going to go on the secondary carbon, which means we could eliminate answer choice B and answer choice D. B is a primary alcohol, D is an aldehyde. So what's going to happen initially is we're going to get an enol. So we're going to have a double bond, but an OH on the secondary carbon. Now the enol form is not very stable. It's going to tautomerize into the ketone form. And so this is going to be the final product, which is acetone. This structure correlates to answer choice C, CH3COCH3. Number 43. Which alcohol will undergo dehydration most rapidly with H2SO4? So is it going to be A, B, C, or D? Well, what you need to know is that alcohol dehydration with H2SO4 is typically an E1 reaction. And as a result, tertiary alcohols work better than secondary alcohols. If you have a primary alcohol, it won't work very well for an E1 reaction. In fact, the mechanism will be E2 in that case. but the tertiary alcohol will react most rapidly with H2SO4. So A is a primary alcohol, B is a methyl alcohol. If we draw C, we have 3 carbons with an OH in the middle, and so the OH is on the secondary carbon, which means it's a secondary alcohol. D has 3 methyl groups, a carbon and an OH. So answer choice D represents a tertiary alcohol. D is going to be the answer. Number 44. Which is the strongest nucleophile in the presence of a solvent such as water? So what type of solvent is water? Water is a protic solvent. Anything that has an OH group or an NH group attached to it is a protic solvent. Now, what you need to know is that nucleophilic strength increases towards the left across the periodic table and down whenever the nucleophile is dissolved in a protic solvent. So there's 3 elements that we have here: oxygen, fluorine, and sulfur. Fluorine is to the right of oxygen, and sulfur is below it. So as you travel towards the left, the nucleophilic strength increases, which means that oxygen is a stronger nucleophile than fluorine. And as you go down, nucleophilic strength increases in the protic solvent. So sulfur is more nucleophilic than oxygen. Okay, yeah, something is wrong with this computer. So using this information, what answers can we eliminate? So we know that we can eliminate C. We said that oxygen is more nucleophilic than fluorine. And we can eliminate answer choice B because sulfur is more nucleophilic than oxygen. But what about between A and D? If we consider answer choice A, we can see that the negative charge can be delocalized into the ring. So that ion is stabilized by resonance. If it's stabilized by resonance, it means that it's more stable than D. And when a base is more stable, that means this is the weaker base. So D is the stronger base. The stronger base is typically the stronger nucleophile. So D is going to be the right answer. So if you're looking for the strongest nucleophile, you want to use the trend first. If it's in a protic solvent, nucleophilic strength increases towards the left and as you go down. Now, also, the stronger nucleophile will not be stabilized by resonance. If you have any resonant structures, it makes the nucleophile weaker. The negative charge can be shared about many atoms, so that's going to be a weaker base, which correlates to a weaker nucleophile. Number 45. Which is the strongest nucleophile in the presence of a solvent such as acetonitrile? Acetonitrile, is it a polar protic solvent or a polar aprotic solvent? Does it have any OH or NH groups? Does it have hydrogen bonds? Well, let's find out. When you hear the word aceto, that means that there's 2 carbons, and nitrile means that we have a CN group. So that is acetonitrile. There are no hydrogen bonds in this molecule, which makes it a polar aprotic solvent. Nucleophilic strength in a polar aprotic solvent increases towards the left, just as a polar protic solvent, but instead of going down like a polar protic solvent, it goes up instead. Now, on the periodic table, we have elements such as fluorine, chlorine, bromine, and iodine in this order. Now, based on this trend, fluoride is the strongest nucleophile in a polar aprotic solvent. Now, if we had a protic solvent like water or methanol or ethanol, iodide will be the strongest nucleophile. But in a polar aprotic solvent, it's fluoride. Number 46. Which of the following reagents is needed to produce 2-hexyne as shown below? So what do we need to do here? How can we figure this out? The first thing that we should look at is the number of carbons. The reactant has 3 carbons, the product has 6 carbons, which means we need 3 more to get to 6. So we can eliminate answer choice B because it has an alkyl halide with 2 carbons, and we can get rid of D because it doesn't have 3. This is 1-bromobutane, it has 4 carbons. So that means that the answer is either A or C. So now let's work out the mechanism for A and C, and let's see which one's going to work. NaNH2 is a strong base. The purpose of that is to remove the hydrogen, making the carbon that is part of the triple bond nucleophilic. And also, it's a strong base as well. Now, answer choice A has a primary alkyl halide. Answer choice B has a secondary alkyl halide. Whenever you have a carbon with a triple bond, when it has a negative charge, you need to know that it's a very powerful nucleophile and it's a strong base. If you have a primary alkyl halide, it's going to favor the SN2 reaction. But if you have a secondary alkyl halide, then it's going to favor the E2 reaction because this works as a strong base. The same is true, let's say, if you have hydroxide. If you mix hydroxide with a primary alkyl halide, the predominant mechanism is the SN2 mechanism. But if you mix hydroxide with a secondary alkyl halide, the major mechanism will be the E2 pathway. So let's react it with propyl bromide. So this is going to be an SN2 reaction. This is going to attack the carbon that has the bromine, and it's going to expel it. And so that's going to give us the product. All you need to do is write this part backwards, starting with the CH2. This carbon is connected to the CH2 carbon. So we can see that answer choice A is the correct answer. But let's go over the mechanism for answer choice B. So the first step is the same. We're going to take off the hydrogen on the carbon that has a triple bond. So we're going to get a negative charge after using NaNH2. But here's where it differs. So I'm going to convert this compound into a line structure. So basically we have 3 carbons with a bromine atom on a secondary carbon. So this is going to be an elimination reaction. This carbon is going to act as a base. It's going to grab the adjacent hydrogen, forming a double bond, expelling the leaving group. Now because this happens in one single step, this is known as the concerted reaction mechanism. The SN2 reaction and the E2 reaction are concerted reaction mechanisms. Because they occur in a single step, no carbocation intermediates are formed. So this is going to be one of the products, and this is going to have the hydrogen that it lost. So it's just going to be this molecule again. So as we can see, we don't have a 6-carbon alkyne. We don't have 2-hexyne. So that's why answer choice B is not the answer. Number 47. Which carbocation will be least likely to undergo a rearrangement reaction? Well, let's solve this by elimination. Let's determine the ones that will undergo a rearrangement reaction, and then we can see which one is least likely to do so. So the carbocations that will undergo a rearrangement reaction are those that are next to a more substituted carbon. So if we look at answer choice A, we have a secondary carbocation. And this carbon is attached to 2 other carbons. And it's adjacent to a quaternary carbon, which means that it can undergo a methyl shift. So this one will rearrange. Now if we look at answer choice B, we have a primary carbocation next to a tertiary carbon. So that too will undergo a rearrangement reaction, and it's going to be by means of a hydride shift as opposed to a methyl shift. So we can eliminate answer choice B. Now if we look at answer choice C, we have a tertiary carbon or a tertiary carbocation, and there's no higher substituted carbon next to it. The adjacent carbons are primary and one is secondary. So C will be least likely to undergo a rearrangement reaction. So the answer is C. If we look at answer choice D, we have a secondary carbocation, which is adjacent to a tertiary carbon. So this will rearrange by means of a hydride shift. So D is eliminated. C is the best answer. Number 48. What is the major product of the reaction shown below? So we have an alcohol. It's a secondary alcohol, and we're using sulfuric acid. So this is going to be an E1 dehydration reaction, which means that rearrangements are possible. So typically, the major product is going to be the most stable alkene. So looking at these answers, which alkene is the most stable? Well, let's start with A. How many R groups are attached to that double bond? So how many other carbon atoms are connected to the green carbon atoms? So here we only have a total of 2. So this double bond has 2 R groups, which means that it's disubstituted. Looking at answer choice B, this alkene only has 1 R group. So it's a monosubstituted alkene. It's the least stable alkene, so the answer is not going to be B. If we look at C, how many R groups are attached to that double bond? Is it a monosubstituted alkene? Is it disubstituted, trisubstituted, or is it tetrasubstituted? There's a total of 4 carbons attached to the 2 double bonded green carbon atoms. So it's a tetrasubstituted alkene. This is going to be the answer. It's the most stable alkene that we have here. Looking at answer choice D, it only has 2 R groups. So it's a disubstituted alkene. Now let's go over the mechanism of this reaction. So the first step is that the alcohol is going to receive a hydrogen. So it's going to turn into a good leaving group, and then it's going to leave as water. So now we have a secondary carbocation, which is adjacent to a quaternary carbon. And so a methyl shift is about to occur. So here's the methyl, and the plus charge is now on a tertiary carbon. And so the last step is the removal of a hydrogen. Let's use water as a base, which could take off this hydrogen and form a double bond. So this will give us the major product, which is a tetrasubstituted alkene. So this is the answer. Number 49. Which solvent is best suited for an SN1 reaction? What you need to know is that SN1 reactions work well with polar protic solvents. An SN2 reaction works good with polar aprotic solvent. So we need to identify which of these solvents is a polar protic solvent. Which one has hydrogen bonds? Let's start with A, DMSO, dimethyl sulfoxide. It looks like this. Dimethyl sulfoxide is very similar to acetone. Instead, there's a sulfur in the middle as opposed to a carbon. So as you can see, there's no OH or NH bond, so this is a polar aprotic solvent. DMSO works well for an SN2 reaction, not an SN1 reaction. Acetone is very similar to DMSO. This is acetone, which is also a polar aprotic solvent, so that's good for an SN2 reaction. 12 crown 4 ether. So basically, this is a cyclic ether made up of 4 oxygen atoms, 8 carbon atoms, so there's a total of 12 atoms in the structure. And this ether is very good for solvating the lithium ion. The 15 crown 5 ether works well for solvating the sodium ion, and the 18 crown 6 ether is good for the larger potassium ion. What it does is it solvates the cation, allowing the nucleophile, like a fluoride ion, to be free to attack the substrate or the alkyl halide. So this is good for an SN2 reaction. Ethanol is a protic solvent due to the hydrogen bonds found in an OH group. So this is good for an SN1 reaction. So C is the answer. Number 50. Which alkyl halide will react most rapidly with sodium methoxide and methanol? So if we take a look at all of the alkyl halides that we see, all of them are primary. And sodium methoxide is both a strong nucleophile and a strong base. A small but strong unhindered base with a primary alkyl halide will favor an SN2 reaction. So we need to know which of these alkyl halides work best in an SN2 reaction. They're all primary, so the only difference is the leaving group. So here's fluoride, chloride, bromide, and iodide on a periodic table. Leaving group strength increases as you go down. Iodide is the best leaving group. The reason why it's the best leaving group is because it's the most stable. For one reason, it's a weaker base than fluoride, and two, iodide is a lot bigger than fluoride. Because iodide is so big, it has more room to stabilize the negative charge. The negative charge is spread over a larger volume. In the case of fluoride, that negative charge is concentrated over a smaller volume, so it's not as stable, which means fluoride is a stronger base than iodide. But iodide is the better leaving group, so therefore D is the best answer. It's going to react most rapidly with sodium methoxide and methanol. 51. What is the product of the reaction shown below? Whenever you see B2D6, it's basically a dimer of two BD3 molecules, and BD3 works the same way as BH3. This reaction with BH3 and hydrogen peroxide and sodium hydroxide, it's basically a syn addition of water. The H and the OH that's added has to be on the same side. But since we don't have BH3, we have BD3. The deuterium atom and the OH added has to be on the same side. So those are the two groups that we're adding. Now, this reaction occurs with Markovnikov anti-regiochemistry, which means that the OH, the more electronegative atom, is going to go on the less substituted carbon, since it's anti-Markovnikov. So it's going to go on the secondary carbon of the double bond. So therefore, we can eliminate answer choice C and D. It's not supposed to be on the tertiary carbon. Now, the syn addition, as you mentioned before, is with respect with the OH and the deuterium atom. Those two have to be on the same side. We can eliminate answer choice D because they're on opposite sides. So therefore, A has to be the answer. The two groups that are added, the deuterium and the OH, they have to be cis with respect to each other. It's a syn addition reaction. Number 52. What is the IUPAC name for the compound shown below? So first, we need to identify the longest chain. 1, 2, 3, 4, 5, 6. So that's a hexane chain. Or if we count it this way, 1, 2, 3, 4, 5, 6, 7. So 7 is the number of carbons in the longest chain. So therefore, it's not hexanol, so C is eliminated. Now, in which direction should we count? If we count from left to right, we're going to have a methyl on 3, a bromo on 4, and an alcohol on 6. So the numbers will be 3, 4, 6. If we count it from right to left, we have an OH on 2, a bromine on 4, a methyl on 5. So clearly going from right to left gives us the lower numbers, and we want to give priority to the alcohol. So we don't want 6-heptanol, we want 2-heptanol. So we have a 4-bromo, a 5-methyl group, and 2-heptanol. Answer choice A and D have these values. The only difference is which one comes first, bromo or methyl. So we got to put it in alphabetical order. Therefore, the correct answer is answer choice A. It's 4-bromo, 5-methyl, 2-heptanol. Number 53. Which of the following is the major resonance contributor? So all of these structures are resonance structures of each other. But one of them is going to be the most stable. Which one is that? So the real question is, where should the negative charge be located? Is it better to place a negative charge on a nitrogen atom, on an oxygen atom, on a carbon atom, or on a sulfur atom? What would you say? So first, let's go to the periodic table. We have carbon, nitrogen, oxygen, fluorine, and sulfur. Now, it turns out that it's better to place a negative charge on an oxygen atom than a nitrogen atom because oxygen is more electronegative. So we can eliminate carbon from the mix. It's not good to put a negative charge on carbon. And so we could take out nitrogen. But now, what about between oxygen and sulfur? Is it better to place a negative charge on oxygen or on sulfur? It turns out that it's better to place the negative charge on the bigger atom. Sulfur is bigger than oxygen, so it has more volume to stabilize the negative charge. Therefore, D is the best answer. It's the major resonance contributor. Number 54. Which molecule is not capable of cis-trans isomerism? Is it A, B, C, or D? Well, let's start with D. D can show it. So let's focus on a double bond. So these are the two carbon atoms that has a double bond. Each of those carbon atoms have a hydrogen and a methyl group. So as we can see, this is the cis isomer. And to draw the trans isomer, all we need to do is flip one side of the molecule. We just got to switch these two groups here, the hydrogen and the CH3. If we switch them, this will give us the trans isomer. So therefore, that molecule can show cis and trans isomerism. So we can eliminate answer choice B. I mean, not B, but D. Let's look at answer choice B. We have 1,2-dimethyl cyclohexane. The two methyl groups can be placed on the front side, which is the cis isomer, or we could put one in the front and one in the back, and that would represent the trans isomer. So this molecule can show cis and trans isomerism. So we can eliminate answer choice B. Now let's move on to part A. So let's focus on this double bond. Let's draw that first. Now we have a methyl group and we have a ring. So there's two hydrogens here. So this is the cis isomer. To draw the trans isomer, we can flip the methyl and the hydrogen. And it's going to look like this. So that's the trans isomer. So that molecule can show cis-trans isomerism. So by elimination, the correct answer has to be answer choice C. But let's see why it can show it. Let's draw the double bond first. So we have two carbon atoms separated by a double bond. Now, this carbon atom has a methyl group and a hydrogen. And then this carbon atom has two hydrogens. Notice that if we flip these two groups, we're going to get the same molecule. So whenever you have a double bond where one of the double bonded carbon atoms has two of the same types of groups attached to it, it will not show cis or trans isomerism. Because if you flip these two, it's going to lead to the same compound. And so the answer is C. This molecule doesn't have cis or trans isomers. Number 1. Which of the following statements is false? Now, before we answer the question, let's go ahead and analyze the chiral centers. Let's start with compound 1. Let's find the configuration of this chiral center. Do you think it's R or is it S? Well, bromine is going to be group number 1. It has the highest priority. This whole thing is going to be group number 2. H is number 4 and methyl is 3. Now keep in mind, in the Fisher projection, the groups on the side are treated as if they were in the back. So if we count it from 1 to 2 to 3, ignoring 4, it appears to be the R isomer. But because H is in the front, we need to reverse it, and so we get the S isomer. So this is S. Now let's do the same for this second chiral center. Bromine is number 1, the group above is number 2, the methyl is 3, H is 4. So going from 1 towards 2 and then towards 3, ignoring 4, this appears to be S. It's going counterclockwise, but because H is in the front, we need to reverse it, making it R. So we have the configuration SR. So now that we have the configuration of compound 1, we could find the configurations for every other compound. Looking at compound 2, the bromine has been switched from right to left. It's on the left side, so the configuration must change. It's R. And then this chiral center also changed. The bromine's on the left as well, so this is going to change from S to R. R to S. Now let's compare compound 1 and compound 3. So if this is the S isomer, this must also be the S isomer too, because the bromine atom is still on the right side. Now this is the R isomer when bromine's on the right for the second chiral center, but here it's on the left, so it has to reverse to S. As you can see, these two are the same, so they're both S. Now let's compare compound 1 and compound 4. So for the first chiral center, the bromine's on the right, and for the second one, for compound 4, the first chiral center, bromine's on the left. So it has to change from S to R. Much like this one. Those two are the same. Now these two, they're in the same direction. Bromine is facing towards the right, so they're both R. So now let's look at the answer choices. Compounds 1 and 2 are meso compounds. Is that true or false? Well, they have the opposite configuration. Compound 1 is SR, compound 2 is RS. And we do have a line of symmetry. As we can see, the methyl groups are symmetrical about the yellow line. The hydrogen is symmetrical about it. And the bromine atom is also symmetrical about it. So therefore, compounds 1 and 2 are meso compounds. So that's a true statement, which means that it's not the answer we're looking for. We're looking for the false statement. Now what about B? 1 and 3, are they diastereomers? Well, let's find out. Looking at the chiral centers for compound 1, it's SR. For compound 3, it's SS. Whenever some of the chiral centers change, but not all, what you have is a pair of diastereomers. As we can see, the first chiral center stayed the same, but the second one changed, which means that B does represent a pair of diastereomers, so that's a true statement. So B is eliminated. Now what about answer choice C? Compounds 3 and 4, are they enantiomers? Well, all the chiral centers change from SS to RR. And second, we don't have symmetry across this line. Hydrogen and bromine are not the same. The methyls are the same. And on this side, there's a lack of symmetry. So because all chiral centers change, and we do not have a line of symmetry, these two compounds are indeed enantiomers. So that's a true statement. So the answer must be D. Looking at 2 and 3, in order for those two compounds to be constitutional isomers, they have to have the same chemical formula, but they must differ in connectivity. And they indeed have the same chemical formula. We have 2 methyl groups, 2 bromine atoms, 2 hydrogen atoms, and so forth. But is the connectivity different? Well, let's find out. So this is carbon 1, 2, 3, and 4. We can count the other way if we want to. So looking at compound 3, let's call this 1, 2, 3, and 4. Carbon 2 and carbon 3 has a bromine atom and has a hydrogen. The connectivity is the same, it's not different, which means that D is a false statement. These are not constitutional isomers. They are stereoisomers. They have the same connectivity, but they differ in their spatial arrangement. As we can see, here the chiral center hasn't changed. It's S, but here it did change. It went from R to S. So 2 and 3 are diastereomers. Diastereomers and enantiomers are types of stereoisomers. They have the same connectivity, but they differ in the way the atoms are arranged in space. Constitutional isomers, they differ in their connectivity. The atoms are just connected differently. So D is the answer. It's the false statement. Number 56. What is the major product of the reaction shown below? So what we have is a tertiary alkyl halide, and we have a strong base, sodium ethoxide. The use of a strong base favors an E2 reaction, which means that we need to create a new double bond. And that's what E2 reactions do. They create alkenes. So we can eliminate B. B is a substitution product. And It's just not going to happen. In the presence of a strong base and a tertiary alkyl halide, we're not going to get an SN1 reaction or an SN2 reaction. So we're going to get an E2 reaction. The question is, where should we put the double bond? That is the real question. So we can get rid of the green hydrogen, we can remove the red hydrogen, or we can get rid of the blue hydrogen. If we get rid of the blue hydrogen, we could form the double bond here. If we get rid of the red hydrogen, we could form it here. And if we get rid of a green hydrogen, we could form it there. We could form it anywhere around the carbon that has the bromine. However, which one is going to be the most stable one? Looking at the products, the most stable alkene form is the one that is conjugated. Answer choice A doesn't have a conjugate alkene. We do have a trisubstitute alkene. If you look at the two double bonded carbon atoms, you can see that it has 3 R groups. So that is basically a trisubstitute alkene, which is fairly stable. If you look at answer choice D, it's not conjugated and it's disubstituted. There's only 2 carbon atoms bonded to the 2 double bonded carbon atoms. But answer choice C is a trisubstituted alkene. We have 3 R groups, plus the double bond is conjugated to the other one. Whenever you see an alternating double, single, double bond pattern, it's conjugated. And it's stabilized by resonance. So conjugated double bonds are more stable than isolated double bonds. So C is the right answer. Number 57, which reagent is necessary to complete the reaction shown below? So let's start with answer choice A. What's going to happen if we add HBr? Well, once we add the acid, the alcohol is going to grab a proton, and it's going to turn into a good leaving group. So this is going to be OH2+. Now this reaction is going to favor an SN1 mechanism as opposed to an SN2 mechanism, because the solution is acidic due to HBr, and a polar protic solvent favors SN1 over SN2 reactions. If you recall, SN2 reactions prefer a polar aprotic solvent. So whenever you have a secondary substrate, the solvent could be the difference between an SN1 or SN2 reaction. So now that we know it's an SN1 reaction, we know we're going to get a carbocation intermediate. Now the bromide ion could attack from either side. It could attack from the front or the back, leading to a racemic mixture of 2 products. So we can get retention and we can get inversion. Now in the second step, we're going to add sodium cyanide with DMSO. So we have a secondary alkyl halide. Dimethyl sulfoxide is a polar aprotic solvent, so this is going to be an SN2 reaction, which means that we're going to get inversion of configuration. So when the cyanide attacks from the back, expelling the bromine atom, this will produce the inverted product. And when it reacts with this one, we're going to get the other product as well. So because we started with 2 different enantiomers, or 2 different stereoisomers, we're going to get a mixture of products. So therefore, this reaction is not the best reaction to produce this product. We wanted to get it 100%, but instead we have a mixture. So answer choice A can give us this product, just not in good yield. So let's see if there's a better option. Let's look at part C. So let's start with the alcohol. And let's react with HCN. Now HCN is a weak acid, so it won't react as fast as HBr, which is a strong acid. So to speed the reaction up, we're going to add heat. So this is going to be an SN1 reaction because the solution is acidic. So in the first step, the alcohol will grab a hydrogen. And then just like before, water is going to leave. So this is going to give us a carbocation. And then the CN group could attack the carbocation. It could attack it from the back or the front. So once again, this will give us a mixture of stereoisomers. We're going to get retention relative to the original product, and we're going to get the inverted product. So answer choice C doesn't give us the retention product in good yield. It gives us a mixture, which is the same as answer choice A. So there's no difference between A and C in terms of the final outcome. So let's eliminate A and C. Now let's start with answer choice B. So what's going to happen if we use PBr3? PBr3 will convert the OH group into a Br. It's going to replace the OH group with a halide. And this reaction works with inversion of configuration. It's an SN2 reaction. Now once we add sodium cyanide and acetone, that's another SN2 reaction. And so we're going to have a double inversion. A double inversion is basically retention. So we're going to get the product in good yield. We're not going to get a mixture of stereoisomers. We're going to get a single product. And this is the answer. That's what we want. Now let's go over the mechanism for the first step of the reaction. Let's see how PBr3 converts an alcohol into an alkyl halide. So in PBr3, the phosphorus has 3 bromine atoms and a lone pair. Bromine is more electronegative than phosphorus, so bromine has a partial negative charge, phosphorus has a partial positive charge, and oxygen is partially negative. So oxygen is attracted to the phosphorus atom. It's going to attack it, and it's going to expel a bromine atom. Whenever oxygen has 3 bonds, it has a plus charge, which means that it's a good leaving group. So the bromide ion, what it's going to do is it's going to attack it from the back. And due to the backside attack, this is an SN2 reaction, and that's why we get inversion in the first step. And we know the second step is another SN2 reaction, so that's going to be another inversion. A double inversion leads to retention. Now let's move on to answer choice D. So if C is the answer, D can't be the answer. So first we're going to react the alcohol with TSCl. We're going to lose HCl, so we could just get rid of it, and we're going to get an OTS group. This reaction works with retention. So the configuration stays the same. If the OH is in the front, the OTS group is going to be in the front. HCl leaves as a byproduct. It leaves as a gas. Now once we add sodium cyanide to it, this is going to be an inversion. It's an SN2 reaction. So we only get the inverted product, which is not what we want. We want the retention product. So that's why D is not the answer. Now, if you want to know what TSCl is, so let's say if you have an alcohol. TSCl is basically a chlorine with a benzene ring. And typically, well, actually, there's a benzene ring, but there's a sulfur first. You have a sulfur atom with 2 double bonded oxygen atoms, then a benzene ring. And then there's like a R group. Sometimes the R group could be a methyl group, sometimes it could be something else, but that can vary. The important part is this portion of the molecule. So what happens is the alcohol attacks the sulfur, and eventually it kicks out the chlorine atom. So you get this product, and then the chloride takes away the hydrogen. Once the chloride takes away the hydrogen, it leaves as HCl. So the formation of a gas drives the reaction forward. It's not reversible. Once HCl is gone, that's it. It doesn't go backwards. And so we get this good product. The purpose of this is it turns the OH group, which is a poor leaving group, into a good leaving group. It's very easy to kick off this group because the oxygen with a negative charge that forms is stabilized by resonance due to these other oxygens that are present. So this product at the right, this is basically ROTS, and this is TSCl, just in case you were wondering. Number 58, which carbocation is most stable? Is it going to be A, B, C, or D? So we know that tertiary carbocations are more stable than secondary ones, which are more stable than primary carbocations. The reason being is methyl groups are electron donating groups. Electron donating groups can stabilize a carbon with a positive charge, which wants electrons. And on the other hand, electron withdrawn groups can destabilize it. Answer choice D has an electron withdrawn group. The carbonyl group can pull electron density away from the carbon chain. So the oxygen can acquire a negative charge, put in a positive charge on this carbon, which is next to another carbocation. Having two positive charges next to each other is not good. So electron withdrawn groups destabilizes a carbocation. So D is the least stable. If we look at everything else, all the other structures are stabilized by resonance. If you look at answer choice C, the alkene, the double bond, can donate a pair of electrons towards the carbocation, producing a resonance structure that looks like this. So C has two resonance structures. The plus charge is shared between two carbon atoms. But answer choice B is better because the plus charge can be shared between three carbon atoms. We can move the double bond here, producing this particular resonance form. And we can move it here, producing another resonance form. So the carbocation in answer choice B is more stable than the one in C because the plus charge can be shared between three carbon atoms as opposed to two. The more atoms in which you can spread out the charge, the more stable it's going to be. If you can spread out the charge over a larger volume, then the charge will be more stable. It turns out A is the best answer. Now let's talk about why. Not only does it have more resonance forms, but instead of putting the plus charge on a carbon, we could put it on a nitrogen atom. This lone pair can be used to form a double bond, pushing this double bond here. Even though there's many resonance forms, I'm going to draw the most important one. So now the double bond is between the carbon and the nitrogen. We have another double bond here, and there's a plus charge, and we have a hydrogen. Well, that plus charge is no longer on the carbon. I take that back. It's on the nitrogen now. So this compound, that ion, is actually a lot more stable because it's better to put the positive charge on the nitrogen as opposed to the carbon because nitrogen is more electronegative than carbon. Also, notice that the ring has three conjugated double bonds as opposed to two. This ring looks like a benzene ring. It's an aromatic ring, which makes it even more stable. So answer choice A is the best answer. Number 59. Which carb anion is most stable? So to review, we said that tertiary carbocations are more stable than secondary ones, which are more stable than primary carbocations. Now for carb anions, where you'll see a lone pair with a negative charge, primary carb anions are more stable than tertiary ones. So the trend is reversed. Electron donating groups like methyl groups, they can stabilize a carbocation. Electron withdrawing groups stabilizes a carbanion. So which answers can we eliminate? So if we look at answer choice A, we have a tertiary carbanion. And if we look at answer choice B, it's a secondary carbanion. So B is more stable than A. Secondary carbanions are more stable than tertiary ones. Now if we look at answer choice C, we have a primary carbanion, but this one is stabilized by resonance. And so the negative charge is shared between two carbon atoms as opposed to one. So this is going to be the resonance form. So C is more stable than B. Now D is going to be the answer because we have an electron withdrawing group. We can put the negative charge on the oxygen, and putting a negative charge on an oxygen is better than having it on a carbon. So let's draw the first resonance structure. We could take this lone pair, form a double bond, and push a lone pair on this carbon. So that will give us a resonance structure that looks like this. Next, we could take that lone pair, form a double bond, and break the pi bond between the carbon and the oxygen. So now the oxygen has 3 lone pairs, and it's going to bear the negative charge. This resonance form is the most stable one because the negative charge is placed on the oxygen as opposed to the carbon. So it's always better to put the negative charge on a more electronegative atom. So that's why D is the answer. It has the most resonance structures, and we could place a negative charge on an oxygen instead of a carbon. Number 60. Which reagent can convert cyclohexanol into chlorocyclohexane? So let's draw cyclohexanol. It's basically a cyclohexane ring with an OH group. So what's going to happen if we react it with SOCl2? SOCl2 will convert the OH group into a Cl group. Just replace it. And so reagent 1 will work. So we can eliminate B because it doesn't have reagent 1, and we can get rid of C. The side product of SOCl2 is SO2 gas, which leaves the solution. Also, you have HCl gas that leaves as well. So the formation of these gases drives the reaction towards the right. Now what about PCl3? We know that using PBr3 can convert an OH group into a Br. And we know the mechanism is an SN2 reaction. PCl3 works the same way. It will convert cyclohexanol into cyclohexochloride or chlorocyclohexane. So it just replaces the OH group with a Cl. And because it's an SN2 reaction, it will occur with inversion of configuration. So since number 3 works and number 1 works, we have to eliminate answer choice A because it doesn't have 3. So therefore, all of them will work. PCl5 and PCl3, the reaction is very similar. Both of them will convert an OH group into a Cl. And for number 2, this is the Lucas reagent. If you add HBr to an OH group, the OH will eventually be replaced with a Br. So the same is true for HCl. If you mix an alcohol with HCl, it will convert it into an alkyl chloride. However, because the chloride ion is a weaker nucleophile than a bromide ion, this reaction might need a Lewis acid to speed up the process because it's a little bit slower than HBr. And so zinc chloride is used with HCl to help the reaction go forward. 61. Which reagent will convert propyne into 1-propanol? Is it going to be A, B, C, or D? Well, let's go through each one. So A is the hydroboration oxidation reaction. Now this reaction occurs with anti-Markovnikov regiochemistry. So what that means is that the group that we're going to add across the triple bond is going to go on the less substituted carbon. It's going to go on the primary carbon of the alkyne. So this reaction initially produces an enol. So I'm going to draw it using line structures. The OH group will be added to the primary carbon, and the enol is going to tautomerize into the aldehyde form. And so this is the final product for answer choice A, which is not what we're looking for. So A is not the answer. Now let's move on to answer choice B. This is the oxymercuration-demercuration reaction with alkynes. And once you add mercury sulfate with water and sulfuric acid, it's going to give us an enol, but with Markovnikov addition. So the OH group will go on the secondary carbon as opposed to the primary carbon. And this is going to tautomerize into the ketone form. And that's not the answer that we're looking for. So B can be eliminated as well. Now let's move on to part C. Add in hydrogen gas with palladium over barium sulfate. This is equivalent to the Lindner's catalyst, and this will give us a cis alkyne, but cis and trans is irrelevant here because these two hydrogens are the same, so it really doesn't matter. But for the Lindner's catalyst, if it did matter, it would give you the cis alkene. Just keep that in mind. Now, once we add mercury acetate with water, followed by sodium borohydride, this is an oxymercuration-demercuration reaction. So it's going to put an alcohol on the secondary carbon. It occurs with Markovnikov regiochemistry. So we won't get an enol, we're just going to get an alcohol. So that's not the answer we're looking for. That's a secondary alcohol. We want a primary alcohol. So the correct answer has to be D. So once we use lithium with liquid ammonia, the alkyne will turn into a trans alkene. But for this particular structure, because the double bond is at the end, there's no cis or trans isomers that we can draw for it. Now once we have the alkene, and once we add BH3 with THF, followed by hydrogen peroxide and sodium hydroxide, this reaction occurs with anti-Markovnikov regiochemistry. It's going to put the alcohol on the primary carbon. So it's going to give us one propanol. D is the answer. 62. What is the product of the reaction shown below? Well, the first thing that's going to happen is the double bond is going to grab a hydrogen. And the hydrogen is going to go on the less substituted carbon. So this will lead to a secondary carbocation. And then we're going to have a hydride shift. So this carbocation will rearrange to form a more stable tertiary carbocation. Once we have the tertiary carbocation, then the methanol will add itself to it. And so we're going to get an intermediate that looks like this. In the last step, another methanol molecule is going to remove this hydrogen, giving us this product. So that's going to be the answer to this problem. So C is the correct answer. Number 63, identify the product of the reaction. So let's go over the mechanism first. Hydroxide is used to remove the hydrogen that's attached to the carbon. That hydrogen is relatively acidic due to the fact that there's 3 electronegative atoms attached to the carbon. So this is going to give us a carbon with a negative charge. Now this intermediate is relatively unstable, so spontaneously one of the bromide ions will leave. And this will lead to a carbene, which looks like this. That is the intermediate of the reaction. Now we're going to react that carbene with a cis alkene. I'm going to turn it. Actually, let's just draw it this way. And let's put the carbene directly above it. So the double bond is going to attack the carbon, and the carbon will use its lone pair to attack the double bond. So simultaneously, these two will react and will form a molecule that looks like this. So it turns out that A is the correct answer. Because the CH3s were cis with respect to each other, they will remain in that position. Now let's say if we started with a transalkene. Let's say that the methyl groups were on opposite sides. Using bromoform with potassium hydroxide, this will give us product B as the answer. So if the methyl groups were trans with respect to each other initially, they will remain that way. But for this particular problem, we started with a cis alkene, so the methyl groups have to be on the same side. So therefore A is the right answer. Number 64. What is the product of the reaction shown below? So you know the mechanism for this reaction already. So let's focus on the products. When you have bromine in water, you're going to get a bromine atom and an OH group that's going to be added across the double bond. The OH group is going to go on the more substituted carbon of the double bond, and the bromine is going to go on the less substituted carbon, which is the secondary carbon. And this reaction occurs with anti-addition. So if we put the OH group in the front, that means that the bromine atom will be in the back, and we can get the enantiomer. By the way, that means the methyl group is in the back if OH is in the front. So now the enantiomer is OH is in the back, the methyl is in the front, and the bromine atom is in the front. So the important thing that you need to keep in mind is that the OH and the bromine atom, the two things that are added across the double bond, those two are anti with respect to each other. So now which one is the correct answer? So first, we need to make sure that the alcohol group is attached to the same carbon as the methyl group. So that means we can eliminate answer choice C and D. The bromine atom should not be attached to the tertiary carbon. Now, looking at A and B, these two have to be opposite to each other. In answer choice A, they're on the same side. That's a syn addition process. So A is eliminated. The correct answer is B. As we can see, the bromine atom and the hydroxyl group, they're anti with respect to each other, and the OH group is on the more substituted tertiary carbon. Number 65. What is the relationship between the two molecules shown below? Are they enantiomers, diastereomers, constitutional isomers, or identical molecules? What would you say? So you need to know the difference between a stereoisomer and a constitutional isomer. A stereoisomer has the same connectivity, but they're arranged in space differently. A constitutional isomer has a different connectivity. So right now, both molecules have the same chemical formula. We have 6 carbon atoms, 2 fluorine atoms. But the connectivity is different. In the first compound, we have a fluorine atom on carbons 1 and 3. In the second one, we have a fluorine atom on carbons 1 and 4. So they're connected differently, which means that they're constitutional isomers. Number 66. How many stereoisomers exist for the compound shown below? So we need to identify the number of chiral centers. The number of stereoisomers is equal to 2 to the n, where n is the number of chiral centers. So how many carbon atoms that are in this molecule have 4 different groups? Let's start with this carbon. Is it a chiral center? That carbon has a bromine atom. It has a methyl group. It has this entire group to the left, and it has a hydrogen that we don't see. So it's a chiral center. Primary carbons are never chiral centers because this carbon has 3 hydrogens. It doesn't have 4 different groups. This carbon has 2 hydrogens as well, so it's not a chiral center. If you repeat this process, you'll find that this carbon here is a chiral center. We have this group to the left, this side, and that side is different, and then there's a hydrogen. So it has 4 different groups. So far we have 2 chiral centers. This carbon's another chiral center. It has a chlorine, it has a hydrogen. The right side is different from the left side. The left side has an OH group, the right side has a few carbons and a bromine atom. And then the carbon that has the OH, that's another chiral center. So we have a total of 4 chiral centers in this molecule. So therefore it's going to be 2 to the 4th power, which is 2 times 2 times 2 times 2, 4 times. 2 times 2 is 4, 4 times 4 is 16. So there's 16 possible stereoisomers in this molecule. 67. How many stereoisomers are possible for the molecule shown below? So this question is similar to the previous problem, but instead of dealing with stereocenters, we're dealing with double bonds. So which double bond can show cis or trans isomerism? Which ones have E and Z isomers? So let's analyze the one on the left. It has 2 methyl groups. It has a hydrogen and an R group. Now, because this carbon, which is part of the double bond, has 2 similar groups, it does not have E or Z isomers. If you flip it, it's going to be the same. Now let's move on to the second one. This one has a hydrogen, and this one has a hydrogen. So if we focus on one of the carbon atoms that are part of the double bond, this one has 2 different groups, so it's okay. If we focus on the other carbon, this one has 2 different groups. So this particular isomer that we see here is the E isomer. The Z isomer would look like this. That's the Z isomer. Notice that the hydrogens are on the same side. Now what about the last double bond? This one has 2 hydrogens at the end, so this doesn't have an E or Z isomer. So therefore, there's only 2 stereoisomers that are possible for this molecule, the E isomer and the Z isomer, because we have only one double bond that shows cis or trans stereoisomerism. If there were 2 double bonds that can show cis and trans isomerism, it would be 2 squared, which is 4. If there were 3 double bonds that had that feature, there would be 8 isomers. Let's say if there were 2 double bonds, it could be EE, that's 1 isomer. The second one is EZ. The third one is ZZ. And the fourth could be ZE. So as you can see, if there's 2 double bonds that show cis-trans isomerism, we can have a total of 4 stereoisomers. But what about if there's 3? So all 3 double bonds could be EEE, it could be EEZ, or EZE, or EZZ. It could also be ZZZ, ZZE, ZEZ, and ZEE. So if there's 3 double bonds that can have cis or trans isomerism, as you can see, there's a total of 8 possible stereoisomers. But for this problem, we only have one double bond that shows cis or trans isomerism. So therefore, we have only two answers, E or Z, which means answer choice A is the right answer. 68. What is the major product of the reaction shown below? Is it going to be A, B, C, or D? Well, we have a secondary alkyl halide. Sodium has a plus charge. Sulfur has a negative charge. Whenever you see sulfur with a negative charge, it's a very, very good nucleophile. And we have a polar aprotic solvent, DMF. So therefore, these conditions favor an SN2 reaction. And an SN2 reaction does not produce a double bond. It doesn't produce an alkene. That's a characteristic of an E2 or an E1 reaction. So C and D can be eliminated. The sulfur is going to attack from the back, expelling the bromine atom. SN2 reactions occur with inversion of configuration. Because the bromine was in the axial up position, the sulfur will now occupy the equatorial down position. So always keep that in mind. The SN2 reaction proceeds with inversion of stereochemistry. So B is the correct answer. All you really need to do is replace Br with SH and change the position from axial to equatorial, and then you'll get the answer. Number 69. How many different monochlorinated products, including stereoisomers, can be formed from the reaction of 2-methylbutane with chlorine in the presence of UV light? So let's draw a picture. So this is butane, and we have a methyl on carbon 2. And we're going to react it with chlorine in the presence of UV light. So how many different monochlorinated products? So where can we put the chlorine atoms? Chlorine can replace a primary hydrogen. This would lead to one product. It can also replace a hydrogen on a secondary carbon. This carbon is primary, secondary, tertiary, and these are primary. So this is the other product that we can get. It can also replace a tertiary hydrogen, giving us this product. And it can replace a primary hydrogen at the end. Now what you need to know is that if you put a Cl here or on this carbon, it's identical. If you're not sure as to why, go ahead and name it. Draw both products. Let's say if we name the first one, this is going to be 1, 2, 3, 4. So it's 1-chloro, 2-methyl butane. Now if you name the other one, you have to count it this way. That's also going to be 1-chloro, 2-methyl butane. So that means that those two compounds are equivalent. So it appears as if the answer is 4, but it's not, because we need to take into account stereoisomers. So which of these molecules have a chiral center? This carbon is not chiral because there's 2 hydrogens. It doesn't have 4 different groups. Same is true for this one. This carbon has 2 methyl groups. The only one that is chiral is this compound. This carbon has a chlorine, it has a methyl group, it has a hydrogen, and it has an isopropyl group on the left. So the chlorine could be in the front, or it can be in the back. So that's 2 stereoisomers for this particular compound. So we have a total of 5 different products that can be formed, including stereoisomers. 1, 2, 3, 4, 5. So C is the answer. Number 70. Which diol can be cleaved by HiO4, periodic acid? So the first thing you need to know is that HiO4 can cleave only 1,2 diols. The 2 hydroxy groups have to be next to each other. So we can eliminate answer choice C and D. Those are 1,3 diols. The second requirement is that the 1,2 diol has to be cis with respect to each other. In answer choice B, the OH groups are in the trans form. That's the trans isomer, so that's not going to work. But here, the OH groups are on the same side, so that's the cis isomer. Therefore, answer choice A is correct. Now, what's going to happen when we mix cis cyclohexane or 1,2-cyclohexane diol with HiO4? What product will we get? It's going to cleave the carbon-carbon bond, and the hydroxy groups will be oxidized into aldehydes and ketones. But because there's no other additional carbons at the end, we're going to have two aldehydes. If there was a methyl group here, then it would be a ketone. So we can rewrite the structure like this. So we have 6 carbons in total and an aldehyde at the first and last carbon. So this would be the product of the reaction. 71. What are the products of this reaction? So we have periodic acid as the reagent. So based on the last problem, we know that it cleaves 1,2-diols. So therefore, it's not going to affect this alcohol because there's not another OH adjacent to it, which means that we should still have it in the product. So therefore, we can eliminate answer choice C and D. Now the bond is going to cleave here. So on one side, we should have a 2-carbon product, which we could see that in answer choices A and B. And then the other side, we should have the remaining amount of carbons. Let's see, it's going to be 1, 2, 3, 4, 5, 6, 7, a total of 8 carbons. And the other one has that as well. Now, what you need to know is that periodic acid, after it cleaves a 1,2-diol, it produces only ketones and aldehydes. It does not produce carboxylic acids. So B is eliminated. This OH will become a ketone due to the presence of this methyl group. And this alcohol, because there's a hydrogen here, it's going to turn into a carbonyl group, but specifically an aldehyde. So just know that this reagent only produces ketones and aldehydes. So answer choice A is the right answer. 72. What are the products of this reaction? So we have methyl cyclohexane reacting with ozone followed by dimethyl sulfide. The temperature of this reaction is very low, negative 78 degrees Celsius, which you can use dry ice to achieve that temperature. Now, what do you think the answer is going to be? Ozone is used to cleave alkenes. Whenever you cleave a cyclic alkene, you're going to get one molecule. It's going to be a straight chain. So you won't get two separate molecules. So you can eliminate answer choice D. Now, if you were to cleave an alkene that is in a straight chain, that's not in a ring, and then you're going to get two products for a single alkene. So here's how you can identify the product. First, you want to break the double bond. Draw everything the same, but don't include the double bond. Where the double bond was, there's going to be 2 carbonyl groups. This is a CH3, and what we don't see here is a hydrogen. So now notice how many carbons we have. On carbon 1, we have an aldehyde, and on carbon 6, we have a ketone. Ozone only produces ketones and aldehydes. You shouldn't get a carboxylic acid, and you shouldn't get a CO2 molecule, so C is eliminated. The issue with B is that it has too many carbons. So we can eliminate B. We started with 7 carbons. We shouldn't have 8. A is the only answer that makes sense. We have an aldehyde at carbon 1 and a ketone at carbon 6. So A is the answer. 73. What are the products of this reaction? So we still have methyl cyclohexane, but this time we're using potassium permanganate under acidic conditions, and we're adding heat to it. And it could be concentrated as well. Now this reaction works similar to the last problem where we use ozone. It's going to cleave the alkene. But there's going to be a difference though that we have to pay attention to. So this carbon, where the double bond was, is secondary after being cleaved. The secondary carbon is going to be fully oxidized to a ketone. So that's not different from ozone. However, the primary carbon will be oxidized fully to a carboxylic acid. If we were to use ozone, ozone will stop at the aldehyde level. But potassium permanganate under acidic conditions and when it's heated, it's going to fully oxidize the primary carbon to a carboxylic acid. And if you have a methyl carbon, that is a molecule with just one carbon by itself, this reaction will fully oxidize it to CO2. So we can see that answer choice C is the answer. It's the only one that has the carboxylic acid. 74. What are the products of this reaction? So we have an internal alkyne, particularly 2-pentyne, and we're going to react it with ozone followed by H2O. Now we know that mixing an alkene with ozone produces ketones and aldehydes. But what about reacting it with an alkyne? If you react it with an internal alkyne, you're going to get 2 carboxylic acids. You need to cleave it at the triple bond, and on the left side you can see that there are 3 carbons. On the right side there's 2. And at each of those carbons that were part of the triple bond, that's where the carboxylic acid is going to be. So we're going to get CH3, CH2, C with a carboxylic acid, and on the other side we're going to get another carboxylic acid as well. So we can see that the correct answer is answer choice C. So we're not going to get any aldehydes or ketones. So A, B, and C are eliminated. And I just realized I wrote C twice. This is supposed to be D. So this is not the answer, but this C is the answer. 75. Which molecule will produce the products shown below during ozonolysis? Is it going to be A, B, C, or D? Well, the first thing we could do is count the carbons and see if we can eliminate any answers. So this has 3 carbons, this has 3, that has 2, so the total must be 8. Let's look at answer choice A. We have a 6 carbon chain, 2 methyl groups, so that's a total of 8. So A is okay. If we look at B, we have a 7 carbon chain, 1 methyl group, so that's a total of 8. If we look at answer choice D, this is 1, 2, 3, 4, 5, 6, 7 with 2 methyl groups. That's a total of 9 carbons. It doesn't add up. So at least we can eliminate answer choice D. If we check C, C has 7 carbons in a methyl group, so it adds up to 8. Now what do you think we need to do at this point? How can we find the answer? Well, what we could do is look at each answer choice and find out which one matches. So we know ozone will create only ketones and aldehydes. So if we cleave it here, this will give us a ketone that looks like this. And on the other side, we're going to have this group. And we should also cleave it here. If we do so, notice that there's only 2 carbons in between the 2 green lines. So we should get something that looks like this. And then for this portion, wherever you see a double bond, add a double bond O. We will get this molecule. We can see that these 2 do not match. This molecule has 3 carbons, this one has 2. So A can be eliminated. So that's one way you can do it. You can check each answer choice, cleave the double bond, and see if it produces the result that we see here. Another way in which we can do it is by putting these together. So which molecules should we put together? It wouldn't make sense for us to put these 2 together because they will form only a 5 carbon molecule, which we need an 8 carbon molecule. The group in the middle, the one with the 2 carbonyl groups, is the one that will connect this molecule and that molecule because it has 2 carbonyl groups. So we need to put this group in the middle. So let's draw it first. And let's draw the carbonyl groups facing one another. So let's connect this carbonyl group to this one. And then let's connect this carbonyl group to that one. Now, because this molecule is symmetrical, it doesn't matter which group that we connect it with. We can connect this ketone with this aldehyde or the other aldehyde. Due to symmetry, it doesn't matter which one we put together. So now let's connect this molecule to this portion of the molecule in the middle. So what you need to do at this point is get rid of the oxygens and connect the molecules by means of a double bond. So if we redraw it, we're going to have a double bond here, 3 carbons, another double bond, and then a carbon with an OH. So as you can see, this portion correlates to this part of the molecule. This part correlates to this part of the molecule. And then this portion is basically this part of the molecule. So you can see where everything is. So based on this, which molecule is the answer? We can clearly see that this molecule looks very similar to C. In fact, they're the same. So C is the right answer. And you could check it. If we cleave it here and here, we can see that we're going to get acetone, and on the right side, we're going to get a 2-carbon molecule that has an aldehyde and an alcohol, which is this molecule, that's from this side. And in the middle, there's 3 carbons. And because we have an alkene here, we're going to get an aldehyde on this side. And the same is true for the alkene on the right. We're going to get an aldehyde on the left side, not the right side. This is the alkene on the left. So if you cleave it, you'll get these 3 molecules. So you can check each answer, cleave in every double bond, and see which one is going to produce this result. Or you can put these 3 molecules together and find out which one is the right answer. So you have to pick a method that you're comfortable using. So the right answer is answer choice C. 76. Which of the following reactions will not work? Looking at answer choice A, we have a primary alcohol, 1-butanol. PCC is a mild oxidizing agent. It will oxidize a primary alcohol into an aldehyde. So answer choice A will work, which means it's not the answer that we're looking for. We're looking for the reaction that will not work. B, we have a secondary alcohol, cyclopentanol, and we're using chromic acid to oxidize it. Secondary alcohols can be fully oxidized to a ketone, and chromic acid is a strong oxidizing agent, so this will work. Tertiary alcohols are highly resistant to oxidation. So tert-butanol is not going to be easily oxidized to CO2. So this reaction will not work, which means that C is the answer. Looking at answer choice D, we have a methyl alcohol. Methanol could be easily oxidized to CO2 because it's 1 carbon. We don't have to break any carbon-carbon bonds. So D will work. Now let's talk about the different levels of oxidation, starting with methanol. The first step in methanol's oxidation is the conversion of methanol into an aldehyde. Whenever you add oxygen or remove hydrogen, it's oxidation. If you remove oxygen or add hydrogen, it's reduction. Formaldehyde can be oxidized further to formic acid. And formic acid can be fully oxidized to CO2. So if you use a strong oxidizing agent, be it potassium permanganate with H3O+ under concentrated heated conditions, or if you use sodium dichromate with sulfuric acid or chromic acid, all of these are strong oxidizing agents. they will fully oxidize a molecule all the way to the end. So let's say if you were to use chromic acid with methanol. Chromic acid will fully oxidize methanol to CO2. PCC always stops at the aldehyde/ketone level. So PCC will take methyl alcohol and convert it to formaldehyde. Now let's say if we have a primary alcohol. A primary alcohol can be oxidized to an aldehyde, and that aldehyde can be oxidized to a carboxylic acid. And this is as far as it goes without breaking carbon-carbon bonds. So PCC can take a primary alcohol and oxidize it to the aldehyde level. A strong oxidizing agent like chromic acid or even potassium permanganate or sodium or potassium dichromate, all of these will fully oxidize a primary alcohol to a carboxylic acid. Now, what if we have a secondary alcohol? How far will it go? A secondary alcohol will stop at the ketone level. So you can use PCC to get the job done, or you can use a strong oxidizing agent like chromic acid or something. Now, if you have a tertiary alcohol, it's resistant to oxidation. So for all practical purposes, no reaction will occur unless you have a very, very powerful oxidizing agent and react it under extreme conditions. 77. What is the major product of the reaction shown below? Before we do this one, let's say if we have 2-bromopentane instead. And let's react it with potassium methoxide. Methoxide is a very strong base. And if you put a strong base with a secondary alkyl halide, this is going to favor an E2 reaction. That's going to be, the E2 reaction is going to lead to the major product in this reaction. So we're not going to get a substitution product in good yield. So we can eliminate answer choice A and B. Elimination reactions always produce alkenes or new double bonds. Now, which hydrogen will methoxide go for? Is it going to go for the primary hydrogen, or is it going to go for the secondary hydrogen? It turns out that if you have a good leaving group like chloride, bromide, or iodide, the strong base, let's say if it's not a bulky base like terpetoxide, if you have a strong base that is non-bulky, it's going to go for the hydrogen that leads to the more stable product. In this case, the secondary hydrogen. This will give us the Zaitsev product, which is associated with a more stable alkene. So keep that in mind. If the leaving group is a good leaving group like chloride, bromide, or iodide, and if you use a strong non-bulky base, you're going to get the Zaitsev product. Now, even if we use a non-bulky base like methoxide, but if we have a bad leaving group like fluoride, it's going to give us the Hoffman product. And the reason why the base is going to go for the primary hydrogen as opposed to the secondary hydrogen is because the transition state resembles more like a carbanion as opposed to an alkene. In this example, the transition state resembles an alkene, and so we're going to get the more stable alkene. But in the case of a bad leaving group like fluoride, the transition state resembles like a carbanion, and we know that primary carbanions are more stable than secondary carbanions. So the base is going to go for the less substituted hydrogen. So this is going to give us the Hoffman product, the less stable alkene. So therefore, answer choice D is the right answer. 78. What is the IUPAC name of the bicyclic compound shown below? Is it going to be A, B, C, or D? Well, first, you need to identify the bridgehead carbons. These are basically the tertiary carbons that you see here that connect the two ring systems together. Now, determine the number of carbons in each link connected to those two bridgehead carbons. In this link, there are two non-bridgehead carbons. On this side, we have a total of 3. You can see it, 1, 2, 3. And in this link, there's only 1. Now we have a total of 8 carbons. You add 3, 2, 1 plus the 2 bridgehead carbons, which means that it's octane because there's a total of 8 carbons. So it's not heptane and it's not hexane. Now, the way you need to name it is going to be bicyclo, and then in descendant order, 3, 2, 1, octane. So A is the correct answer. Now, let's go over another example so you could see what to do for the sake of practice. Go ahead and name this bicyclic compound. Feel free to pause the video. So first, let's identify the bridgehead carbons. In this side, there are 2 carbons. On this side, we also have 2 carbons. And in this link, there's a total of 3 carbons. So 3 plus 2 plus 2 is 7, plus the 2 bridgehead carbons, it's 9. So it's nonane. So it's going to be called bicyclo in descendant order, 3, 2, 2, nonane. Let's try one more example. Try this one. So first, identify the bridgehead carbons. These are the 2 carbons connecting the 2-ring system. Now on this side, we have a total of 4 carbons. And on this side, we have a total of 3 carbons. And in the middle, there's nothing between the 2 bridgehead carbons, so we're going to put 0. 4 plus 0 plus 3 is 7, and if you add the 2 bridgehead carbons, that give you 9. So this is associated with nonane. So it's going to be called bicyclo because it's 2 rings, and then in descendant order, 4, 3, 0, nonane. So now you know how to name bicyclic compounds. 79. Which of the following conformations of cyclohexane is least stable? Is it A, the chair conformation, B, the half chair, C, the bolt conformation, or D, the twist bolt? You need to know that the chair conformation is the most stable. The second most stable is the twist bolt. And then the bolt is the third most stable. The least stable conformation is the half chair conformation. It has the highest energy. And so B is the answer. Now, if you want to draw the pictures, this is the picture for the chair conformation. For the twist bolt conformation, it looks something like this. The bolt looks like a boat. And this is going to be the half chair. It looks like a rocket ship, kind of. But B is the answer. The half chair is the least stable. Number 80. Which of the following reactions will not work? Is it going to be A, B, C, or D? Well, let's look at answer choice A. What's going to happen if we take a ketone, cyclopentanone, and react it with hydrogen gas? If we use a Raney nickel catalyst, it can reduce the ketone into an alcohol. So I'm going to propose a mechanism. It might be a radical reaction, but I'm going to keep it simple. So this bond is going to be used to form the connection between the carbon and this hydrogen. And this bond is going to be used to form the connection between this oxygen and this hydrogen. So thus we get cyclopentanol. So answer choice A will work, which means that it's not the answer that we're looking for. We're looking for the one that doesn't work. Now let's move on to answer choice B. B will not work. A carboxylic acid cannot be reduced by sodium borohydride. NaBH4 is not strong enough to reduce a carboxylic acid. NaBH4 can reduce a ketone, an aldehyde, or something that's more reactive, more electrophilic than a ketone or an aldehyde. So B is the answer. Now let's go over answer choice C. let's talk about the mechanism. So we're adding methyl magnesium bromide, which is a Grignard reagent. Magnesium has a positive charge, which means that the methyl group must have a partial negative charge. So it's attracted to the partially positive carbon atom of the carbonyl group. So the methyl is going to attack it, and the pi bond is going to break. So initially, we're going to get an alkoxide ion, which is basically an oxygen with a negative charge attached to an R group, and we're going to add a methyl to it. In the next step, we're going to add H3O+. We are going to acidify the solution with the hydronium ion. So this is going to grab a hydrogen, and it's going to turn into a tertiary alcohol, which we can see that we do indeed have. So C, that reaction works, which means C is eliminated, and we know the answer is already B. Now let's move on to answer choice D. Lithium aluminum hydride and sodium borohydride can both reduce this ketone into an alcohol. Lithium aluminum hydride has a lithium plus ion. It has an aluminum atom attached to 4 hydride ions. Hydrogen is more electronegative than aluminum, so hydrogen bears a partial negative charge. And the hydride ion is attracted to the partially positive carbon atom. So it's going to add in a nucleophilic addition reaction just like the Grignard did. So we're going to get an alkoxide ion, and we've added a hydrogen, and then in the next step, using H3O+, we're going to acidify the solution. So this will give us cyclopentanol. So reaction D works. So B, the one that doesn't work, is the answer. 81. Which reagents will convert propyne into a primary alcohol? Propyne is a 3-carbon alkyne, and sodium amide is a strong base. It's strong enough to remove the hydrogen. So for each answer choice, this is going to be the product after the first step of the reaction. Now, once we have this carbon with this negative charge, in answer choice A, it's going to react with acetone. So acetone, we can draw it like this. It has 2 methyl groups and a carbonyl group. So the alkyne is going to attack the partially positive carbonyl carbon, and then the pi bond is going to break, and so we're going to get a structure that looks like this. So we're going to have a total of 6 carbons. So this carbon connects to the middle carbon. That carbon has an oxygen with a negative charge, and that carbon is attached to 2 other methyl groups, as you can see here. In the next step, it's going to grab a hydrogen from H3O+. And it's going to turn into alcohol. So if you want to draw the line structure, it's going to look like this. So as you can see, it's a tertiary alcohol and not a primary one. So answer choice A is not the answer that we're looking for. Now what about answer choice B? What type of product will we get? Let's go through the mechanism. So the first step, like in answer choice A, is the removal of the hydrogen. So we're going to start with this nucleophile. And we're going to react it this time with an aldehyde, CH3CHO, which looks like this. It's a 2-carbon aldehyde. So the nucleophile is going to attack the carbonyl carbon just like before, and it's going to break that pi bond. So we're going to add 2 carbons, And this carbon is going to have an oxygen with a negative charge. And then in the next step, the last step actually, it's protonation. So now let's convert the final product into a line structure. So right now this is 4 carbons, and this is the 5th carbon. As we can see here, we have a total of 5 carbons, and the OH is on a secondary carbon, which makes this a secondary alcohol. So we can eliminate B. Now what about C? What if we have CO2? What's going to happen? So let's start with the 3 carbon nucleophile. Let's react it with carbon dioxide. Carbon dioxide is a linear molecule. It looks like that. And so this is going to attack the carbon as it's been doing before. And so we're only going to get a total of 4 carbons. But notice that this is the deprotonated form of a carboxylic acid. Now once we add H3O plus to the solution, we're going to get rid of the negative charge. We're going to add a hydrogen to the molecule. So we're not going to get an alcohol. Instead, we're going to get a carboxylic acid. So that's the answer for C. So by elimination, it has to be answer choice D. Now what exactly is CH2OCH2? How can we draw that? How can we assemble 2 carbon atoms, 4 hydrogen atoms, and an oxygen such that every hydrogen atom has 1 bond, every carbon atom has 4, and the oxygen has 2 bonds? So we have 2 carbon atoms. Each of them contain 2 hydrogen atoms. We can't place the oxygen in the middle because carbon would only have 3 bonds. The only way to do this is to draw an epoxide, which looks like that. As you can see, every carbon atom has 4 bonds, oxygen has 2, and hydrogen has 1. But I'm going to draw the line structure of the epoxide. The nucleophile is going to attack one of the carbon atoms. It really doesn't matter which one because it's symmetrical. And then one of the carbon-oxygen bonds will break. So it's connected to this carbon, which is a CH2, and that carbon is no longer connected to the oxygen because this carbon-oxygen bond broke. However, the carbon at the end is still attached to an oxygen. So here we have another CH2, and that CH2 has the oxygen with a negative charge. And now we can protonate it with H3O plus. So therefore, this will give us a primary alcohol, which looks like this. So answer choice D is indeed the correct answer. 82. Which of the following reactions will produce an epoxide? Is it going to be A, B, C, or D? Well, let's start with A. What's going to happen if we mix ethanol with sulfuric acid? There's 2 things that can happen. One, you can get an elimination reaction where it forms an alkene. Sometimes you can also get this where 2 ethanol molecules will get together and form an ether. So that's more like a substitution reaction. It turns out that if you reach a temperature of 140, it will turn into an ether with removal of water. At a higher temperature of 180, it favors elimination, but water will still be removed. Let's go over the mechanism for both processes. Either case though, we can see A is not the answer. None of these reactions will produce an epoxide. So in the meantime, feel free to pause the video and propose a mechanism for those two processes. So the first one is an elimination reaction. When you see concentrated sulfuric acid, know that there is a small amount of water dissolved in the solution. The first thing we're going to do is react the alcohol with an H plus to turn it into a good leaving group. So it's going to become OH2. Now, is this going to be an E2 reaction or an E1 reaction? Because the oxygen is on a primary carbon, it can't be an E1 reaction. It is very difficult to form a primary carbocation. A primary carbocation is relatively unstable. So this has to be an E2 reaction. Another alcohol molecule will come in to grab the hydrogen, form a double bond, expel H2O without forming an unstable primary carbocation. Primary alcohols can be dehydrated using an E2 mechanism. If it's a secondary or tertiary alcohol, then it's going to be an E1 mechanism under acidic conditions. So that's how we're going to get an alkene. Now let's go over the substitution mechanism. So the first step is going to be the same. That is protonation. Now, which substitution mechanism do you think is about to occur? SN1 or an SN2 reaction? Now, it can't be SN1 because, as we mentioned before, it's very difficult to form a primary carbocation. Primary carbocations are not stable, so it has to be an SN2 reaction. So another alcohol molecule, instead of going for the hydrogen and performing an E2 reaction like we did before, which generated an alkene, it's going to attack the carbon that has the water, that has the good leaving group. And so we're going to get an ether. So now we can use water, or we can use another ethanol molecule to get rid of this hydrogen. It really depends on which molecule is at the right place at the right time. So now we have this ether, diethyl ether. This is an example of a bimolecular dehydration reaction. If you want to quickly draw the product of that reaction, here's what you can do. Put the two alcohols facing each other. And then all you need to do is take out water. Once you remove water and connect the two other parts together, you can see that this will give you the ether. Now what about part B? What type of product will we get in that reaction? So we have a molecule that has two functional groups. It has a halide and an alcohol. Sodium hydride is a strong base. The hydride ion will be used to deprotonate the alcohol. It's going to turn it into an alkoxide. Once you take off the hydrogen, the oxygen with negative charge becomes a good nucleophile. And so an intramolecular reaction will occur. It will attack the carbon that has the bromine. When a molecule reacts with itself, typically it closes to form a ring. Let's call this atom 1, 2, 3, 4, 5, 6. So this is going to give us a 6-membered ring. So this is a cyclic ether, but not an epoxide. The epoxide looks like this. This is what we want. Now what about part C? What's going to happen in this case? So we have phenol. Phenol is a relatively acidic alcohol. The pKa is 10, so we don't need to use a strong base like sodium hydride to get rid of the hydrogen. We can use sodium hydroxide. It's still a relatively strong base, but it's not as strong as sodium hydride. Hydroxide will deprotonate the phenol molecule, giving us the phenoxide ion. And the second step is the Williamson ether synthesis reaction. We're going to react it with an alkyl halide, and it's going to turn into an ether. So all we need to do is add 2 carbons to the oxygen. So the product is ethyl phenyl ether. As we can see, this is not an epoxide, so we can eliminate answer choice A, B, and C. So the answer is going to be D. So first we have an alkene, cyclohexene, and we're going to react it with bromine. Now, you've seen this mechanism before. You know the double bond is going to attack the bromine atom, the other one will be expelled, and bromine will simultaneously attack the double bond, forming a cyclic brominium ion. So this bromine atom is going to have 2 lone pairs and a plus charge. And then water is going to come in, and it's going to attack one of the carbons. It really doesn't matter which one because they're both the same. And so we're going to get a halohydrin. This reaction occurs with anti-addition. So one of the bromine atoms is in the front, the other OH group is in the back. But let's not worry about stereochemistry for this example. We don't have the alcohol yet because we just added water. So in the next step, we need to use another water molecule to get rid of the hydrogen. So now we have the halohydrin. Now let's react it with sodium hydroxide. This alcohol is a little bit more acidic than most other alcohols due to the presence of the bromine atom. Whenever you add an electron withdrawing group, the acid becomes a stronger acid. If you add an electron donating group to an acid, it makes the acid weaker. So hydroxide is going to take off a hydrogen and form an alkoxide ion. So now the oxygen with the negative charge is attracted to the carbon attached to the bromine atom because that carbon has a partial positive charge. And so it's going to attack this carbon, kicking out the bromine atom. And this will create an epoxide, which looks like this. So as we can see, D is indeed the right answer. 83. What is the major substitution product of the reaction shown below? H3PO4 phosphoric acid works very similar to H2SO4. So the first step in this reaction, just like the other reactions under acidic conditions, is protonation. We're going to protonate the secondary alcohol before we protonate the primary one. The reason being is it's easier to form a secondary carbocation than it is to form a primary carbocation. So this is going to turn into a good leaving group. In the next step, water is going to leave. So now we have a secondary carbocation. And the other alcohol is attracted to it. It has a partial negative charge, and so it's going to attack the carbocation. And the ring is going to close. So this is going to be number 1, 2, 3, 4, 5, 6. So we're going to get a 6-membered ring with an oxygen in the ring. Now we still have a hydrogen on the oxygen, and that oxygen has a plus charge. The methyl group is on carbon 6. So if the oxygen is number 1, let's call this number 2, 3, 4, 5, 6. Or better yet, let's count it the other way. Let's make this 2, 3, 4, 5, 6. If we do it that way, you can see that the answer that we're going to get is C. The last thing that we need to do in the mechanism is use a water molecule to get rid of the hydrogen. And then we'll get this answer. And that's all you got to do for this problem. So that's it for 83. 84. What is the major product of the reaction shown below? So we have a diol, and we're adding sulfuric acid to it. What do you think is going to happen? Well, the first thing that's going to happen is protonation. The oxygen is going to grab a hydrogen, and it's going to turn into a good leaving group. So we're going to get a OH2. And then it's going to leave. So once water leaves, we're going to get a stable tertiary carbocation, or relatively stable. It turns out that this carbocation is going to rearrange because it could form something more stable. And the way it's going to rearrange is by means of a methyl shift. So this methyl is going to trade places with the carbocation. So now the methyl is on the right side, and we have a carbocation on this carbon. That is the carbon that has the OH group. The OH group can act as an electron donating group. It can donate a pair of electrons and stabilize the carbocation. So now the carbon won't bear the positive charge, the oxygen will. And it turns out that oxygen can bear a charge better than carbon, and that's why the rearrangement occurs. So now we have an oxygen with a hydrogen and a positive charge. This reaction is known as the Pinnacle rearrangement reaction. So now water is going to take away a hydrogen so that oxygen no longer has the positive charge. And as you can see, C is going to be the answer. We're going to get a ketone after the methyl migrates to a different carbon. 85. Which of the following statements is false? Well, let's start with answer choice A. Compounds 1 and 2, are they diastereomers? True or false? Well, let's see. This fluorine atom is in the axial opposition, and the same is true for that one. So the chiral center there does not change. If we look at the next fluorine atom, it's in the axial down position. Here it's in the equatorial position. So as we can see, the second chiral center changed, but the first one didn't. When some chiral centers change, but not all, what we have is a case of diastereomers, which means that A is a true statement. Since we're looking for the false statement, we can eliminate answer choice A. Another way in which you can analyze it, notice that this fluorine is in the up position, this one is in a down position, which means that we have the trans isomer, and here it's in the up position, and this is in the equatorial up position, so that's the cis isomer. Cis-trans geometric isomers are also known as diastereomers when they have chiral centers. Now what about B, compounds 2 and 4? Compound 4 is a cis isomer. This is down and that's down. They're in the same direction. So 2 and 4 are cis. Looking at compound 3 is trans. This is down, that's up. So that's the trans isomer. It turns out that two cis isomers are indeed meso compounds. There's only two ways to draw a cis isomer. Since both fluorines are in the up position for compound 2, we're going to put both of them towards the front. Let's choose up to represent the front and down to represent the back. So for compound 4, both fluorine atoms are in the down direction. We really don't need the absolute configuration. The relative configuration will be enough to get the right answer. So those are the only two ways in which we could draw the cis isomer. And as you can see, there's a line of symmetry. So even though we have two chiral centers, the molecule has the plane of symmetry, which means that these are meso compounds, which means compound 2 and 4 are the same molecule. They're identical to each other. So B is a true statement. 2 and 4 are meso compounds. Now, for compounds 1 and 3, let's draw it this way. So we've chosen to make the group that's up to be in the front and the one that's down to be in the back. So this is what we're going to have. And compound 3 is the reverse. The first fluorine atom is facing in a downward direction, so it's in the back. And the second one is facing in the equatorial up position, so it's going to be in the front. Now let's move on to answer choice C. Compounds 1 and 3, are they enantiomers? So notice that compound 1 doesn't have a line of symmetry, and the same is true for compound 3. There is no line of symmetry. And also, all of the chiral centers change. This chiral center, it flips because the fluorine was in the front, now it's in the back. And this chiral center changes as well. If all chiral centers change, and if there's no line of symmetry, then the two compounds will represent enantiomers. So C is a true statement, which means D has to be the answer. Now looking at 3 and 4, we have the trans isomer and the cis isomer. Cis-trans isomers are always diastereomers. As you can see, one chiral center remained the same, but the other one was changed. Whenever some chiral centers stay the same, but some change, you have a case of diastereomers. So 3 and 4 are not identical molecules. They're diastereomers. So that means D is a false statement. Now, let's focus on compound 1. Compound 1 had a fluorine in the axial up position and one in the axial down position. And we redrew the molecule like this. We chosen the axial up position to be in the front and the axial down position to be in the back. Now, even though the relative configuration is what's really important, are these two molecules the same? Well, let's find out by analyzing the absolute configuration. Let's see if the chiral centers represent the R configuration or the S configuration. So let's start with the fluorine on the right side. If fluorine's in the front, that means H is in the back. So fluorine has a higher atomic number than carbon. So this is going to be group number 1. This carbon has more priority than this one because this carbon has a fluorine. And so this is going to be group number 2, this is number 3, H is number 4. So we're analyzing this chiral center. Because H is already in the back, we can count it from 1 to 2 to 3. So this is going clockwise, which means we have the R isomer. Now let's move on to the next chiral center. Let's analyze this one. So if fluorine's in the back, that means H is in the front. So this is going to be number 1, 2, 3, 4. Counting from 1 to 2 to 3, this is going counterclockwise, so it's S. But we need group number 4 to be in the back, and H is in the front, So we got to reverse it, which means that it's R. So both chiral centers are in the R configuration. Now, with Newman projections, it could be quite tricky. Let's see if we can get the R configuration. Let's focus on this chiral center first. Let's draw the hydrogen. If the fluorine is in the axial up position, H is in the equatorial down position. And if fluorine is in the axial down position, H is in the equatorial up position. So focusing on this chiral center, we have a carbon, a fluorine, and a hydrogen. Let's say we're looking down at this portion of the molecule. Then this portion which extends from it, that must represent the front. This is one way I like to analyze it, and for me, I find that it works. Now we know that fluorine is number 1. This carbon is number 2 because that carbon has the fluorine. This is 3 and this is 4. So number 2 is in the front. We use that circle method that we've used in earlier problems. So I'm going to put a little F here to represent that it's in the front. 1 is above it, 3 is to the left, 4 is to the right. Now we need to rotate the molecule. We want to get 4 above the 2. So we need to move the 1 and get 4 in its position. So let's rotate it counterclockwise. So now 4 is at the top, 1 is on the left side, 3 is on the right side. And now we're going to flip the molecule in such a way that 4 is going to kick out group number 2. 1 and 3 are going to flip to the top. So 4 is in the front, 2 is below it, and 1 and 3 are at the top. So if we count it from 1 to 2 to 3, this appears to be the S isomer since it's going counterclockwise. But because 4 is in the front, we need to reverse it to put it in the back. So this will give us the R isomer, which is what we have. So now let's get rid of a few things. So now we're going to focus on this chiral center. So we have, that's the chair conformation, we have a fluorine atom, and we have a hydrogen. And then we have this other line, which is this line here. If you view this part, like if you look straight down at it, then this group has to represent what's in the back. So here's what's important. When analyzing this chiral center, this line represents what's in the front. When analyzing this particular chiral center, this line represents what's in the back, if you look at it in towards that direction. So is it going to be R or is it going to be S? So fluorine is number 1. This carbon is number 2 because it bears the fluorine atom. This one is 3 and H is 4. So once again, we're going to put 2 in the circle. But what's in the circle represents what's in the back. So we don't need to reverse it. So we have 3 on this side, 4, and 1. We need 4 to be just above the 2. So let's move the 4 here. And let's rotate this molecule. So now the 4 is at the top, 3 is still on the left, 1 is on the right. And now what we're going to do is we're going to flip it. So 4 is going to displace 2. So 4 is in the center, 2 is below it, 1 and 3 at the top. And then if we count it from 1 to 2 to 3, it's R. And what's in the circle represents what's in the back. So we don't need to reverse it. So therefore, these two structures are indeed equivalent to each other. 86. What is the IUPAC nomenclature of the molecule shown below? So the way we should number it is the double bond has to be given the highest priority. So we don't want to name it this way. We want to put the 1 with the methyl so we can get the lowest number. So 1, 2, 3, 4, 5, 6. We want to count it that way. So we get the methyl on carbon 1, the bromo on carbon 3, and the chlorine on carbon 5. Now, if we were to count it, let's say, this way, the methyl will be on carbon 2, the chlorine on 4, the bromine on 6. And that would lead to higher numbers, so we don't want to do it that way. So we have a 3 bromo, so we could get rid of answer choice B and answer choice C. And then 5 chloro, 1 methylcyclohexene. Now B comes before C, so we got to put bromo before chloro, which means we can eliminate answer choice D. So A is the answer. It's going to be 3 bromo, 5 chloro, 1 methylcyclohexene. 87. Which molecule is equivalent to the Fischer projection shown below? So how can we figure this out? The best thing that we can do is see which answer choice matches this Fischer projection. But we need to find the absolute configuration of it first. So let's start with this chiral center. Bromine is going to be group number 1. It has the highest priority. This R group is number 2. This carbon has more priority than the methyl group because the carbon at the bottom has the chlorine atom. So this is group number 2, this is number 3, and H is number 4. And since we're dealing with a Fischer projection, the hydrogen is going to be in the front, so we have to reverse it. So if we count it from 1 to 2 to 3, ignoring 4, it's rotating clockwise, which means this is the R isomer, but we have to reverse it since group number 4 is in the front. We want it to be in the back. So what we really have is the S isomer. So let's put S. Now let's move on to the next chiral center, which is this one right here. So we can see that chlorine has the highest atomic number. Now comparing these two carbons, this one has the bromine, so it's going to be group number 2, this is number 3, H is number 4. And keep in mind, you need to compare one atom at a time. The reason why chlorine is number 1 is because you're comparing chlorine with carbon, not with bromine. So you compare the first atom with the first atom. Bromine is the second atom relative to this chiral center. So you can't compare it directly with chlorine. So counting it from 1 to 2 to 3, we're rotating it in the clockwise direction, that's R, but we got to reverse it since H is in the front. So it's going to be S. So both chiral centers has the S configuration. Now let's analyze the Newman projections. Let's start with answer choice A. So bromine has the highest atomic number, so it's going to be group number 1. H is number 4, the methyl is number 3. Now this chiral center, that carbon is attached to a carbon that's on the back, which is really this group here. We're analyzing this chiral center, that's the carbon with the Br. And this other group, the chlorine atom, that group is in the back. So we'll call it group number 2. So let's use the circle method. So 2 is in the back. We can see 3 is at the top. 4 is on the left. And 1 is on the right. So when dealing with Newman projections, when you're analyzing the chiral center at the front, the other group, the one that you don't see, is in the back, which is this group. Now, if you're analyzing this chiral center, in a Newman projection, that group is in the back. So this group, which is this carbon here, that's in the front. As long as you understand that, then it won't be too difficult to find the absolute configuration when you have a molecule in a Newman projection. So right now, 2 represents what's in the back. So I'm going to put a B. So let's move 4 to the top. Let's rotate the molecule clockwise. So now let's flip the molecule. So 4 is going to kick out 2. 1 and 3 are going to flip to the top. So now we have group number 4 in the back. And so we can count it from 1 to 2 to 3. So this is the S isomer. So let's put an S. Now, notice that for answer choice A, carbon 2 has the same 3 groups as answer choice B. It has a hydrogen, a methyl, and a bromine in the same order, which means that carbon 2 has the same configuration. For answer choice B, it's S. Now, if we look at answer choice C relative to A, the hydrogen is in the same position. However, the methyl and the bromine atom, they're switched, which means that the configuration changes. So it's going to change from R to S. It's going to change from S to R. Take that back. Now, for the sake of practice, we can go ahead and confirm that answer. So let's do that. Bromine is going to be number 1. H is number 4. The methyl is number 3. The carbon in the center, that's number 2. Well, not that carbon, but the carbon that's behind it. That's group number 2, which is really this group here. Keep in mind that carbon's in the back. So let's put 2 in a circle. And then we have 1, 4, and 3. So let's rotate it clockwise. And then let's flip the molecule. So it's 1 to 2 to 3. And group number 4 is already in the back, so this is the R isomer, which is what we have. Answer choice C and D both have the R isomer for carbon number 2. As you can see, if you look at carbon number 2, they have the same groups. The H, the methyl, and the Br, they haven't changed relative to each other. So carbon 2 has the R configuration for answer choice D. Now, we want only the S configuration. So therefore, we can eliminate answer choice C and D. We don't have to consider them anymore at this point. So now we need to focus on A and B. We need to know which one has the S isomer for carbon 3. This is carbon 1, 2, 3, 4, and 5. So let's start with answer choice A. So we're going to look at carbon 3, which is basically this chiral center. It has a chlorine, a hydrogen, and an ethyl group, which we can see here. Now, it's attached to this group, and that group is basically the front carbon. So keep that in mind, which means we're going to have to reverse it. So chlorine is number 1. The carbon that is in the front, the back carbon, carbon 3, which is the chiral center that we're analyzing, is attached to carbon 2, which is in the front. And that carbon, the priority is number 2, because comparing ethyl with a carbon that has a bromine, the carbon with the bromine wins. It has more priority. The ethyl is group number 3, H is number 4. So keep in mind, number 2, which is in a circle, now represents what's in the front, because we're analyzing the carbon in the back, and it's attached to the carbon in the front. The carbon in the front is carbon 2, the carbon in the back is carbon 3. So be careful to avoid mixing the priority numbers with the carbon numbers in the chain. Somehow you have to distinguish those two, because it can get quite confusing. So we have 1 on this side, we have 4 and 3. I'm looking at these numbers. We want 4 to be on top, so we're going to rotate it counterclockwise slightly. So we want 4 to be on the top, 1 is over here, 3 is over here. And then let's flip the molecule. 4 is going to kick out 2, and then 1 and 3 are going to be on the top. So going from 1 to 2 to 3, that's counterclockwise, that's the S isomer, but group number 4, which is in the circle, is in the front. And we want it to be in the back, so we got to reverse it, which means this is R. So therefore, we can eliminate answer choice A, because both chiral centers must be S. So the answer has to be B. But let's analyze it. So let's analyze carbon 3. Carbon 3, as we mentioned before, has a Cl, a hydrogen, and an ethyl group. And carbon 3 is connected to carbon 2. Carbon 3 is the back carbon of the Newman projection, and carbon 2 is the front carbon. So once again, we're going to put carbon 2 in a circle. Now let's rank every group. Chlorine is going to be group number 1. Carbon 2 is group number 2. Carbon 2 has the bromine atom. It has more priority than the ethyl group. So I'm going to put group number 2 right there. So keep in mind, we're analyzing chiral center, which is carbon number 3. And carbon 3 is attached to carbon 2, which is basically that whole group. And not carbon, it's in the front. So carbon 2 is group number 2. Group number 1 is Cl. Ethyl is number 3. H is group number 4. So we're going to put 2 in a circle. Group number 2 is carbon 2, which represents the stuff in the front. This is 3, this is 4, and this is 1. We're going to rotate it this way. So 4 is at the top, 3 is over here, here's 1. And then we're going to flip it. So going from 1 to 2 to 3, we can see that it's R. But we need to reverse it because group number 4, which is in a circle, and what's in a circle represents the front, but we want number 4 to be in the back. So once we reverse it, it's going to be S. It's going to be going counterclockwise. So as we can see, for answer choice B, both chiral centers has the S configuration. Number 88. Which molecule has the highest boiling point? So what you need to know is that alcohols have higher boiling points than alkanes, because alcohols have hydrogen bonds. So we can eliminate answer choice B and C. Now, if you have 2 alcohols, the one that has more carbon atoms will be the one with the higher boiling point. So the correct answer is D. The more atoms a molecule has, the reason why it has a higher boiling point is because there are more London dispersion forces. If the intermolecular forces of a molecule increase, the boiling point will increase. So intermolecular forces include dipole-dipole interactions, hydrogen bonds, and London dispersion forces. If we had to rank them, D is going to have the highest boiling point. It has the most number of carbon atoms, and it has hydrogen bonds. The second one is answer choice A. It's going to have the second highest boiling point due to hydrogen bonds. Now, which one has a higher boiling point, B or C? Because they both contain 5 carbon atoms. They both have the formula C5H12. Pentane and neopentane are isomers of each other. It turns out that straight chain alkanes have a higher boiling point than branch alkanes. So this one has the lowest boiling point. 89. Which solvent works best for the reaction shown below? So the first thing that we need to do is that we need to determine what type of reaction mechanism that we're dealing with here. Is it an SN1 reaction, SN2, E1, or E2? Well, no double bonds were formed, so it can't be an E1 or an E2 reaction. Those reactions produce alkenes. So it's a substitution reaction. Is it an SN1 reaction, or is it an SN2? We know it's a substitution reaction because bromine was substituted with the NH2 group. It was replaced by it. The answer lies in the fact that we have a tertiary alkyl halide. Tertiary alkyl halides favor SN1 reactions and not SN2 reactions. Now, the second thing that we need to look at, now that we know we have an SN1 reaction, is the solvent. What type of solvent works best for an SN1 reaction? SN1 reactions work well with polar protic solvents. All of the solvents listed in each of the answer choices are protic solvents. They all contain hydrogen bonds. They have OH groups. But the second requirement is that the solvent has to be polar, in addition to being protic. So all solvents are protic, but which one is most polar? It turns out that as the polarity of the solvent increases, the rate of the reaction will increase if the reactants are neutral, uncharged. Ammonia is neutral, and the alkyl halide is neutral as well. So which solvent is most polar? You need to know that water is more polar than methanol, and methanol is more polar than ethanol. The OH bond is highly polar. The carbon-hydrogen bond is nonpolar. So ethanol is the least polar because it has more carbon-hydrogen bonds. So methanol is preferred over ethanol. So we can eliminate answer choice A and B because it contains ethanol in it, and ethanol is the least polar. Now looking at C and D, answer choice C is the answer because we have more water, less methanol. And water is more polar than methanol. So therefore, this is the answer. 90. What is the major product of the reaction shown below? So we have an epoxide. We're going to react it with sodium methoxide and methanol. Now, what you need to know is that when you react an epoxide with a nucleophile under basic conditions, the mechanism is going to be an SN2 reaction. So as a result, the nucleophile is going to attack the more accessible carbon. That is the carbon that is less substituted. So out of the two carbons that are part of the epoxide, it's going to go for the secondary carbon as opposed to a tertiary carbon. If you recall, SN2 reactions work better with secondary substrates as opposed to tertiary substrates. The secondary substrate is more accessible to the nucleophile. So methoxide is going to attack from the back, causing this bond to break. Now, we have to be very careful with the stereochemistry. The methyl does not participate in the reaction, so the stereochemistry of the methyl remains the same. Now, the oxygen is attached to the carbon or to the ring in two locations, here and here. The bond between the oxygen and the tertiary carbon is unaffected in the reaction, so that part has to remain the same. Now, at the secondary carbon, that's where the SN2 reaction is taking place, so we're going to have inversion of configuration. The carbon-oxygen bond is in the front, and methoxide attacks from the back. So the OCH3 group is going to be added to the back. The hydrogen that was in the back will now be flipped to the front due to the inversion of the SN2 reaction. So this is what we're going to have. Now the last thing that's going to happen is the oxygen with a negative charge is going to grab a hydrogen, turn it into an alcohol. So which one is the correct answer? Well, let's analyze. So the methyl group is in the back, which means we can eliminate answer choice D because the methyl group is in the front. Now looking at the oxygen is on the tertiary carbon. In answer choice C, the oxygen is on the secondary carbon, so we can eliminate answer choice C. Now the methoxy group, the OCH3 group, is on the secondary carbon, but it's in the back. We can eliminate answer choice A because it's on the front on the secondary carbon. So B is the correct answer. The methyl is in the back, the OH is in the front on the tertiary carbon, and the OCH3 group is in the back on the secondary carbon. So B matches the answer that we have. 91. What is the major product of the reaction shown below? So we have the same epoxide, and we're going to react it with methanol again, but this time under acidic conditions as opposed to basic conditions. Now the mechanism for this reaction is not purely SN1, nor is it purely SN2. The first thing that's going to happen is the oxygen is going to grab a hydrogen. And so I'm going to put that here instead of redrawing it. So the oxygen is going to have a positive charge. Now, what you need to keep in mind is that you can draw the resonance form where this bond is going to break, and that will lead to an intermediate, a carbocation intermediate, where the plus charge is on a tertiary carbon. But what you need to understand is that the resonance hybrid is in between the two. So because the resonance structure is a tertiary carbocation, we know that the tertiary carbon has a significant amount of partial positive charge. So this bond is relatively weaker and easy to break. Now the methanol has an oxygen with a partial negative charge, and so it's attracted to the carbon that has a partial positive charge. So like in SN1 reaction, the nucleophile is going to go for the tertiary carbon, but we don't fully get a carbocation because the oxygen, if we were to form the carbocation first, the oxygen could just connect back to it. So instead, the oxygen always maintains some contact with that partially positive carbon. Now the methanol is going to attack it. And because it attacks from the back like in SN2 reaction, we're going to have inversion of configuration. But like in SN1, it goes for the tertiary carbon and not the secondary carbon. So that's why it's not purely SN1 and not purely SN2. So keep this in mind. Under basic conditions, this reaction is like an SN2 reaction where the nucleophile attacks the less substituted carbon. Under acidic conditions, it's going to attack the more substituted carbon, but with inversion of configuration. So now let's draw the product that we have at this point. So this hydrogen did not participate in the reaction, so it's going to have the same configuration. Now the carbon-oxygen bond is going to break, but the carbon-oxygen bond that is attached to or part of the secondary carbon, that's going to be unaffected. So therefore, that bond is still intact. So the OH group is still going to be in the front on the secondary carbon. Now we have inversion of configuration at the tertiary carbon. So the methanol attacks from the back. The oxygen was in the front. So the methanol is now going to be in the back. The methyl group, which was in the back, due to the inversion of configuration at the chiral center, the methyl group is now going to be in the front. So now all we need to do is take another methanol molecule and remove the hydrogen. And so now we have the answer. So the OCH3 group is in the back. The methyl is in the front. We have an OH in the front. And then the H is in the back. So the only answer that corresponds to what we have here is answer choice D. As we could see, the methoxy group is on a tertiary carbon, and it's in the back. The methyl is on the tertiary carbon, it's in the front. The OH is on a secondary carbon, and it's in the front. So only answer choice D matches the answer for this problem. Number 92. Which of the following reactions will not work? Is it going to be A, B, C, or D? So take a minute and pause the video. Write out the mechanisms for this reaction and find the one that will not work, or the one that doesn't have the right products. So let's go ahead and begin. Let's start with answer choice A. So we have an ether. We have a tert-butyl on one side and an isopropyl group on the other side. And we're going to react it with HBr. So when dealing with ethers under acidic conditions, what we need to find out is we need to determine if this reaction will work by an SN1 mechanism or an SN2 mechanism. The carbons that are attached to the oxygen include a tertiary carbon and a secondary carbon. Tertiary carbons favor SN1 reactions, and secondary carbons favor SN1 reactions, particularly if you have a protic solution. In this case, it's acidic, so it's definitely protic. So the mechanism is going to be predominantly SN1. For an SN1 reaction, a bromine, or the bromide ion, is going to attack the more substituted carbon, that is the tertiary carbon, under SN1 conditions. Under SN2 conditions, it would attack the less substituted carbon, but under SN1 conditions, it's going to attack the more substituted carbon. So the first thing that's going to happen is the oxygen is going to be activated by a hydrogen. So under acidic conditions, the first step is protonation. Now, what do you think is going to happen next? Once oxygen have a positive charge, it becomes a good leaving group. So the carbon-oxygen bond is going to break. The molecule will split into two parts. So we're going to have a relatively stable tertiary carbocation and isopropyl alcohol. At this point, the bromide ion is going to combine with the tertiary carbocation. And that's why the bromine atom attacks the more substituted carbon, is because tertiary carbocations are more stable than secondary ones. And these will be the products of this reaction. So answer choice A is not the answer, but it's correctly written. It's a true statement. We're looking for the false statement, or the reaction that will not work. So now let's move on to answer choice B. So we have ethyl methyl ether, and we're going to react it with another acid, HI, hydroiodic acid. So just like before, the first step is protonation. Now we need to know what kind of mechanism we're dealing with. Is it going to be SN1 or SN2? The mechanism is SN2. If we look at the carbons, on the right side we have a primary carbon. It's very difficult to form a primary carbocation, so this is going to favor an SN2 reaction. On the left side we have a methyl carbon. Methyl carbocations and primary carbocations are unstable, so an SN1 mechanism will not work here. So after protonation, we can't break a carbon-oxygen bond because we're going to get an unstable carbocation intermediate. So instead, the nucleophile is going to attack it at this point. Now, because we're dealing with an SN2 reaction, iodide is going to attack the most accessible carbon, and that is the methyl carbon. The methyl carbon is more accessible than the primary carbon. So once it attacks it, the carbon-oxygen bond will break without forming an unstable carbocation. So we're going to get methyl iodide and ethanol. So as you can see, under SN2 reaction conditions, the nucleophile attacks the less substituted carbon. Under SN1 conditions, it will attack the more substituted carbon. So the same is true for epoxides, as we've seen in the last two problems. So answer choice B is a true statement, which means it's not the answer. Now let's move on to answer choice C. So we're going to react it with HBr, excess HBr. That means all of the oxygens that you see here will be replaced with bromine atoms. So by looking at the products, you can tell that answer choice C is not a true statement. It's a false statement, because this is not going to be the final product. This is going to be an intermediate, but the OH group will eventually turn or be replaced with a bromine atom. So answer choice C is the false statement, which means answer choice C is the answer. But let's go over the mechanism. So the first thing that's going to happen is protonation. This oxygen is going to grab a hydrogen. Now, this carbon is secondary. This one is primary. There's many mechanisms that can occur here. We can get an SN2 mechanism where the bromide attacks a primary carbon. That can happen. Or we can get an SN1 mechanism where the carbon-oxygen bond breaks. Because both can occur, and because we're using excess HBr, it really doesn't matter what order you do it because the final result will be the same. The best thing is really the speed, whichever one occurs faster. So carbocations take time to form. It takes energy to ionize a molecule and to generate ions. So usually the SN2 reaction is faster than the SN1 reaction. But they can both occur in this example. But let's go with the SN2 reaction. The bromide ion is going to attack the primary carbon since it's more accessible than the secondary carbon. And a carbon-oxygen bond is going to break. So we're going to get isopropyl alcohol initially, and we have this as well. Let's focus on this molecule. So now the primary alcohol will be protonated with another HBr molecule because we have plenty of it in the solution. It's excess. And the OH is going to turn into a good leaving group. Now, because the oxygen is attached to a primary carbon, it's not going to leave and form an unstable primary carbocation. It's not going to work by an SN1 mechanism. Instead, the bromide is going to attack from the back in an SN2 reaction, expelling water. So as you can see, one of the products has 2 bromine atoms. Now, isopropyl alcohol will react with HBr. So as in the case of the other reactions, first we need to add a hydrogen to the OH group. And so it's going to turn into a good leaving group. Now, because the oxygen is attached to a secondary carbon, this is going to favor an SN1 reaction as opposed to an SN2 reaction, especially under protic conditions. So we're going to get a secondary carbocation, and then the bromide ion is going to attack. And so this is the other product that we're going to get. So going back to answer choice C, whenever you're adding HBr to this compound, especially if it's excess, any OH that you see or any ethers that are present in its molecules, any alcohols or ethers, will be cleaved, well, the ethers will be cleaved, and any alcohols will be replaced with bromine atoms. So your final product shouldn't have any oxygen atoms. They should all be replaced with a bromine atom. So wherever you see an oxygen atom, put a bromine atom. This carbon is attached to an oxygen atom. So we're going to have to put a bromine atom. So the ether will be cleaved here and here. Now this carbon has an oxygen atom, and the same is true for that one. So at both of those positions, we need to put a bromine atom. And that's how you can quickly see what the product is going to be. So for example, let's say if we have a molecule that looks like this. So the bond will break here, 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 and here. Let's react it with excess HBr. So identify the carbon atoms that are attached to an oxygen atom. We have 1, 2, 3, 4, and 5. At each of those positions, we're going to put a bromine atom. And wherever you see a green line, you need to break the connection. So we're going to have a bromine atom here, 2 bromine atoms on that molecule, 1 bromine atom here, and another one here. So as you can see, that's going to be the product of the reaction if you add HBr, excess HBr, to that compound. So answer choice C is the correct answer. But now let's go over the mechanism of answer choice D. So what we have here is anisole. You can also describe it as methylphenol ether. And let's react it with HI. So will the iodide ion, will it attack the phenyl ring or the methyl group? The nucleophile will never attack the phenyl ring. It can't work for an SN1 or an SN2 reaction. Whenever you have an aryl halide, or let's say a leaving group attached to a benzene ring, the SN1 and SN2 reactions, they won't work for aryl halides, the same way they don't work for vinyl halides. So iodide is not going to attack the benzene ring, at least not in a SN1 or SN2 mechanism. The first thing that's going to happen, as usual, the oxygen is going to grab a hydrogen, making the oxygen a good leaving group. Once that happens, we can't get an SN1 reaction. This bond is not going to break because methyl cations are very, very unstable. So instead, this is going to be an SN2 reaction. The iodide is going to attack the methyl from the back, causing the carbon-oxygen bond to break. So this will give us phenol, and we're going to get methyl iodide. So even if we add HI under excess conditions, HI will not react with phenol. Let's assume that it did. Let's just see what's going to happen. If we add a hydrogen to the oxygen and turn the OH group into a good leaving group, we'll have this. Let's say if water were to leave, we would have an unstable aryl cation. Having a plus charge on a double bond is not good. So water won't leave. This is not going to happen. It's very, very difficult to make that happen. So under normal circumstances, this process won't occur. So phenol is always going to be your product whenever you have a benzene as part of the ether. So the nucleophile is going to attack the other carbon. So keep that in mind. Even if you use excess HI, the OH in the benzene ring will not be replaced with an iodine atom. Number 93. What is the product of the reaction shown below? So which of these alkenes will we get? As you can see, there's many to choose from. So the first thing we need to realize is that we have basically a tertiary alkyl halide. The carbon that has the bromine atom, that carbon is attached to 3 other carbons, which means it's tertiary. And we're using a strong base. A tertiary alkyl halide with a strong base will favor an E2 reaction. In an E2 reaction, the base, which is hydroxide, is going to eliminate a hydrogen and a bromine atom. So therefore, our answer should only contain 2 phenyl groups and 2 methyl groups. So that alone will eliminate 2 answers. We can eliminate answer choice C because it has a bromine atom, and D, it doesn't have 2 methyl groups. The hydrogen is still there when it should be eliminated. So we're between A and B. So are we going to get the trans isomer or the cis isomer? Which one? Now this is where we got to focus on the stereochemistry of the E2 reaction. The hydrogen and the bromine atom, they have to be anti with respect to each other. So notice that the hydrogen is in the back and the bromine is not in the front. The methyl is in the front. So we need to trade places. We need to switch the methyl group with the bromine. And here's how you can do it. What you need to do is you need to rotate the molecule. So the methyl is going to move to where the phenyl is located. The bromine atom is going to take the place of the methyl, and the phenyl is going to take the place of the bromine atom. And you have to do it in order. So the left side is going to be the same. Let's redraw it. And on the right side, we're going to have the same symbols, but now methyl is in the place of the phenyl group. The bromine atom has taken the place of the methyl group, and the phenyl group has taken the place of the bromine atom. So this is what we now have. So hydroxide is going to grab the hydrogen from the back, form a double bond, and expel the bromine atom that's in the front. So before you eliminate H and Br, make sure that these two are on opposite sides. So if the H is in the back, make sure the bromine atom is in the front. And you can look at the dash and the wedges based on that. So once we eliminate it, notice what we have. The methyl group, we have one in the front and another one in the back. So therefore, they're trans with respect to each other, which means the phenyl groups are also trans. And you can see that they're on opposite ends. But you should base your answer on the methyl groups because you can clearly see that one is in the front and one is in the back based on the dash and the wedge. So therefore, the correct answer is the trans isomer. So A is the right answer. 94. What is the major product of the reaction shown below? So we have a sawhorse projection, and we still have a tertiary alkyl halide with a strong base. So it's going to be an E2 reaction. And we know that C and D can be eliminated. The bromine atom shouldn't be there, and we should still have two methyl groups. So once again, the answer is going to be between A and B. Now we need to adjust this molecule. The two positions that we need are these two positions. The phenyl is clearly in the top, the methyl is at the bottom. Those two positions are anti with respect to each other. So we want the hydrogen and the bromine atom to be in those two positions. So what we're going to do is we're going to rotate this molecule this way first. Let's get the bromine atom. Let's put it on the top. So the bromine atom is going to take the place of the phenyl group. The phenyl is going to take the place of the methyl group. And the methyl is going to take the place of the bromine atom. Now we want the hydrogen to take the place of the methyl group, so it will be anti to the bromine atom. So what we're going to do is we're going to rotate it in this direction. So now the hydrogen has replaced the methyl group, the methyl has replaced the phenyl group, and the phenyl has replaced the hydrogen. So now H and Br are opposite to each other. They're anti with respect to each other. And once they're in this 180 degrees apart, now the base can abstract the hydrogen and expel the bromine atom. So hydroxide is going to come in, grab the hydrogen, the carbon-hydrogen bond will break, those two electrons in the CH bond will be used to form the pi bond, and the leaving group will leave. So we're going to get a double bond. The question is, where are the methyl and the phenyl groups relative to each other? So in a situation like this, you don't want to look at the phenyl and methyl groups in terms of which one is up and which one is down. Rather, view it this way. You want to know which one's on the left and which one's on the right. The phenyl group is on the left, and here the methyl is on the right. Here, the methyl is on the left and the phenyl is on the right. If the methyl groups were both on the right, it's going to be cis. But because we have a methyl group on the left and one on the right, it's trans. So this is the one on the left, and this is the one on the right side. So this is the left side, this is the right side relative to the double bond. Now, the phenyl on the left is over here. It's to the left of the alkene, and this one's on the right, so it's over here. So as you can see, we have the trans alkene, so A is the answer once again. 95. What is the major product of the reaction shown below? So we have a secondary alkyl halide. This carbon is attached to two other carbons, and we have a strong base. So this is another E2 reaction. So we need to know which hydrogen the base can remove. So bromine is in the axial down position, which means that hydroxide can remove a hydrogen that is in the up position. It can only remove a hydrogen that is one carbon away. So that is on one of those carbons. Now, this hydrogen is not in the up position, it's in the equatorial down position. In order for the hydroxide to remove the hydrogen, it has to be in the up position because bromine is in a down position. So therefore, this hydrogen is not anti with respect to the bromine atom. So the base is not going to go for it. Now this hydrogen is in the up position. So the base is going to go for this hydrogen. It's not going to go for the isotope of hydrogen, which is deuterium, because that's in a down position. So it's not going to remove that. So now let's write the mechanism. So hydroxide is going to grab the hydrogen, form a double bond, and expel the bromine atom. So let's convert from a chair conformation to this structure. So let's say that carbon 1 is the carbon with the methyl. Carbon 2 is the one with the bromine atom. Carbon 3 is the one with the deuterium atom. We're not trying to name it. We're just using these numbers as a reference. So this is carbon 1, 2, and 3. Notice that the deuterium atom is on carbon 3. And notice where the double bond is located. The double bond is formed between carbons 2 and 3, which means it's here. Therefore, the correct answer is answer choice A. It can't be B because hydrogen was removed. So this hydrogen was eliminated. And it's not going to be C because the double bond was not formed between 1 and 2. We couldn't get rid of this hydrogen. And for D, we can't form a double bond here because the bromine is nowhere in that region. So therefore, only answer choice A makes sense. 96. Which of the following molecules has the highest dipole moment? So basically, which molecule is most polar? The carbon-fluorine bond is highly polar. Carbon has an electronegativity value of 2.5, and for fluorine is 4.0. The difference between these two values is 1.5. The dipole moment points towards the more electronegative fluorine atom. Because fluorine is more electronegative, it bears a partial negative charge. Carbon bears a partial positive charge. So if we draw the dipole moment for answer choice B, notice that the arrows, they point in opposite directions, which means that they cancel. So the net dipole moment is 0, which means B is nonpolar. We're looking for the molecule that's polar, that has a net dipole moment. So basically, if a molecule has symmetry, it's going to be nonpolar. Notice that we have a line of symmetry here. These two are directly opposite to each other. If you look at answer choice A, there's a line of symmetry. These two reflect across the line, and the same is true for those two, and then those two as well. So therefore, A is going to be nonpolar. If you draw the dipole moments, these two are opposite to each other, so they will cancel. And then these two are opposite to each other. They cancel as well. And these two are opposite to each other. So therefore, the net dipole moment is 0. So A is eliminated. For answer choice C, we can draw a line of symmetry here. These two reflect across it, and this is directly in the middle. So that's nonpolar as well. Now, to draw the dipole moments, you got to be careful with this one. So we have an arrow going this way, we have an arrow going that way, and another one going this way. So do they cancel? Well, we need to jump into physics a little. So these three fluorine atoms are separated by 120 degrees. So we got a vector that is going in a positive y-axis, another vector that's going at an angle, and another one that's going at another angle. The one on the right, you can break it down into its x and y components. It has a y component that goes in a negative y direction. The x component goes in a positive x direction. Now for the vector on the left, it has a y component that goes down and an x component that goes to the left. Notice that the x components, they cancel. And these two small y components cancel with this larger vector that's going in the positive y direction. They're opposite to each other. So basically, the vectors, the dipole moments, they completely cancel. The net dipole moment for this molecule is 0. Now looking at answer choice D, there's no line of symmetry that we can draw. Well, maybe we can draw it here. I guess you could say this is symmetrical from each other, but if you draw the dipole moments, it's not going to be nonpolar, it's going to be polar. Here's why. The dipole moments, they don't cancel. We have one going this way, another one going this way, and another one going this way. The net dipole moment is in a positive y direction. Now, the one on the left and the one on the right, they partially cancel, but not completely. So we have three vectors, one going up, one going this way, and another one going this way. So we can break it into x and y components. So we can see that the x components cancel, but the y components, they all point in the same direction. That is in a positive y direction. So that's where the net dipole moment is. So answer choice D is the answer. It's the molecule that is most polar because it has the largest dipole moment. Everything else completely cancels. So even though the other three answers have polar bonds, the carbon-fluorine bond is polar, the entire molecule as a whole is nonpolar because the dipole moments cancel. So answer choice D is the answer. At high temperatures, a large alkane molecule can decompose into a smaller alkane and alkene by a homolytic bond cleavage of its carbon-carbon bonds. Which molecules are most likely to form from the free radical disproportionation reaction shown below? Is it going to be A, B, C, or D? So what exactly is a homolytic bond cleavage? A homolytic bond cleavage is where the bond breaks and both atoms get an electron. So because the two carbon atoms are similar, they share the same electronegativity. When the bond breaks, they both will gain one electron. So homolytic bond cleavages forms radicals. And so this is what we're going to get. Now what about a heterolytic bond cleavage? Let's say if we have a carbon and a bromine atom. Because bromine is more electronegative than carbon, when the bond breaks, bromine is going to take both electrons. And this leads to ionization. So the carbon will have a plus charge, that's the formation of a carbocation, and the bromine will have a minus charge. So anytime you're dealing with, let's say, an S1 reaction, the leaving group leaves, and you get a carbocation, this is an example of a heterolytic bond cleavage. Now let's say if carbon is bonded to an element that is less electronegative than itself, like hydrogen. In this case, when a bond breaks, carbon takes both electrons. And so this will produce a carbanion, and the hydrogen has a positive charge. So that's another example of a heterolytic bond cleavage. The element that's more electronegative takes both electrons with it. Now in this example, we have a homolytic bond cleavage, and we're going to generate two radicals. So we need to know which bond is going to break and which two molecules we're going to get. So for example, let's say if we break this bond here, Is that bond the most easiest one to break? If we break it, on the left side, we're going to have an ethyl radical. On the right side, we're going to have this radical here. So this is a primary radical and this is a tertiary radical. The bond that's going to break is the one that leads to the most stable radicals. A tertiary radical is much more stable than a primary radical. But is there a place that we can break the bond and get a more stable radical? Because primary radicals are not very stable. It turns out that there is. Actually, let me do this. So as we can see, if we break the line here, this will give us a primary radical and a tertiary radical. But let's say if we break it here, on the left side, we're going to get a radical that looks like this. That's a tertiary radical. And on the right side, we're going to get a secondary radical. It turns out that's the best location to break the carbon-carbon bond. There's no other places to break it that's going to give us the most stable radicals. If we break it here, we're going to get a methyl radical, which is not good. Same is true for here. If we break it here, that's a methyl radical, that's not stable. If we break it here, we get a primary radical, that's not good. But if we break it here, we get a secondary radical and a tertiary radical. So therefore, this bond is the most easiest one to break because it leads to the most stable radicals. So our answer should have a compound that has 3 carbons and another one that has 5. So we can eliminate answer choice B because we have an answer with 2 carbons. That can form if we break it here, but that's not going to be the major product because the primary radical is not as stable compared to the secondary radical. We can eliminate D because we have a compound with 4 carbons. We need one with 5 or 3. And we can eliminate C as well because this compound has 2 carbons. Answer choice A is the one that works. Here we have a 5-carbon alkene and a 3-carbon alkane. So that's the only one that matches the numbers that we have if we break it at this position, which leads to the most stable radicals. So answer choice A is the right answer. Now let's go ahead and propose a mechanism for this process. So let's start with 2,3,3-trimethyl pentane. And not in heat, we need to get 2-methyl, 2-butene, and in addition to that, we need to get propane. So we know that the homolytic bond cleavage will occur at the carbon or at the point where it leads to the most stable radicals, which this bond is the one that has to break. So when it breaks, each carbon will gain 1 electron. So it's going to produce 2 radicals. So we're going to get a tertiary radical. And in addition to that, we're going to get a secondary radical. Now, in order to form an alkene, we'll need to remove a hydrogen. So we need to remove this hydrogen. The alkene that forms is going to be between the hydrogen that is abstracted and the radical. The other radical, that is the secondary radical, is going to abstract the hydrogen. So this hydrogen will leave. It's going to take one of its electrons with it. That is one of the electrons in this bond. And it's going to form a carbon-hydrogen bond. So this hydrogen goes with this carbon. So now what can we do to form the alkene? The other electron in the carbon-hydrogen bond will be used to form the double bond. And so here it is. So that's the mechanism for this reaction. So that's how you can take a large alkane, use heat to get a smaller alkene and a smaller alkane. 98. Which reagent is needed to complete the reaction shown below? So what's going to happen if we use, let's say, hydrogen gas? What product will we get? Hydrogen gas will reduce the alkene into an alkane. The hydrogen will simply add across the alkene. So we're going to add 2 hydrogens, 1 to each of those carbons. Now it's important to understand that there already was a hydrogen to begin with, so now we have 2 hydrogens on each of those carbons. Now in addition to that, hydrogen gas will also reduce the ketone into an alcohol. It's not going to reduce the ester. The ester is less electrophilic than the ketone. So if you use hydrogen gas with palladium or hydrogen gas with the uranium nickel catalyst, it will reduce the alkene part of the molecule, the double bond, and the ketone, but not the ester. All we want to do is reduce the ketone, but not the alkene and not the ester. So therefore, hydrogen gas will not give us the product that we want. We don't want to reduce the alkene. So we can eliminate answer choice A. Now what about answer choice B? What's going to happen if we use lithium aluminum hydride? Lithium aluminum hydride is going to reduce the ester into an alcohol. Let's go over the mechanism for that process. Whenever aluminum has 4 bonds, it's going to have a negative formal charge, and lithium has a positive formal charge. So one of the hydride ions will attack the carbonyl carbon. So this will produce a tetrahedral intermediate. And this tetrahedral intermediate will immediately collapse, kicking out methoxide. So the ester will initially be reduced to an aldehyde. But now aluminum hydride will reduce the aldehyde further. Another lithium aluminum hydride compound will reduce this aldehyde into an alcohol. So we have to add 2 hydride ions to go from the ester to the alcohol. Now in the second step, we're going to add H3O+. So this oxygen will grab a hydrogen, and then it's going to turn into the alcohol. Now lithium aluminum hydride reduces not only the ester, but the ketone as well. So here's the ketone. And it only needs 1 hydride ion to reduce it. Once it adds, the oxygen with the negative charge will grab a hydrogen from H3O+, producing the alcohol. So that's how lithium aluminum hydride reduces the ketone. So using LaH, also known as lithium aluminum hydride, the ketone will be reduced into an alcohol, the alkene will be unaffected, and the ester will be reduced to an alcohol. So this is going to be the product if we use answer choice B. So we don't want the ester to be reduced. Therefore, we can eliminate answer choice B. Now what about using sodium borohydride? NaBH4 is not strong enough to reduce the ester. However, it can reduce the ketone into an alcohol. So NaBH4 is the answer, because all we want to do is reduce the ketone into an OH group. Now the mechanism that we use to reduce the ketone to an alcohol using lithium aluminum hydride is the same for NaBH4. So C is the correct answer. Now what about answer choice D, a Grignard reagent? The reason why D doesn't work is because, for one, the Grignard will attack the ketone and the ester, but it does so by adding carbons. We don't have any additional carbons, so that's why we can eliminate D. But let's go over the mechanism for this reaction. So this is C6H5 is basically a phenyl ring. It's a benzene ring. So the phenyl group will attack the carbonyl carbon, and we're going to get an oxygen for negative charge and a phenyl group, and then H3O plus will be used to add a hydrogen to the alkoxide ion, and so that will give us this alcohol. So that's how the ketone will be converted to an OH group using the Grignard reagent. But instead of adding hydrogen, we're adding a phenyl group or an R group. Now what about the mechanism between, let's say, an ester and a Grignard reagent? So let's go over that example. It's similar to the reaction between lithium aluminum hydride and the ester. We need to add 2 R groups as opposed to 1. So we're going to add the Grignard reagent to it. The phenyl will attack the carbonyl carbon, and then we're going to get a tetrahedral intermediate, which looks like this. And then after that, it's going to collapse, kicking out the methoxide ion. So now we're going to have a ketone. And then another Grignard reagent will react with the ketone, converting it into an alkoxide ion. So notice that we've added 2 phenyl groups at this point. So now we need to quench the reaction with acid. So this oxygen will grab a hydrogen, turning into a tertiary alcohol. So therefore, using the Grignard reagent followed by H3O plus will produce this compound. The ketone will turn into an alcohol by the addition of a phenyl group, and the ester will be converted to an alcohol by the addition of 2 phenyl groups. So the correct answer is answer choice C. 99. Which compound is most stable given the heat of combustion in kilojoules per CH2 group? Is it compound 1, 2, 3, or 4? The most stable compound is the one that releases less energy. So if you take away the negative sign, look for the smallest number. 658 is less than 663, it's less than 674 and 691. So ignore the negative sign and look for the one that has the lowest energy, or that releases the least amount of energy during combustion. So answer choice C is the right answer. Now let's talk about why that's the case. And let's use a potential energy diagram. Let's compare compounds 3 and 4. Now both compounds represent a hydrocarbon. And all hydrocarbons during combustion produces the same products, CO2 and water. Therefore, the energy of the products will be the same. So let's say compound 3 starts here. It goes up and then it goes down. P represents the energy of the products. Compound 4 is going to start at a higher energy level, but it's going to end up at the same position because the products are the same. The energy difference between the reactants of compound 3 and the products, that's going to be 658. It's negative because as you go from reactant to product, the energy decreases. You're going down the hill. Now between compound 4 and the products, it's 691. Now notice that compound 4 is at a higher energy level than 3. As the energy increases, the stability decreases. So because compound 4 is at a higher energy level, it's less stable. Now because compound 3 is at a lower energy level, it's more stable. So as the energy decreases, the stability increases. So therefore, as you can see, the compound that is most stable is the one that releases less energy. 100. An unknown molecule with the molecular formula C7H12O undergoes hydrogenation to give an optically active compound that is resistant to chromic acid oxidation. Which of the following compounds could it be? Is it A, B, C, or D? The first thing that we should do is calculate the IHD, the index of hydrogen deficiency, or the degrees of unsaturation. And we could do so using this formula. It's 2n plus 2 minus the number of hydrogens divided by 2. N represents the number of carbon atoms, which we have, which is 7. And we have a total of 12 hydrogens. Now, if you have elements such as nitrogen or fluorine, those elements will affect the number of hydrogen atoms. So any element that is in the same column as nitrogen, like phosphorus, decrease the number of hydrogen atoms by 1. For any halogens, increase the hydrogen atoms by 1. For chalcogens like oxygen, sulfur, or even selenium, you don't have to make any changes. So we don't have any nitrogen or nitrogen, phosphorus, or fluorine. We don't have that. So we don't have to change the number of hydrogen atoms. 2 times 7 is 14, plus 2 is 16. 16 minus 12 is 4, and 4 divided by 2 is 2. So the IHD is equal to 2. Now, what you need to know is that a double bond has an IHD of 1, and a ring has an IHD of 1. A triple bond has an IHD of 2. So looking at compound A, we have 1 ring, 1 double bond. So the IHD is 2. For compound B, we only have 1 double bond. The IHD is 1. So B is eliminated. C has a ring and a double bond, so the IHD is 2. And the same is true for D. So the IHD can help you to eliminate certain answers. Now let's move on to the next information. The problem stated that the optically active compound is resistant to chromic acid oxidation. And this is after hydrogenation. So Hydrogenation, which is adding H2 and a catalyst like platinum or palladium, it doesn't affect an alcohol. So the alcohol won't change during the reaction. And we know that tertiary alcohols are resistant to chromic acid oxidation. Secondary alcohols can be oxidized. So answer choice A has a secondary alcohol, so we can eliminate that. C and D both contain tertiary alcohols. Now the last thing that we need to deal with is the fact that the compound is optically active upon hydrogenation. So looking at answer choice C, once we add hydrogen gas, the double bond will disappear. The alkene part will be reduced into an alkane. And so we're going to get a molecule that looks like this. Now for answer choice D, upon hydrogenation, the double bond will disappear as well. So which of these two compounds is optically active? This compound is optically inactive. For one reason, it doesn't have any chiral centers. That carbon is not chiral. The left side is the same as the right side. And also, there is a line of symmetry here. So due to that fact, this is optically inactive. For this compound, it has a chiral center. We have a methyl group, an OH group, and the left side is different than the right side. The right side has a methyl, the left side does not. So D will yield to an optically active compound upon hydrogenation. So D is the right answer.